segundinho. Já. Good morning, everyone. So you have one more day of our meeting, the third Brazilian meeting in category theory. And today we're going to start with a presentation from Peter Arndt from Düsseldorf. So thank you, everyone, for being here. Thank you, Peter. You can start.
Okay. Welcome, early birds. So I'm going to give this talk, which is about figuring out questions of definability, definability of classes of structures by logical formulas. That's a thing in model theory. And I want to say a disclaimer before starting. So this involves lots of, in principle, pretty complicated notions. There'll be accessible categories in classifying toposes and geometric morphisms. If you are in principle interested in these things, but if you think along the talk this is over my head, then hang on, because the point of the talk is that I can boil this down to very simple questions to just about functor categories and pre-sheaves. So it will all become easy at some point, but until then you might be scared. Okay. So definability. So this is the situation I want to treat here. If I have, actually, where's the pointer? Center? Okay, whatever. I point with my hand. I want to treat this situation. Let's say we have two categories of models of some first order theories, T and S. And we want to ask what's the image of F? So can we describe it by extra formulas in this language of S? Is it everything, maybe? So, very general question. There's tons of questions like this in mathematics. Representability questions. So here's a warm-up example. So we could ask if the second one is the category of abelian groups, and the first one is the category of rings. You could ask, is every abelian group the underlying additive group of some ring? Right? This one is not thoroughly solved. There's not an open question, but that's the kind of question I want to treat. And, well, as I said, it's about definability. So you could also ask, well, it's this image of F can be described by adding some more axioms to the theory of S. Can I delineate this by some formulas that have to hold in order to be in the image of S? Or more generally, I could, for any such functor, I could just ask, okay, what are the first order sentences satisfied by everything in the image? So that would form this theory of the image. Then I can ask, okay, what models of S satisfy those sentences? So there's this Galois connection. It's a sort of a closure operator. We ask just about satisfaction of formulas in this image. Okay, that's a bit abstract. So let's go to an example that illustrates very well what I want to treat here. It's a classical example from lattice theory. Lattice theory was fashionable in the 50s and 60s, and they had a big problem. It was sort of like Fermat's last theorem of lattice theory, the Dilworth congruence lattice problem. It was asking, so if you have a lattice, it's an algebraic structure with meets and joins satisfying equations. So there's a notion of congruence. It's an equivalence relation such that if you quotient out by that relation, the operations are still well defined on the quotient, right? So to any lattice, I can associate its congruence lattice, or actually what I need for this one here is just the compact congruences, those that are generated by finitely many equalities that I want to hold. Compact congruences. And Dilworth asked, is every distributive semilattice, that's the kind of thing that pops out here, a congruence lattice? So why did he ask this? Because he proved that every finite DSL is such a congruence DSL. well, he proved it supposedly, and Gretzer-Schmidt wrote it down later. There was another partial answer later on. Hoon proved that every DSL of cardinality at most Aleph 1 is of this kind. So this image seemed to be pretty big of this functor. And then it was resolved eventually by Wehrung. He proved that, well, it's not essentially surjective, this functor. There are congruence DSLs. So Wehrung proved that there's some non-congruence DSL of cardinality Aleph omega, and then Ruzicka lowered it to Aleph 2. So these kinds of crazy things can happen. So these notions of lattices and so on, they don't have to tell you anything. I'm just telling you this kind of thing can happen with the functor. Yeah, that at some later cardinality thinks the difference kicks in. So here's a corollary that informs the kind of thing I wanna go after in this talk. So there cannot be any first order sentence that distinguishes general DSLs from congruence DSLs. Why? If there was such a formula phi, well, then we could take a model of not phi, something where it doesn't hold. It would need to be something of cardinality Aleph 2 at least, yeah, would be outside of this image. But then we can use downward Löwenheim's golem, shrink it to a countable thing that satisfies exactly the same first order sentences. But well, then we are in the image and it would have to hold, so that can't be. Yeah, so this implies that the image is not first order definable in any way. So the general picture that you would have for such a thing, a functor, yeah, it creates some image in this target category, and you might imagine some well-delineated thing, but actually it's more like this. It's dense in there. It's literally dense actually in some topology, the topology where the closed classes are those that are definable. Okay. So here are my 3 questions that are, or like example questions. So you will see, I'll answer. There's a bigger range of things I can answer in the end. So yeah, I want to ask in general, what is the elementary class? So that means, you know, the first order definable class or closure in this topology generated by the image of F. But actually my methods are not about first order logic. They're about something else, about kappa geometric formula. So that's a different fragment of infinitary first order logic. It's not the finitary usual first order logic that you know probably. It's another language. So that's, for this one I have some methods that I want to show. Okay, so what are kappa geometric formulas and kappa geometric sequence? Kappa geometric formula is built from atomic formulas, so you know, stating the validity of some relation or some equations between terms by using infinitary disjunctions, also infinitary conjunctions, but at most with less than kappa constituents in this disjunction, and also existential quantifiers over less than kappa variables. These are my ingredients. I can build formulas from this, and I can ask, yeah, it's just the obvious semantics. I can ask when is this true of a structure and when not. And there's this notion of kappa geometric sequence. So I can do one more thing. So if I have 2 kappa geometric formulas, I can ask if some implication between them holds with the for all in front. So really, this comes from a sequent calculus. Then it's less awkward to have this single implication. It's actually a natural thing. So that's the kind of theories I wanna build out of my structures in the image. And well, there's also I could also ask what negations of geometric formulas hold in the image. That's a special thing that I also can say something about. Okay, so that's the question that I'm gonna ask. Now I'll talk about accessible categories. What is that? I have to fix this cardinal kappa here. There's this notion of kappa-directed diagram. What's that? It's a diagram such that any set of less than kappa objects admits a cone somewhere inside the diagram to some other object of the diagram. Okay, and that this notion of kappa-directed diagram it allows us to formulate the notion of kappa-presentable object. What's that? It's well, the formal definition is this one here, homing into a column of a kappa-directed diagram well, that should be the same as homing somewhere in a finite state of this diagram, or kappa, less than kappa stage of this diagram. So this exactly captures actually what you would think, for example, if kappa is Aleph 0, what finitely presentable means. Yeah? So in the category of groups, for example, this exactly means finitely presentable. Finitely many generators, finitely many relations that we divide out. The intuition is that, well, if you have a such a column here and a finitely presented group here, well, all of its finitely many generators, they have to go somewhere. This will be picked up on a finite stage of the diagram. Okay, that's the two ingredients. We'll use these notions by themselves also, but these are the two ingredients to define what is a kappa accessible category. It's a category which has these kappa directed colimits, and there should be a set of kappa presentable objects such that everything is a colimit of those, so a kappa directed one. So for groups, for example, you know, a general group can be put together by gathering all of its finitely presented subgroups, and all the generators and relations will appear in such a diagram on the way. Okay. So examples, well, all the algebraic structures are actually Aleph 0 accessible, so things defined by equations and operations, for the reasons that I told you for groups. So it's not just those, so fields, the category of fields, for example, is Aleph 0 accessible. A finitely presented field would be one that has finite transcendence degree over its prime field, and is then a finite algebraic extension of that. And well, there's tons of other kinds of structures where this presentability notion makes sense. So here's a pretty general example. So if you have any finitary first order theory, now the usual first order logic sense, over a countable signature, then the category of models is Aleph 1 accessible. So this covers a lot of ground. And also there's other examples where you can just prove by hand that it's accessible, and well, you wouldn't come from such a presentability notion. So here's a theorem. How does this tie to the previous slide? Kappa accessible categories are exactly those of the form models of some kappa geometric theory. That's really a correspondence here. Okay, so that's one ingredient here. I'm going to state some results, and they are pretty unwieldy. So I'm in a funny situation here. I have a proof of something, and I'm not sure what it is a proof of. So the proof is much more insightful than the statement here, so bear with me. This is a bit crazy. So I'm going to put myself in this situation here, right? I have a functor between such categories of models of kappa accessible, of kappa geometric theory, so equivalently just some functor between kappa accessible categories. It should be, that's what's called an accessible functor. It should preserve these kappa filtered colimits. And I need to ask something else. So I can look on both sides at the subcategories of kappa presentable objects. And I want to ask that this functor restricts, so it sends kappa presentable objects to kappa presentable objects here. It's not much of a thing to ask, because if you just raise the kappa high enough, this will happen eventually. So if I just in this situation here, the other one will also kick in for some high enough kappa. All right, so let me at least give you one statement here. We'll prove it, and then I think it makes more sense. So if our functor is essentially surjective just between the kappa presentable objects, well, then the kappa theory of the things in the image is exactly that S. It's such a density situation. Yeah? So the kappa small objects, kappa presentable objects, will not be sufficient to distinguish, and those already determine our kappa geometric theory. That's how you can think of it. So here's an example with this the Dilworth congruence lattice problem. So since we know that this functor is essentially surjective on things of cardinality at most Aleph 1, and we have really Aleph 1 presentable categories here, we know that there can't be any Aleph 1 geometric sequence that distinguish the image from general DSLs. Yeah, so I'm working here in a different fragment than from general first order logic. So we have these infinitary disjunctions and conjunctions. So in that direction there's more possible, but we don't have arbitrary alternations of quantifiers, and so in that direction there's less possible. It's an incomparable language about which I can just say things in terms of definability now. okay, there's some more. So the general idea here is I can give you conditions on this restricted functor between the kappa presentable objects, and then conclude something about the logical validity of things here. So if f kappa is fully faithful, well, then this image, it can actually be characterized by some by adding some more axioms to the language of S. Yeah, so that's not a given. Sometimes it can't be characterized. So if it's fully faithful, then it can. And well, here's a funny one. So if everything in B, in the target category, admits a homomorphism to the image of F, well, then the image of F and B, they satisfy the same negations of geometric formulae. Okay, now comes the interesting part. How do I prove this? And actually, you can get more out of this proof. So I had a hard time actually formulating results. I like the proof much better. This goes into topos theory. So Grothendieck topos means topos in this talk. What's a Grothendieck topos? It's a reflexive subcategory of some presheaf category with a left exact reflection functor. That's one possible definition. And well, we've heard about this example here, right, in Anna's course. For any topological space, we can create this topos of sheaves, set-valued functors satisfying this sheaf condition. And that's actually a pretty good embedding here. So it's not just, so it's a functor. So if we have a continuous function here from x to y, then it induces certain functors between the sheaf categories. It's an adjunction. So there's a right adjoint going in the same direction here, and the left adjoint in the other one. And the left adjoint will preserve finite limits. This is called a geometric morphism. And the notion is exactly there to capture this kind of thing that's induced by continuous maps. So for good enough spaces, sober spaces, they can actually reconstruct the space from the sheaf topos. So it's a really something that preserves a lot of information. And also the continuous maps might have properties, and you can describe them in terms of these geometric morphisms. So here's a list. Yeah, if you have a continuous map, it might be surjective. You can just formulate in terms of the functors how that when that is the case. It's precisely equivalent to f upper star being faithful, one of these functors. So it's categorical properties on this side that tell you something about the properties of the continuous map. F is an embedding, so it means it's an inclusion of with a subspace topology on X. If and only if f lower star is fully faithful. And it could be, so the image is dense in X if this is true, and it's a closed inclusion if something else is true. So there's categorical counterparts to this, and they give rise to these definitions. So geometric morphism is called a surjection if f star is fully faithful, and so on. Okay, so that's the topology embedding into topos in the world of Grothendieck toposes. Now, we've also heard that Grothendieck toposes are sort of set theoretic universes where we can interpret logic, but we didn't ever really go into it very, very much, so I have an extra slide here. There's an analogy that I like a lot to explain this, how to interpret, why we can interpret first-order logic in a topos. So think of the collection of continuous maps from some topological space to the complex numbers, C star algebra. This is inherits structure from C. So we can do pointwise addition, pointwise multiplication, pointwise complex conjugation, and so on. So structure of C is inherited, but not the properties. So this here is a ring, but it's not a field. Being a field is a property. Sort of the same happens with functor categories like this, and more generally these reflexive subcategories also. So we inherit structure from set, from the category of sets. For example, we have limits and co-limits. Actually, for presheaf categories, they are literally computed pointwise, like here. So it's operations that we have. We also have such a factorization in the category of sets, right? So every map can be factored by a surjection onto the image, followed by an inclusion. That's also the case in every such functor category, and more generally in sheaf categories. And we can use these two things to interpret geometric formulae. So a geometric formula is, we should think of it as a sub-object of some other object. So free variables correspond to where this should live. And that's what you should think here. So we can interpret conjunctions by pullbacks. This is, if you look at it in sets, this just means intersection. That's what we want to do for interpreting a conjunction. We can interpret disjunctions like this. Well, we have our two interpretations of some formulae. We form their coproduct, which exists. And then we do the image factorization. And so we get a new subobject of X that interprets the disjunction. And also existential, well, if we have something in two variables, it will be interpreted in X cross Y. Then we project down to Y. So we can just form the image of this. Okay. So let's go to the other side. So there's another source of toposes. So geometric theories. For now, it's Aleph 0 geometric theories. They give rise to toposes. Actually, every topos arises like this. It's a surjection here. So what do they do? If you have a geometric theory, there's a so-called classifying topos for that theory. It has the following property. Well, in this topos, there's a generic model of that theory. There's some model there, yeah. So it satisfies the axioms in this sense. You can check them like this. I'll call it UT. And every other model of T in every other topos, it will arise by through a geometric morphism from that topos to the classifying topos. And you take the generic model here and transport it along the left adjoint of the geometric morphism into the target category. So since the left adjoint preserves arbitrary colimits, it will preserve all of these colimit parts here, the disjunctions. And since it preserves finite limits, it also will preserve the finite conjunctions. And then you get a model here, and actually, well, every model comes like that. That's what classifying toposes do. Well, I want to go to kappa toposes. That's a relatively new thing, so developed by Christian Espíndola in a few articles so far. What's a kappa topos? Well, I ask a little bit more about the reflection functor. It should now preserve kappa limits, so bigger cardinality of bigger diagrams should be preserved. And well, we have the same picture here. Kappa geometric theories have classifying kappa toposes, and they have the same property here. Okay. Now, we can draw from this embedding of topological spaces into toposes. So there's something that carries over to all toposes from spaces. Namely, if we have a continuous map F between topological spaces, it can be factorized as a surjection, followed so onto the image simply, followed by an inclusion, which is just the subspace included into Y then. And this inclusion we can further factor into a dense inclusion, to just take the closure of the image, followed by a closed inclusion. That's a factorization that we always have in topological spaces. We have the same factorization in toposes. It's a bit, we know we have the notions for a geometric morphism, what it means to be a surjection, dense inclusion, and a closed inclusion, and this factorization always works actually. The construction is a bit unwieldy, but in general, so you take some co-algebras, category of co-algebras for a co-monad here and so on, but well, it exists. So in particular, it exists for classifying toposes. Well, every topos is a classifying topos. And you can ask, what does it mean if we factor such a geometric morphism between classifying toposes into a surjection followed by two such inclusions here? You can actually say what happens here. So an inclusion through a geometric morphism of some other topos into this topos here, it corresponds to adding more geometric axioms to our theory here. So which one? So if we start with a classifying topos here for some theory and go to that one, well, it will correspond to an S model in that topos. That's what classifying toposes do. So there's a particular S model here, and well, we can form the theory of that S model. Which geometric sequence are satisfied by that model? That might be some more axioms. That might be a special thing. It might be the zero ring, for example. It satisfies tons of things. So it has its own theory, and that's what is classified by this thing here. And well, the other intermediate topos that shows up is, well, it's a classifying topos of the theory of just negations of geometric formulae that hold for this special object. Yeah, this is worked out in Olivia's book. Cool. So this I want to use now to say something about these axiomatizability results. Yeah, so a little result on the way. So since I'm passing to the world of kappa toposes, not just toposes, well, this factorization, it carries over. It still works. The standard construction is still okay. Yeah. But actually, we don't have to rely on this. So that's the point of the talk. Now we'll go to something much easier. We don't have to rely on this general construction, taking co-algebras of some comonad here and so on. That's really hard to figure out what actually what kind of category this is in the end. We're in a good shape here. We can always pass to the world of pre-sheaf toposes in this setting. This is really good news because those are much easier. So here's why. If I have some kappa accessible categories, so my categories of models of kappa geometric theories, so that's maybe for the experts, the intermediate stuff. Well, it's the int completion of the kappa small objects, which can be described as kappa flat functors, blah blah blah. In the end, the result is every kappa accessible category like this is the category of models of some kappa geometric theory like this, and there is a pre-sheaf topos classifying that theory. So that's not at all true for if you restrict yourself to finitely accessible categories or something. Oh no, there it might actually work. But you know, in general, so if you stay in the world of non-kappa toposes and geometric theories, sometimes you can't escape having a non-pre-sheaf topos here. But if you allow this extra parameter kappa, you can always get yourself into the world of pre-sheaf categories. And I'm sort of getting around the problem from yesterday's talk of Thiago Alexandre. So I always am in this situation where my category is a category of points of some now kappa topos, kappa geometric theory. Okay, but that's good news. So what I want to do now is factorize a geometric morphism just between pre-sheaf toposes, and that's an easy thing to do. Yeah, so I'm back into my original situation here. So I have a accessible functor between two categories of models of kappa geometric theories, which restricts to the kappa small objects here. And well, my conditions here that I wanted, that we have this commuting square and so on, they boil down, or they allow me to conclude that this functor is induced actually by a functor of between the theories, between the classifying toposes of these theories. Yeah, so this functor arises. So what is A? A is kappa geometric morphisms from set to my classifying topos, and I can post-compose this with that geometric morphism to S, and then I'll get something here. So under my conditions on the functor, it arises like this. And now I'm gonna use this. So I have such a functor here, so such a geometric morphism, and I want to factorize it. So here's the good news. Now it's a functor between pre-sheaf categories, and here I can actually do something very easy. So here's the proposition. I got this joint with Eduardo Ox in some discussions. So, I mean, I have these small index categories, C and D, and I can just look on those what's happening. Yeah, those would be my kappa small objects. So I have this functor here. That's the restricted functor on the kappa small objects. What can I do? Well, I can map it to its image in D, take the full subcategory on the objects in the image, and then I can include this to the category of objects, full subcategory again, which admit a morphism to the image, and then I can include that in here. And this will induce, so so this is a bunch of functors between small categories. I can pre-compose with these and can extend them, and then I get geometric morphisms, and that's my factorization. It's really easy in this special case. Okay, so here's the first, so this part A of the theorem I announced, so here's the first proof of such a thing. So if my functor is essentially surjective on the kappa small objects only, well, then the second part, that's just an equivalence. Then I have the same categories here. G of C is D in that case. So the second part will be just an equivalence. And so the theories classified by these two preshift toposes are the same. That's exactly this density situation. I can't distinguish the theories classified by the two here. So that's how I got to this theorem A. But actually, you can do more. So here comes the part where I say, okay, I have a proof, and I have a hard time formulating what it proves. So we can use this in a more clever way, actually. So we have this density statement that we can't distinguish the image by actual formulas whenever we have such an equivalence. It doesn't. But there's more situations where this happens. So what we just need is the preshift categories to be equivalent. So G of C should be Morita equivalent to D. That's enough. And let me give you an example. Yeah, so that's the sufficient thing. It was a long-standing open problem asked by Tarski. If in usual first-order logic, you can distinguish the free group on n generators from a free group on another number of generators. This was open for many years, and then solved in 2006 by two teams of authors simultaneously. So the answer is no. In first-order logic, you cannot distinguish. The free groups on a finite number of generators, they all satisfy exactly the same first-order sentences, no matter what's the number of generators. Now, if you pass to infinitary logic, that's no longer true. So here's a simple sentence that tells you, I have that many generators. But this is not a geometric sequence, right? There's an alternation of quantifiers. So now I can show to you that there must be geometric sequences that also do these distinctions, but I cannot pin them down, actually. I don't know any example, but I can prove to you that that exists. And often that's enough in model theory to just know about definability without having the concrete formulas. So how can I figure that out? I want to pick out the free group on n generators. What do? Well, it's a usual group. It lives in the topos of sets. So it's classified by geometric morphism to the classifying topos of groups. That's actually a usual one topos. So it's not a kappa topos. It's a standard topos situation here. So what's the geometric morphism? Well, it takes the generic group and maps it to my Fn. Both are preshift toposes. Set is just set to the 1-point category. And so what do? What is the classifying topos of groups? It's set to the finitely presented groups without an op. Actually, that's wrong. So now I apply my factorization for presheaf toposes. Well, I just see where this point gets mapped. Well, it gets mapped to the free group on n generators with op, sorry for that. And picks out that one. And I do the same with a different number, m. Now I have to compare these two toposes. Are they equivalent or not? Well, as such, it's not easy to see, but I can go for Morita equivalent. So do these categories? It's a one-object category with all morphisms of these groups, right? Do they define the same preshift category? What do I have to do? I have to go to the Carubian envelope, to the idempotent completion. Then I can compare them. If those are equivalent, then I have the same preshift categories. Well, and I removed the op now in this slide. Very good. Well, they're not the same. So what's the idempotent completion of this one object category with just the free group? I have to look at all the idempotents in there. An idempotent will carve out a subgroup of this one. All subgroups are free of free groups, and in general there can be more generators in a subgroup of a free group. But if it's a reflective subgroup, then its number of generators is bounded by that n. So for n, I get all the free groups up to n. For a smaller m, I just get all the free groups up to m. It's different categories. And so we have different classifying toposes, and so they classify different geometric theories, and we know there must be a formula distinguishing the two. That's pretty concrete, and you can really carve out things by considering these small categories here. Okay. Yeah, so that's my conclusion here. Yeah, since I have maps, so also there was this part 3 of the theorem saying, okay, if we just have maps into the image, then that says we have the same negations of geometric formulae holding on both sides. That's the case here. I can always map from a free group to some other free group. So It's also a piece of information. So the distinguishing formula must be an actual sequence with formulas on both sides, not just a negation of a geometric formula. Okay. So that's the technique I wanted to show you. Yeah, if you introduce this kappa, you land in the world of pre-sheaf toposes, and you can just consider the small index categories and maybe their idempotent completions to figure out stuff about definability. Okay. Yeah, I should have said it on this slide, but okay. And the kappa is crucial for this, right? So this wouldn't work just in the world of usual toposes. It's really raising the kappa that brings us always into this situation that we have an essential morphism, so one that is induced by maps between the small index categories. It's only the kappa that brings us into the pre-sheaf world to begin with, and it's the kappa that makes the factorization easy, really. Okay. So that was the main part of my talk. Just advertising this little twist here that brings you to a good and easy situation. So some outlooks on where this can go. So in a topos, you cannot just interpret first-order logic. You can also interpret type theory, and in an infinity topos, you can work with homotopy type theory, and so that's a very powerful and rich language that can be used very well in lots of situations. But it's like so also in a usual topos, you can interpret all of first-order logic with quantifiers for all and exists alternating as you wish and so on. It's just that these formulas are not preserved by the inverse image of a geometric morphism. So this fragment of geometric logic or kappa geometric logic, we look at it because that's what is preserved under geometric morphisms. That's where this whole thing of classifying topos works. But in general, there's a richer language that you can also employ. So it's an open question that a bunch of people is working on right now. What would be the fragment of type theory or of homotopy type theory that is preserved by geometric morphisms? It's not so trivial to work this out, and people are wondering and working on it. But yeah, I sort of, before they got there, I already provided one of these theorems because my factorization, it works also for infinity 1 toposes. It's just a bunch of Kahn extensions that just go through. Okay. Another question that comes with this here is the following. So there's a bunch. So there's general geometric theories or kappa geometric theories, and there's a bunch of better ones. So you can ask for coherent theories, regular theories. So there's fragments of this which are better behaved, and so there's also the theories of pre-sheaf type. That's my result, right? So if we allow ourselves to introduce this kappa here, we can always get into a better fragment of geometric logic, which is the theories of pre-sheaf type. They don't allow a really neat syntactic description. Which theories are these? I really don't know a good answer here. But raising kappa does not just bring us into this nice fragment of pre-sheaf type. It brings us often into much better fragments, actually, into, for example, Horn theories. What's a Horn theory? It's one where we just use atomic formulas and conjunctions between these. No disjunctions, no existentials. It's a much easier fragment. So with this kappa, if we introduce infinitary conjunctions, we often get from things that are geometric to actually Horn theory. So we can get into even better fragments. That happens a lot. So here's an example. An Archimedean field is one where every positive element has this property that if you sum it often enough to itself, you get bigger than any other ones. There should be for all y in front. And that's geometric. Well, it's not a Horn theory. It uses a big disjunction here. But you can turn it into an infinitary Horn theory if you allow yourself infinitary conjunctions. That's what we are doing now with passing to the kappa geometric theories, right? This will happen a lot because you can just, if something is on this side here, you can negate it and it will flip the infinitary disjunction into a conjunction. And it's just a negation of this formula now. So what's the benefit of having a Horn theory? Here's another example, divisible groups. So it's a question, when precisely does this happen? When do we get Horn theories? It's just something that I see happening in lots of examples. I don't have a general answer, but would be interesting. So how can we use this? So there's a cool phenomenon in topos theory. So it's often the case that you have this if you have a classifying topos, you have this generic model in there. So let's take the classifying topos of the theory of rings. There's a generic ring in there. It's actually a pretty concrete object, but I don't go there now. And sometimes these generic objects, they satisfy additional formulas that are non-geometric. Yeah, so it's true, and that's amazing, that the generic ring is actually a field in this sense here. If an object is if an element is not zero, then there is an inverse. So of course that's completely wrong for general rings. And if this were a geometric formula, then it would be transported to every other ring in every other topos, so we know it's wrong. It can't be true, right? There are rings that are not fields. But the generic ring satisfies this non-geometric sequence. And what does that mean? So if we want to prove something about all rings with a geometric formula that's valid for all rings, well, we can actually just prove it for that universal ring, for the generic ring. We can work on that topos and figure out stuff that satisfies, and then it will be transported, if it's a geometric formula, to every other ring. And this says, without loss of generality, we can assume that our ring is a field in this sense. That sounds crazy, right? It's just, okay, the catch is that we have to use intuitionistic logic, and then you don't get that much out of this fieldiness. But it's still, I mean, it's useful. It's in many cases. So there's this project of synthetic algebraic geometry that some friends of mine are pursuing right now, and they do algebraic geometry on top of the generic local ring, and they use tons of these things. So the generic local ring is also a field, and that's a thing, for example, that happens for Horn theories. So rings are a Horn theory. And such non-geometric sequences are passed down to localizations easily if you have a Horn theory. So there's a bit of benefit that I wanted to point out. So to be able to go to the Horn formulas. Yeah, there's a wonderful paper or preprint by Ingo Blechschmidt who figures out these things. So actually, he figures out the master axiom, so that is satisfied for the generic object of any theory, and all the non-geometric sequence that hold for that generic object, they follow from a single axiom, the synthetic quasi-coherence axiom. And yeah, he has an extra chapter on Horn theories, which really makes things much easier. And so that's a place where we can go to in the Kappa world. I still have to see if everything in here generalizes to the Kappa world, but my experience so far is that the Kappa doesn't harm anywhere in most proofs of topos theory. Okay, as I foreshadowed, so where is this used? There's this cool idea that is used a lot in topos theory of synthetic versus analytic mathematics. So what is that? So synthetic mathematics means you just axiomatize the thing you want to talk about. So for example, Euclidean geometry, you put axioms like, so you have two kinds of things. You have points and you have lines. And you say, okay, if I have 2 points, then there's a line that goes through them, so I can produce a line from points. You just axiomatize what happens with your basic objects of consideration, and you don't define further what is a point, what is a line. In analytic mathematics, you do that. Yeah, so it's mostly based on set theory. You say, okay, what is a line? It's a solution set, or of such an equation here in the plane, given by coordinates over some field. So it's often, so this is sort of like if you have a synthetic theory, it sort of allows you to concentrate on just the thing you want to talk about, and not in sort of theoretic arbitrary encodings of this thing, right? So it's often very nice to read proofs in here, because they really just concentrate on the subject matter and not on some crazy constructions that encode it. So there's tons of these fields. So there's synthetic differential geometry, that's really a topos subject, which sort of axiomatize and emulates standard differential geometry, which is about manifolds, which are point sets with some differentiability stuff and so on. There's more fields. There's synthetic probability theory, which synthesizes measure theoretic probability. There's synthetic algebraic geometry, which I mentioned, which is a much nicer way to talk about schemes. It's like the old Italian algebraic geometers who considered point sets, solutions of polynomials. You can really talk in that way about your geometric objects in this world, while secretly talking about scheme theory, but that's hidden in some topos environment. There's synthetic computability theory, and so on. So it's a bit, so if I tell this to my computer science students, it's a bit like a high-level programming language here. So Python, you have a package that does it all for you, and this is like, C, where you have to, allocate memory and so on. You really go into the nuts and bolts of things. Everybody wants to prefers a high-level programming language usually, right? So, and that's where these extra non-geometric axioms come to play. So usually you develop such a synthetic piece of mathematics, like synthetic differential geometry, in a topos, which has, for example, the generic C-infinity ring that we will probably see at the end of the mini course somewhere. And you can ask, okay, what extra non-geometric axioms does it satisfy, and how can I use them? So this is really a place where this Horn theory-ness of our axioms comes to play. And well, more generally, so being synthetic or analytic, it's not an absolute notion, right? So we can emulate Euclidean geometry in analytic geometry, just by playing coordinates here. But then you could further say, okay, but there's an intermediate thing. We have maybe a synthetic linear algebra. It's a bit like what João Paixão does, right? Which also doesn't really talk about coordinates or stuff. It's an intermediate thing. So there's something can be analytic relative to something else, or synthetic relative to something else. And so the picture that's emerging in all of these fields now, it's a web of toposes where you can emulate one thing and another thing. And so, for example, in the classifying topos of Euclidean geometries, it's just some axioms that you give, so it has a classifying topos. Is this in the right direction? I'm not sure. Well, if you are the classifying topos of fields, then you have a field there, and you can emulate. You have a model of these axioms here, right? Yeah, that's the right direction. You can pull it back. So this landscape of synthetic theories, it sort of corresponds, at least where it's not where it's geometrically formalized. It corresponds to a web of toposes which emulate the target theories, right? So, and well, I think it's worth going to kappa topos in this web here. So this is something that's being it's also very, very new work. People are trying to get to know this picture here of synthetic mathematics, and there's even a synthetic mathematics of synthetic mathematics right now, or like it's work in progress by Ulrich Buchholz and Johannes Schipp von Branitz. So I think that's a really neat picture that's emerging here about the landscape of mathematics, and I think maybe including a kappa here will give people a much easier time actually to figure out stuff. Okay, that's what I wanted to say.
Thank you, Peter. So do we have comments, questions? I think I go there first.
First of all, the slides were gorgeous, really, really pretty.
I used the background color of the EBTC. You notice?
That was the touch. I mean, it's a sort of a simple probably question, but you have this hypothesis on kappa being regular. I was just wondering, is that convenient, or is it really necessary?
It's necessary. That's just the theory of kappa accessible categories just works for regular kappa. Okay. Right at the beginning, you need it.
Yeah, because I was wondering, even synthetically, because you have this. I mean, you define the syntax of. I mean, it's way in the past, so maybe it doesn't. But I think that then if regularity is what you need also for even for the conjunct existences to match.
No, to just you could define kappa geometric formulas just for any kappa. That would be fine.
Okay.
But yeah, for the link to accessible categories, you need it to be regular.
Okay.
Thank you, Peter, for a beautiful talk. It's amazing. As for a comment that I like very much this kind of integration between two forms of abstract or categorical model theory, accessible categories and topos theory. I recall that in Mackay Paré book, there is this construction called the powerful image of accessible functor that seems related to this, but there is no topos application there. So the technical stuff becomes much harder. And this direct connection between presentations of topos by logic, and there is also a presentation of accessible categories by formula, seems very useful and enlightening the situation. So thank you very much. We have many things to do concerning examples to deal, of course.
Yeah, of course. The special group is what motivated all of this. There's an open question that brought me to this thing, actually, a particular reasonability question.
Oh, yeah. Thank you very much.
So I look up the powerful image. I didn't know that. Thank you.
Thanks, Peter. Kind of quite interesting. I wanted to go back to the first motivation. Do you mind repeating to me what was your Dilworth?
Dilworth congruence lattice problem, right?
That connects to the synthetic versus analytic.
Oh, I'm not sure it does. Maybe that's just a different thing. Wait, where are we? Here.
Yeah,
go.
there. What's congruent lattices in terms of, I mean, they all look analytic somehow, right? They don't look synthetic at all. And I mean, the question here is about the Aleph-2. Do you have any reason for Aleph-2 being the one that doesn't, where the thing?
I know, I didn't, so the proof is extremely complicated. I mean, I thumbed through it and no, I don't know. I don't know why Aleph-2. I mean, I know a tiny bit about Währungstechniques, but he got an Aleph Omega, so it was, which is not regular even. No, I don't know anything about this. But this is not part of the synthetic mathematics picture, so I don't think that's an instance of this.
Yeah, I just wondered kind of if it would be connected eventually, but it didn't look like at the moment. But
no, to me not either.
Well, thank you very much in any case.
Let's thank Peter again.
Hello, can you hear me? Not yet. Testing 1, 2. It's closer? Oh, okay. I see. Right, okay. Yep.
Hello, so the second talk will be given by Benjamin Merlin Bumpus. He is now from the University of São Paulo. He's a professor there now. Thank you so much, Ben, for being here. You can start.
Thank you so much. Okay, so today I had a little bit of a hard time deciding what I was going to talk about because this work that I'm going to be talking about today is part of a broad set of papers. In fact, there's going to be 6 new papers released in the next, hopefully, half a year. And so it was a little bit hard to decide what to talk about without going crazy on new stuff. So I figured that usually a good talk is a talk where people understand what I'm talking about. So I'm going to try to stick to few things and make them simple and try to outline a program. So I'm going to start off with a little announcement. It has nothing to do with the talk. Then I'm going to be talking a little bit about the research program more broadly. Hopefully this is a research program I can get everybody excited about. And next year, everybody will be doing the same thing. And then I'll go into the technical parts and we'll talk about the problem that we're going to be studying. It's a computational problem. And the main results. So everything I'm going to be speaking about today is joint work with Ernst Althaus, who's in Mainz in Germany, James Fairbanks, the University of Florida, Daniel Rosiak, who's at NIST in Washington, D.C. And then what happened is that we had written a paper, first the 4 of us, and then afterwards Emilio Minichello from CUNY joined and helped us clean things up a bit. All right, so let's start off with the announcement. Announcement is that there's a new website, which you can find at this address. So what's the point of the website? The point of the website is to have a compendium of all researchers doing category theory in Brazil, or any researcher who likes category theory and doesn't necessarily do category theory. I don't actually care. The more the better. We want students, we want professors, we want your friends and family. Put everybody on here, okay? So it's important to have a list of people because it's a way for us to show that there is a community of category theory. It's a way for us to get funding. So if people want to say, look, there's a lot of people doing category theory, you point to the website and hopefully there's a big ass list. So everybody get on there. Second thing that's important is that this is also a space for blogs. So I know that we have all of these Cultura Extensão projects in Brazil, and a lot of people ask me, how do I get my students to fill out their Cultura Extensão hours? Get students to write a blog post about something in category theory that you like, and make it a blog post where you explain your work to a broader audience. That way we have a compendium of results, and your students get the hours they need, okay? That's the end of the sales pitch. Okay, so what do? I do categorical algorithmics. I really like the name because I invented it 2 days ago. But it's a new field. And so what is the field? What is it about? So categorical algorithmics is the study of category theory in service of algorithmics. And it is also the study of algorithmics in service of category theory. Okay, so I think of this as 2 communities working for each other. And so in some sense, I think that one should be using category theory to understand the structures that underpin algorithm design and algorithm construction and complexity theory. And vice versa, one should understand algorithms that underpin computations in category theory and what we can do with this. Okay? There's a lot of people studying computationally relevant category theory, especially in ACT. And so this is starting to grow, and I think the field needs a name, so that's the name. All right. So what are we talking about today, more specifically? Today I'm going to be speaking about diagrams and dynamic programming. So a little bit of my background. I came to category theory a little bit later. I started off as an algorithmicist and a graph theorist. And so I was studying these things called tree decompositions on graphs. They are basically the biggest tool there is in theoretical computer science for obtaining fast algorithms for NP-hard problems. The idea is that you break up your graph into little pieces, and it has some horrible looking axioms that are stated very combinatorially. And during my PhD, I found category theoretic way of writing down these constructions. And that's what got me into category theory in the first place. And the point is that when you have an object that's broken up into pieces, what you want to do is solve your problem on the little pieces and join up the solutions. Okay, so that's what we're going to be doing today. And if I'm going to break something up into pieces, it makes sense to think about diagrams. That's the most naive thing to do, and it works. So let's do it. So the computational problem I'm going to be studying is the initial limit problem. So here's the story. I think of a diagram in a category as a set of equations. So the objects of your diagram are variables, and the morphisms of your diagram are specifying some sort of conditions on these variables. And so whether this diagram has a limit that is initial or not, I can interpret this as my system of equations having a solution or not. Okay? And so this is exactly what we're going to be doing. We take a diagram where J is finite, and we have a finitely complete category E. And I want to know, this category has an initial object, which I denote as empty set. And I want to know whether the limit is initial or not. Okay? So what's the pipeline? Why do I care about this in the first place? So many computational problems can be written down as presheaves from some category of interest. Think of, I don't know, the category of graphs, into set, where I attach a set of certificates. So, for example, take the 3 coloring problem. I let K3 be the graph on 3 vertices, no loops, simple graph. Then the representable on K3 is exactly proper 3 colorings. Okay? And there's many applications in categorical databases, topological data analysis, constraint satisfaction, you name it. And my student Anni, who gave a poster, she's here, she was gave a poster presentation on Monday, outlines a lot of problems that you can write down as presheaves and how to think about them. So the point is, I think of this as a mapping that takes an object to a set of certificates for my problem. Okay, so these are witnesses of the structure I'm looking for. Now, if X is large, then it's in most cases hopeless to try to write down this set and just compute P. The decision problem is basically asking whether P is empty or not, right? So this is the functor that goes into the walking arrow category. I send a set to true if it's non-empty. So if X is large, this is far too expensive. I can't just write down this set. And the problem is, especially, you might think, well, if I have a lot of certificates, it might be easy to find one. I might just be able to randomly pick one. But if there's very few certificates, for me to prove that there is no certificate, to distinguish no certificate versus one certificate, is very hard, right? So I have to end up searching my entire space. So the point is, let's break X up into little pieces. Let's solve our problem on X. So this is kind of the pipeline. And the results, all the results we'll be talking about today, you can fit. Anytime you have a presheaf like this, you can apply these results to. And so just making this formal, pick some diagram J, and solve on the pieces and join it up. Okay? And so this talk is going to be trying to tell you how. How do we actually do this? All right, so this is the main theorem. It's a mouthful. And so first of all, we're going to be talking about a special kind of diagram. Can I point? Oh, wow. Pretty cool. So I have a special kind of diagram. Don't really have to care about this right now. I'll talk about this later. But our result works for diagrams that are particularly nice, or the algorithm works for that case. And the idea is you're building a category here starting with an n-vertex graph, G. And I have some property about this graph, which you can forget about for now. It's just some measurement on this graph. And I'll let W be the maximum size of any of the sets that I produce in the image of D. And then the point is that there's an algorithm that decides this initial limit problem with a running time that is exponential in K and W, then square in W, and linear in N. I know there's some people who do algorithmics here. If this looks suspicious to you, I'll explain later. Okay. But this is what people call a fixed parameter tractable algorithm. So for fixed K, then this is now linear in N, right? So this is really good. We want linear in N. N is the number of pieces in my decomposition. Okay? So the point is that k is controlling something about your input. When k is fixed or small, you can get away with something you wouldn't ordinarily be able to get away with. So why is this good? So the naive algorithm would be just compute the limit. You know, I look up in Reel's textbook, how do you compute a limit? And you do it, you know, just by brute force. And you end up with something that looks like this. So you got some exponential in the size of the piece, the biggest piece you have, number of objects in your diagram, number of morphisms here. So just for reference, if I have 100, if my diagram has 100 pieces in it, and the maximum size of any set I attach to each one of these pieces is 5, the brute force algorithm takes, you know, number of steps that's bigger than the number of particles in the universe. Our algorithm takes 2,500 steps. Okay? So does anyone want to run this one? Okay? Cool. Me neither. So the point is, I'm going to tell you about how do you get this. So let's do a little warm-up. So simpler problem. I give you a diagram, and you can do one of two things. If the diagram is not discrete, you throw your hands up in the air and you say, I don't know. Okay? But if the diagram is not discrete, sorry, if the diagram is discrete, you better give me an answer, and I want an answer fast. So how do I do this? Does anyone have any ideas? Well, if the diagram's discrete, to check if the limit is empty, I just look at each one of the pieces, and I ask if they're empty, right, of the diagram. The pieces are small, and I'm done, right? I'm computing a big product, right? That's what the limit is going to be. So then all that remains is to check if a diagram is empty or not. But you know, depending on how you store this diagram, you can do this in constant time or in linear time, depending on how you write this down. But the point is, I just have to check if there's at least one morphism in my domain category. My domain category is finite, so you can just store it in a computer as a big graph. Okay. All right, so that's the warm-up. So, okay, what was this? What did I just do? So what the warm-up is saying is we've got this picture. You give me a diagram. So here's my category of diagrams of shape J. I've got two options. I can compute the limit, just brute force, just build the whole limit, and then check if the limit is empty or not. This works, but this is the naive algorithm. This is the thing that takes more steps than the number of particles in the universe. We don't want that. What we just did was just evaluate this on every bag, on every piece of your decomposition, and then take a big AND, right? So this is the limit, logical limit, right? So here I get a Boolean diagram. Okay? Now, when the diagram is discrete, this commutes. So what we just hand waved was you can do this when the diagram is discrete. Sadly, this does not commute when the diagram is not discrete, right? So here's the obvious example. So I have a set with two elements. Their limit is empty. None of the sets is empty. So you can't just compute locally and check whether the sets are empty and decide whether a limit is empty, right? Because this morphism picks out A, this morphism picks out B. There's nothing in the pullback. All right. So the remedy, and what this paper's talk is about, so we're going to construct an endofunctor here from the category of diagrams to the category of diagrams that will fix commutativity. So when we stick this endofunctor in here, now this commutes. Now this is fast to compute because I'm just checking whether sets are empty or not. Okay? This is a big AND. This is fast to compute. So the point is, I'm going to tell you that this thing exists, and then I'm going to tell you that I can compute this fast. Okay? And it's going to look a little weird when I tell you how it's defined, and hopefully no one will believe me that you can compute it fast. And then I'll convince you. That's the plan. And everyone can say, ooh, ah, okay? Right, so this is how you define the functor. Take your diagram, compute the limit. You got a limit cone. Factorize your limit cone with image factorizations. So my limit cone is lambda. I'm going to factorize this. So I'm just pointwise, factorize everything. Does anyone feel uncomfortable with this? Hopefully everyone should feel uncomfortable with this. Because I just told you the point is that I don't want to compute that, right? And I'm defining this thing in terms of the limit. So everyone should be looking at me thinking I'm a little crazy. but let's stick to it. So everything I'm going to be talking about, the results, I need categories to be regular. I'm not going to really go into all of this too much, but right, this is finally complete category. I have certain coequalizers, and then I need pullbacks of regular epis along any morphism to be a regular epi. Okay, so that's what we need, but I'm not going to be doing it too much right now. So the point of what makes regular categories nice for us is that we have these factorizations which are regular epi and mono. Okay, and we use that. So just to remind everybody, factorization, take morphism. I'm going to split my morphism up, factorize it into two components, an epi, in this case a regular epi, which I call me, because it's the other way around as im, and im of f. Okay? Whoops. So you get a functor from morphisms in E to little triangles, commutative triangles in E. Okay? And you can lift this functor to diagrams. So I get a functor, factorizations, that takes morphisms of diagrams into commutative triangles of diagrams, where here I had a morphism and I'm going to factorize it. I factorize my morphism into a little triangle. Here I'm going to factorize diagrams, so I'm going to get a diagram here, and its factorization, which looks like the picture I was trying to give you before. Okay, so as I alluded in the picture, I'm a big fan of spoiling the result at the beginning. We're going to be computing the limit, defining something in terms of the limit, and then magically telling you that you don't need it. So there's an adjunction, the limit functor, which takes any diagram to its limit, and there's this constant functor that takes any object and produces a diagram indexed by just one object, and it's just a single object diagram. You get the co-unit of this, so you get, this is the limit of D viewed as a diagram with only one object, and it has a map to D. What is the map? Well, it's the limit cocone. Limit cone. Okay? So the point is that this is now a morphism of diagrams, so I can stick this into my functor. This gives me a functor that takes diagrams, D, and returns a morphism, which is going to be the limit cone sitting above the diagram. Okay? Now given this, we can apply the factorization. So this is going to factorize our limit cone. And then we pick the factorization, the images, and this returns a diagram in the category we started with. Okay, so this is just formally defining the picture I had before with the big cone and the limit. And I'm going to call this my functor. It's going to be the im functor. I'm suppressing the lambda of the limit cone, right? So it's just going to be im takes in a diagram, applies all of this. Any questions? Everybody's happy? All right. So, yeah. Mm-hmm. This is the epi and this is the mono. Yeah. Yeah, yeah. The functor pi, it keeps, it's just returning the dot. It's like, it's forgetful. It just gives you back this object, because that dot is going to be a diagram, and it just returns a diagram. Yeah. Cool. So lemma says that if you start off with a diagram, so I have a category, it's regular, and I have the appropriate limits. Then for any diagram, the limit of that diagram is isomorphic to the limit of this image of that diagram. Right? So if you do this in set, you should believe it, and it extends. I actually proved this twice without realizing, because the first time I proved it for co-limits and co-cones, I was doing another thing. And then afterwards I realized, wait, I had proven this in a more complicated way, and so we made the write-up nicer. So now we have two proofs. So here's how it goes. So you start off with the factorization. So here's the limit of my diagram D, and I factorize it with this image. And these are morphisms of diagrams. So now take the limit of this. So the limit of delta of limit of D is just going to return limit of D again. Get a map onto the limit of the image of D. And limit's right adjoint, so preserves this mono, and I get a mono into limit of D. Okay. Now, by definition, I know that G of F is the identity, right? Because I started, I got the limit, and I just made this commute. So I can conclude that GF of G is G. G is mono, so I get the desired isomorphism. Okay? All right. So the point is that if you get a regular category with J-shaped limits and a strict initial object, then this commutes. So you use the lemma that I just proved before. And so if anyone's bored in the rest of the talk, you can try proving this. It's 2 lines. So I'll let you think about it. But the point is, we just proved that this thing commutes. So this magical functor I told you makes this it fixes this diagram, right? So now this works for, and importantly, the theorem I told you I needed diagrams into finite sets, right? I don't need that here. So to prove that this thing commutes, nothing fancy's happening. For the algorithm, I'm working with finite sets. Well, technically, I can work in any pre-sheaf category, but all right. So the point is that now our line of attack is to say, we're not going to do brute force, which is this path. We're going to instead apply this functor, which I still haven't told you whether we can compute this fast or not, but for now you trust me. So the fact is that you can do this fast. And then this is locally check if each thing is empty. And if any one of them is empty, you reply no. And if they're all not empty, you say yes. Okay? So let's do a little recap. So we started with a diagram. This diagram was specifying some sort of equation. We want to know whether the limit of this diagram is empty, i.e. we want to know if this equation has any solutions. So one option is test the whole limit. This is the naive option. Too many steps. And we prove that local checks suffice on the image of D. And there's a problem, which I've been alluding to all along, which is, how do you compute this thing? Okay, better know how to do this. So I defined it in terms of the limit, and I just told you I don't want to test the whole limit. So got to do something smarter. All right, so the point is that we're going to find a way of computing this thing fast without ever looking at the limit. And we're going to do this using tricks that in complexity theory people use all the time. We're going to be doing dynamic programming. And this is actually very standard. So I like this stuff because so far I'm taking very standard stuff in category theory and very standard stuff in complexity theory, and you put them together, and they give you cool results that are actually quite general. So I like simple things that do cool stuff. So we need special kinds of diagrams. These things called structured co-decompositions. And maybe I can tell you a little story. So when I started working in category theory, I was interested in generalizing tree decompositions, which are these things that people use in graph theory, to other kinds of structures. And I came up with a thing called a structured decomposition. So kill the co. And I thought, wow, I really did it. That's pretty cool. I got a category theoretic thing. I feel really smart. It generalizes tree width. Everybody's going to love it. And it is pretty cool. And so the reason why people love it so much is that algorithmicists are convinced, when you ask them, that when you compute on these things, you're using tree decompositions to compute. Like, that's the thing that makes the algorithm work. And I was convinced of this too. So when I first did this work, I thought, oh, well, because of contravariance, I have to do something funky, and I end up with this thing, which I didn't really want, but whatever, it's just because category theory is weird. And then I looked inside, I meditated a little bit, and I realized category theory did it again. This thing is actually the important part, and the structured decomposition is the non-important part. It's an artifact. So whenever people in algorithms are computing something fast, actually doing the work here, not on the decomposition. So you can talk more about that later. But the point is that this is emerging as the actual important structure. And so in a series of papers that I'm working on writing now, we got 4 papers about algorithmic applications of these things, another paper about the graphs you can construct using code decompositions. And there ends up being a lot of depth there, even just from an algorithmic and graph theoretic standpoint. All right, so what are these things? So you take a graph G. In this talk, you can let G be a finite simple graph. But you know, because everyone's a category theorist, you can think of G as a pre-sheaf and take a growth and deconstruction if you want. Other way of doing this is you subdivide all the edges, similar to what Michael Robinson was talking about. And you get this thing called a barycentric subdivision of the graph G. So this is a category. You start with a graph, get a category. And it looks like this. So if this is my graph, so it's a little triangle with a pendant, little buddy over there. For each vertex becomes an object, the white objects. Each edge becomes an object, the yellow objects. And I have a cospan from the vertex objects to the edge objects. And so I'm looking at diagrams with this shape. Right? That's what a structured co-decomposition is. People like to, well, me, I like to call the white things the bags, and I like to call the yellow things the co-adhesions. Okay? This is terminology that I'm borrowing from graph theory. All right, so the point is, you give me a diagram that looks like this. Final note on what this looks like. If you're into sheaf theory, these things turn up all the time. So if you look at the sheaf condition diagram, you know, you get your, whoops. One of these is a U, right? So you got your usual equalizer diagram for the sheaf condition. So this thing's a graph, right? You got 2 things in source and target map. This thing's a graph. So the things in here, if you unpack this product, all of these f of u's are the white bits. And if you look at this product, all of the f of uv are the yellow bits. So you can view this literally as an attachment diagram of the thing you get when you apply f to the check nerve. I don't know if that helps anybody, but I'm trying to give people words in different languages. But okay, point is, these are diagrams, they're pretty natural, and they turn up all over the place, actually. So let's just give you an example. So here's a graph G. I'm going to construct a structured co-decomposition of shape G. So I get, for each vertex of G, I get sets, and the white ones. For each edge of G, I get yellow sets. And I have maps. Here I take A to X, B to X, and C goes to Y. Okay? These are my maps. Image of G is going to be the diagram that is kind of filtered out, right? Consists of only these points. And the way to visualize this is the limit of this diagram actually has only 2 points in it. Those 2 points consist to exactly the 2 matching families you see here. The point called CYBVR and CYB beta VS. Okay? This is a distributed representation of the limit. That's what you should think of this guy as. Okay? So every point in the limit comes from exactly 1 matching family here. Okay? That's just a picture to keep in mind. So let's get to the algorithm and give you some feeling for how that goes. So there's 2 main components to the algorithm. First, I'm going to have this filtering operation and then a gluing operation. So the algorithm is actually pretty simple. So I start off, you give me a structured co-decomposition here, D, and you pick out some of the one of the cospans in there. Every cospan is indexed by some edge in the original graph. That's defining the shape of the diagram. So what I do is I take a little pullback of this cospan, and I'll have L1 and L2 be the 2 pullback maps. And I'm just going to replace in this diagram, I'm going to leave the whole diagram untouched, except for these 3 objects. I'm going to replace them by the images. So I'm going to replace D of T1 by the image of L1, and I'm going to replace D of T2 by the image of L2. and also replace d of e by the image. Okay, so I just like did a little pullback, took the image. Okay, so far, this is. I mean, are there any questions on this so far? Yes, am I doing this backwards? No. So I take this diagram, which right now the co in my head is flipping. This is a cospan, right? Yeah. So we have this cospan, and I'm taking a pullback of this cospan. So I would just want the diagram here. So I have dt, de, and d of t2. And I'm going to take a pullback here and project onto the components. So it's just locally. So I have, for each edge, I've got this pair of maps with common codomain, and I take a pullback of them. I'm pretty famous for forgetting the words for everything. So if I say something wrong, just shout at me. Probably it is wrong, okay? So that's the filtering operation. It takes as input the diagram and an edge, and returns a diagram. There's nothing functorial about this filter. This is algorithmics. We get dirty, okay? But the point is that what we will construct at the end of this is a thing that is functorial, which is this image diagram, okay? And so then there's this gluing operation. The gluing operation is very simple, just notation's a little heavy. So you start off with two structured co-decompositions, and you fix a vertex in each one of those, an object in each one of those. And also you pick a new object you haven't looked at so far. And then you pick and you construct a little cospan from these objects. And then you're just going to glue them together. So here's my first diagram, the D1 diagram. Here's my D2 diagram. I pick an object, d of x1. I pick an object, d of x2. I define a little cospan, and now this whole thing is a new structured co-decomposition. Just putting the diagrams together. Famously, diagrams of diagrams are just diagrams, so it flattens out, okay? Right. So, the main algorithmic lemma is this tree lemma. The tree lemma says, let T be a tree. And we're going to look at a structured co-decomposition that's very special. It's got a shape which is a tree. So I went from general diagrams, now I'm going to extremely restricted class of diagrams. These are diagrams that look like trees with subdivided edges, so you get a cospan for every edge of the tree, right? So if my tree looks like this, then I replace each edge of the tree with a cospan like that, okay? So I'm looking at this very special kind of structured co-decomposition, and I pick an edge in the tree. That edge is going to be a cut edge. So it's going to look like this. It's going to partition my tree into two parts. I have a subtree T1 and a subtree T2, and my edge splits it. And I get two induced structured co-decompositions, which are just the restrictions to T1 and T2. So this DI is going to be a restriction. So D1 is a restriction to T1 of this thing. And then the theorem says that I get this recursive relation. The image diagram of D is the same as the filtering operation applied on the edge E of what? Of the diagram you get by gluing the recursively constructed image diagrams of the D1 side and D2 side. So you pick the edge, remove it, recursively solve the thing on the two subtrees, put the two trees back together, and now filter the last remaining edge that you had originally removed, okay? Just by taking a pullback. So in practical terms, what this means is, this is telling you that the image diagram of a tree-shaped structured co-decomposition is obtained by, for each one of these edges, take a pullback and project back. Take a pullback and project. Take a pullback and project on each one of the edges of these little cospans. And if you do that, then you're going to end up with a diagram which is all filtered out. Or if you prefer the sheaf theory language, this is going to be a diagram I can point my finger now. This is a diagram that is it's giving you a distributed representation of the set of matching families. Okay? Crucially, the biggest limit I ever took was a pullback. Okay? This is why this works. So if I start taking bigger limits than pullbacks and I just keep growing, the pullback will grow. It's a product, right? So it'll grow really fast, and that screws up the entire algorithm. I don't want that. I want to be only taking bounded sized operations, and so I can prove to you that I'm only ever doing something with bounded sized pieces. Okay? So this is the tree lemma. And the tree lemma, it says that, well, I can take, this is the recursion that I get, and you get a recursive algorithm, which is just, apply this. And so it gives us an algorithm that runs in time w squared n, where w is the size of the sets involved in the tree, right? So any one of the objects in that tree. It's the biggest size of any one of those, just an upper bound. Okay? So this is really good in the case of trees. Right, so I told you trees, and I was supposed to tell you about other kinds of diagrams, so how do you go there? Well, the general case, we go as general as having an arbitrary graph here, okay? It says, well, what we're going to do in complexity theory speech, we're going to be doing a, what is it called? A logical truth table reduction. So the idea is that I'm going to take an instance, I'm going to return to you a bunch of instances, and a logical combination of truth on these instances determines the truth on the whole thing, right? So that's what I'm doing. So I'm starting with an instance D. So I have this diagram of shape G. I'm going to pick a forest in G. I'm going to do this intelligently. And from this forest, I'm going to construct a family of diagrams indexed by some set, which I'll get to in a second. And this family will have the property that the limit of D will be empty if and only if, for all of the diagrams in this family, the limit is empty. Okay? Crucially, because each one of these are forests, by the discrete diagram case and the tree algorithm, you put them together, you get an algorithm for forests, which is fast. So the idea is, our algorithm boils down to split your diagram into lots of little diagrams, apply the tree algorithm a bunch of times. How many linear little diagrams are you going to get? We're going to get I many of them, and now we're going to explain where the I comes from, what it actually is. So this is the recap. So we have a diagram. I'm going to give you a family of these structured code decompositions where F is a forest. And I'm going to get the running time of this thing, I'm going to get W to the K. W is the size of the biggest set in the diagram D, right? K is this feedback vertex number of G. So what is a feedback vertex number? A feedback vertex number is the number of vertices I need to remove to make a forest. So for example, here's a graph that has a cycle in it. This graph has feedback vertex number 1 because I can pick a single vertex whose removal returns a forest. Okay? So the point is, what we're going to do is we fix a feedback vertex set. I'm going to call that I. This is a set of vertices whose removal gives me a forest. And basically, for each one of those feedback vertex sets, I'm going to get a collection of these points. Look here. I'm going to look at what is the set of things in here. And for each one of these, I'm going to produce a new diagram containing just a singleton. So for each one of the elements in this single set, I'm going to make a copy of this diagram, which is the same everywhere else, but I replace this set with a singleton. Then I take pullbacks accordingly, and basically what I'm doing is I'm forcing consistency along cycles. So each one of these diagrams I get here, I'm going to get one diagram per choice of options in the feedback vertex set. And this forces that the matching families of Ti, or of tau I, are exactly the matching families that all agree with the points that are in the, that I chose in my little feedback vertex set. And that's basically it. Then I'm just going to recurse, and I get this algorithm running in this time. Okay, so that's a high-level picture of what's going on. So, as a summary, what was happening was that I started off with simple question. I want to know whether there's a limit of a diagram is empty or not. Now, if you were to apply this to the 3-coloring algorithm functor that I told at the beginning, if you give me take a little graph and say that you cover your graph with a bunch of subgraphs. This defines a diagram whose colimit is that graph. That's just what it means to cover a graph. Now, if I hit this little diagram with a contravariant functor, I'm going to get a co-decomposition, or you can construct such a thing. I'm hand-waving a little now, but this is an application of this result. And so this gives you an algorithm where this gives you a structured co-decomposition here, where the sets locally are all of the local, let's say, 3 colorings of the pieces I use to cover my big graph. And so by doing this, you recover classical algorithms in graph theory where you can do 3 coloring parameters by tree width, these sort of things. So the point is that classically, you might have some other auxiliary structure. Maybe you're building your graph with a colimit, but it doesn't have to be a colimit. And then what you're actually going to get is this new structure here, which is obtained by the contravariance of the fact that most of the computational problems are most naturally written down as contravariant functors. And by contravariance, I'm going to get this thing that looks like that, or at least this is a data structure that I can construct from these diagrams. And where the maximum size here, this W, is going to end up being the size of the local solution spaces over the pieces that I used to construct my original input. So this is basically the main lemma that lets us do dynamic programming in lots of cases. Okay? And so that's basically it. I think that the takeaway message is there is such a thing called categorical algorithmics, and the name is new. And I invite everybody to be involved. I think it's really cute. I think that it's also useful. And you use simple ideas in category theory and simple ideas in algorithms and put them together. And the putting together part is the hard part. But I think there's lots to be done. As I mentioned, there's a series of papers that are going to be coming out. There's joint work with Anni and Ugo and my student Paulo, and that we're working on currently. So there's lots of things happening, and if anyone's interested, we should chat. Thanks so much.
Thank you, Ben. So do we have questions, comments?
So about the hidden constants in the big O notation. Can I say anything? Can you say anything about? Is it going to be one of those cases where the leading constant is astronomical and so on?
So the hidden constants are actually very good. This is actually implemented. So in algebraic Julia, up to this point, the tree lemma is implemented. It's implemented and run and benchmarked on gigantic instances. I wrote the first batch of code. I didn't benchmark it. Then James Fairbanks and others benchmarked. So don't ask me about that. They did a bunch of high-performance computing stuff. But it runs, and you can just take your favorite problem, hit it with something, and get this thing back. And as a note, one other thing that I think is a nice byproduct, even though I don't spend my life writing code, I was very happy to do this categorically because the code was 70 lines. This was nothing. If somebody had asked me to do this with normal combinatorics, graph theory stuff, I would not have wanted to write the code. But it took me a day and a half, and that was mostly because the first day I needed to learn algebraic Julia. But yeah.
Okay, lovely, very pretty. But no, work doesn't disappear. So, and limits are complicated. Let's try to recap what happened. One big simplification is to say the categories are regular.
Yes.
That's a big one, right?
Yeah.
Another big one is to say, I have a graph, but more than a graph, I have as a forest with a specific set. And then on this kind of graphs, I mean, because at some stage at the beginning you said intro G is a special graph. Then you kind of say, I mean, just repeating what I think you said to see if I'm understanding correctly. So this integral G op, we transformed it into a forest with this special set of graphs that I want to repeat for each one of the guys there, the same forest. And then is to my mind, the big beautiful insight that you take every edge and make it into a correspond, and each kind of corresponds, you can somehow create a pool. So that gives you that chew on W to the chew that will control the complexity of the stuff.
Yeah.
Full.
Yeah.
Phew. Very beautiful. Thank you.
Thanks. So yeah, actually, one thing that I should mention. So because what I'm doing is parameterized complexity, this stuff is NP hard in general, right? So what's crucial is that, well, there's two things that are crucial. I'm allowing exponential work in some parameters, but not the size. So parameterized complexity is about confining the exponential, the combinatorial explosion to some relevant secondary parameter, which isn't the input size. So the idea is, you know, if you try to run this on arbitrary, like the worst case on an arbitrary graph is going to be horrendous, because an arbitrary graph is going to have a really big feedback vertex set, so this is going to be exponential. But the point is that a lot of times the diagrams that you actually get, even in practice, right? Like imagine that you have a big wiring diagram and you're trying to build something. Because we're humans, we don't like building things that have a lot of cycles in them because they're hard to reason about. And in fact, people have actually looked at this. If you look at like the compilation trees for, now I forget what is ML or something like this, they all have low tree width as graphs. So you can show that all of these things are actually, very often in practice, the diagrams you end up with, sure, they might have some cycles, but they don't have that many because we produce them. Or the structure that, where the data is coming from, tends to have some extra structure to it. So you can usually expect this k to be relatively small, and then when that's relatively small, if k is the most 3, then you're still good. You know, this is just constant then, times n. So if k is very small compared to n, if n is 10,000, then that's what's really driving the running time. So it ends up big O being of n when k is fixed. So that's the trick. But we're not getting something for nothing. We're putting the hard part here. But the point is, let's put the hard part somewhere where it's independent of n. And if we can do that, then we at least have control over where the blow up is happening, so that we can still get something that's practical on n, but runnable for a lot of cases. And when k is too big, then I put my hands up and say, I don't know. It's kind of like the first. So yeah.
More questions, comments? So let's thank Ben again. So we have a small problem that the pão de queijo is late. So, and we are running an event in Minas Gerais, so we need to wait a little bit for this. So in this time, I'm gonna run this random choice to choose who is gonna receive the next book. So just for 2 minutes, I'm gonna take the book. 1 minute, please. O livro, sim. Então, essa aqui é a ideia. Achei.
Só de se tiver atrasado, né?
Mm, well, we talk a little bit about graphs, so I'm gonna use this book called Introdução à Teoria Espectral de Grafos com Aplicações. And now I have to take the website. Pode parar a transmissão também. Pode pausar, obrigada. The number is 10. Let me see who is 10 here. Ten is César Augusto Freitas Bernardes. So it's the César Augusto Freitas. He's not here today, so he's not reading list. So another number, yeah, it must to be here. He can win tomorrow if he's here. So I will do it again. It was me again, so I just gonna skip. This thing's so bad. Two. It's some Ana, but it's not my name here. Two is Aliel. Aliel is not here. Two, she's only coming tomorrow. $21. Gabriel Luiz. Gabriel is not here.
O pointer é esse aqui? Ah, tá bom. Tudo bem, tá certo. Voltamos já? Voltamos? Então, bem, obrigado a todos de estarem aqui na continuação do mini curso, né, de Feixes e Anéis Sem Infinito. Né. A Ana fez a apresentação um pouco da teoria de categorias, o que a gente precisa e também dos feixes. Então, agora a gente começa a fazer feixes não só sobre espaço topológico, sobre versões generalizadas, e os anéis sem infinito começam na aula que vem e na última aula também. Ops. Tá bem no cantinho. Tá. Então, esse é o plano da aula de hoje, né? Topologia 100 pontos. Vamos explicar um pouco sobre isso. O Ciro comentou a respeito também ontem. Coberturas e topologia de Grothendieck e topos de Grothendieck. Então, a Ana tinha comentado sobre coberturas em espaços topológicos, né? Então, a gente considera aqui um espaço topológico X e um aberto de X, e uma família de subabertos desse aberto U é uma cobertura quando a reunião desses abertos dá U. Né? Cobertura bastante intuitivo. A noção de cobertura de espaços topológicos, de abertos de espaço topológico, tem essa propriedade. Né? Então, é claro que o U sozinho cobre U, é a função identidade. E se você tem uma cobertura de U, onde cada elemento da cobertura tem outra subcobertura, eles próprios têm cobertura, então essas compostas, que são subconjuntos do maior, também vai cobrir U. Essa é uma coisa da reunião. Reunião de reuniões é reunião. Uma outra propriedade das coberturas de abertos num espaço topológico é que se a gente tomar um aberto V dentro de U e considera a interseção do aberto U alfa com V, isso é uma cobertura de V. Isso é uma propriedade que decorre basicamente da distributividade entre interseção e reunião. Interseção de abertos, de dois abertos é aberto, reunião de uma família de abertos é aberto. E notem essa propriedade aqui, U inter V igual a V, porque isso é equivalente a dizer que V está contido em U. Então, nós podemos trabalhar sobre a noção de cobertura. A gente não usou em nenhum momento, nesse ponto, nada sobre pontos. Né? Então, só usamos a estrutura do conjunto de abertos, que não é só um conjunto, é um poset, é um reticulado. Isso é chamado um locale. Tá? É um tipo especial de reticulado. Então, o que é um locale em geral? O locale é um reticulado completo, né, que quer dizer que todo conjunto é um poset, onde todo conjunto tem supremo e ínfimo, todo subconjunto do locale tem supremo e ínfimo, e que vale essa lei de distributividade dos ínfimos binários com sups arbitrários. Né, então, essa lei aqui. Né. É claro que todo espaço topológico, todos os abertos do espaço topológico formam um locale, porque o ínfimo ali é a interseção binária e o sup é a reunião arbitrária. Então, distributividade de conjuntos se aplica, nesse caso, para distributividade de abertos. Um outro caso importante de locale, que é também espacial, vamos falar um pouco desses nomes aqui, é o conjunto dos ideais radicais de um anel comutativo com unidade. Né? Ou seja, dado um anel R, com unidade e comutativo, e I um ideal, o radical de I, como a Ana também tinha colocado ontem, né? São os elementos do anel, tal que alguma potência dele vai pertencer ao ideal. Né? Essa é a definição clássica de radical. Né? Felizmente, né, no caso dos anéis, isso equivale a dar uma certa topologia no conjunto dos ideais primos próprios do anel. Ela tem o isomorfismo de locales. Esse é um ponto porque os feixes são mais fáceis quando a gente... E a geometria algébrica é mais fácil quando a gente enxerga essa propriedade espacial aqui também. Nem todo locale vem de um espaço topológico, mas também, como o Ciro apontou lá rapidamente na apresentação dele, locales e espaços topológicos têm uma adjunção, né? E exatamente essa adjunção se restringe a uma equivalência, a maior equivalência possível, quando você liga os locales chamados com suficientes pontos, né, que são os espaciais, e, por outro lado, os espaços topológicos são sóbrios, né? Todo fechado irredutível tem um único ponto genérico. Então, como eu mencionei antes, né, os abertos do espaço formado pelo conjunto dos ideais primos com a topologia de Zariski, que a Ana mencionou ontem, são isomorfos, enquanto locales ao locale dos ideais radicais. A estrutura de locale aqui não é difícil também de imaginar. Ela é herdada, digamos, da soma de ideais, que é o sup, e da interseção. Então, bem, essa aqui foi o comentário que eu fiz agora há pouquinho, né, entre a conexão entre espaços topológicos e locales. Adjunção. Então, locale é o que é chamado de topologia sem ponto, a classe dos locales. Você pode formular muitas das propriedades topológicas sem qualquer menção a ponto, né? Muitas, mas não todas. Então, compacidade é algo que tem a ver só com coberturas, regularidade também. Então, algumas ou várias noções têm a ver mais com diretamente com o reticulado de abertos. E também a noção de feixe, a gente não precisa de fazer nenhuma menção diretamente aos pontos para definir a noção de feixe, nem muito menos de cobertura. Então, se você tem um locale L maiúsculo e um elemento L minúsculo, um elemento do locale, uma cobertura desse elemento é só uma família de de elementos menores iguais, cujo supremo dá o próprio locale, né? O locale é um radical completo, os supremos sempre existem, tá? Então, a gente pode definir a cobertura num sentido ainda mais generalizado, né? A ideia de cobertura num sentido ainda mais generalizado, que é tomar, por exemplo, uma categoria pequena, por questões técnicas, também com questões técnicas de conveniência técnica, a gente assume que ela tem pullbacks, né? E uma família recobrinte ou uma cobertura ali dentro é só uma certa família de flechas que tem um contradomínio, um codomínio, ou codomínio, melhor dito, esse objeto A fixado. Então, uma cobertura de A é uma família de flechas que terminam em A, né? Satisfazendo algumas propriedades, né? Então, todo isomorfismo sozinho já cobre o objeto, né? Então, isso aqui a gente lê em termos de composição a propriedade que cobertura de cobertura gera cobertura. Então, é bastante análogo ao que nós fizemos agora há pouquinho com os supremos em espaços topológicos. Então, aqui é a composição, talvez aqui tenha uma indexação para ser arrumada, né? E agora sim entra essa propriedade de a subida que tem pullback, essa categoria, que se a gente tem uma família que cobre uma cobertura B alfa, não sei se está lendo, né? B alfa linha, que cobre um objeto A. Então, se nós temos um objeto B e nós fazemos esses pullbacks, isso vai gerar também uma cobertura, agora não do A, mas do B. Então você puxa coberturas para trás por pullbacks. Então essa é uma propriedade importante, chamada estabilidade. Está aqui o desenho formal, né, o desenho mais limpo, né, tem os mapas aqui presentes. Só está na outra direção. E o que é uma pré-topologia de Grothendieck, ou alguns lugares falam de coverage, né? É simplesmente uma função, né, que associa a cada objeto uma família de famílias de objetos que tem contradomínio o objeto A em vista, né? Satisfazendo aquelas propriedades que a gente comentou agora. Um isomorfismo sozinho já cobre, cobertura de cobertura é cobertura quando você faz a composição, e se você faz o pullback de uma cobertura por um morfismo, também dá uma cobertura do cara que foi puxado para trás. Em particular, se a gente começa com uma categoria que é um locale, todo POSET tem uma estrutura de categoria natural, como a Ana apresentou na primeira aula. Nós cobrem o I, quando a gente junta todo mundo aqui, isso vai cobrir o U, né? Uma transitividade. E aqui é o axioma de estabilidade, o axioma de pullback aparecendo. Então, ter uma flecha de V para U quer dizer que V é menor ou igual que U, é uma categoria de POSET. A cobertura é supremo, então V menor ou igual que U quer dizer que V é igual a V ínfimo U. Bem, U é o supremo dos Juiz, V ínfimo o supremo dos Juiz. Como a gente está num local, isso troca de posição, eles comutam. Isso aqui é o sup de V ínfimo Juiz. Bem, então essa nova família é uma cobertura de V pela definição de cobertura que a gente está tomando. Então, isso prova que todo locale tem uma estrutura natural ou herda uma estrutura natural de topologia de Grothendieck. Em particular, os abertos do espaço topológico têm uma estrutura de pré-topologia de Grothendieck. Okay. Outro exemplo, né, de pré-topologia de Grothendieck numa categoria C, sempre disponível, é nós tomarmos a chamada topologia discreta, onde as coberturas de um elemento, sei lá, C, aqui está, acho que na ordem trocada, são exatamente as famílias formadas por um isomorfismo só. Tá? Então, um isomorfismo. Bem, mais formalmente, dada uma pré-topologia, a gente pode associar algo que é mais estável, mais límpido, né? Que não fala de famílias, mas de famílias canônicas. Essa é a ideia de chamar isso de civil crible, o original em francês, que para cada objeto C da nossa categoria, isso é uma família de flechas que chegam em C com uma propriedade de estabilidade por composição para trás. Então, por exemplo, num locale, nós tínhamos que o U é o sup dos Uis, se a gente tem isso. O U também vai ser o sup dos, vamos chamar VI, V de UI, melhor, onde esses VUIs são quaisquer caras que estão abaixo, na verdade, a família de todos os VUIs que estão abaixo do I. Então, se você engorda a família colocando não só o I, mas todo mundo para baixo. Bem, essa é a propriedade associada com a noção de civil ou crible. Fecha para trás. Então aqui a gente usou o nome de downset, ou seja, fechado para baixo, né, ou ideal à esquerda. E, bem, não é difícil de ver que um sieve, vou usar isso aqui, um sieve sobre o objeto C corresponde a dar um subfuntor do funtor Homo. Justamente essa propriedade de estabilidade é um diagrama comutativo que usa a inclusão do subfuntor associado, sendo, digamos, não só como um subconjunto, mas a propriedade de naturalidade ali envolvida. É uma conta rápida. Né? Por outro lado, essa versão mais conjuntista de sieve é mais fácil de ver como que a gente escreve o subfuntor gerado ou o sieve gerado. Né? Então, dada uma família de flechas que chega em C, você pode fazer de forma abstrata o que a gente fez aqui. Como que você fecha para trás? Bem, fechando para trás. Você escreve todos os morfismos que vão ser feitos com a composição com um morfismo que já estava na família original. Né? Então, você fecha na mão formalmente digamos, o conjunto que você tinha selecionado e compondo todo mundo que está para trás, isso dá automaticamente fechado para a esquerda. A definição formal de topologia de Grothendieck numa categoria, então, não precisa daquela condição técnica de pullback. É uma coisa técnica, conveniência, aparece muitas vezes nas categorias de verdade que a gente tem na mão, elas estão sempre presentes, tá? Mas não precisa. Tá? Então, uma topologia de Grothendieck, não mais pré-topologia, então uma família que é uma função que a cada objeto da categoria pequena C, em geral, a gente assume pequena. A Olivia Caramella apresentou uma versão equivalente, que às vezes é conveniente, uma flexibilidade a mais quando é pequenamente gerada, né, em termos topológicos. Mas para a gente aqui, a gente vai considerar pequena, vai associar para cada objeto C uma família de sieves ou de subfuntores do rumo traço C, satisfazendo o análogo da condição de maximalidade, quer dizer, aqui o crivo gerado por um isomorfismo são todos os subfuntores, o funtor inteiro, o funtor máximo, toda flecha cifatória por isomorfismo, então essa é a condição de maximalidade. Essa aqui é a condição, seria correspondente à condição dita 3, o fechamento por pullback. Agora a gente está na pullback no sentido dos conjuntos. Isso aqui é um pullback no sentido dos conjuntos, tá certo? Eu troquei um pouco a ordem, porque ele é mais simples de apresentar. O terceiro axioma era mais difícil, mas depois ele fica mais simples quando a gente estabiliza. E aí tem um outro que representa uma combinação das duas últimas propriedades, que é chamado de localidade. Né? Então, se você tem uma cobertura de C e um outro sieve sobre C, tal que para cada elemento desse sieve da cobertura, você puxou esse cara que a gente não conhecia muito bem, puxou para trás por um pullback, e isso deu um cara da cobertura não de C, mas de D, puxando para trás. Então, se isso ocorre sempre, né, para cada elemento da cobertura, então é porque aquele sieve teste, de fato, está na topologia. Então, isso é uma forma de chamar de localidade. Né? Então, toda pré-topologia gera uma topologia nesse sentido, com essas propriedades aqui, as três propriedades. Então, um sítio pequeno é formado por uma categoria pequena e uma topologia de Grothendieck nessa acepção dos três axiomas. E essa é a observação que eu comentei, né? Dado qualquer topologia de Grothendieck que você tem para indexação formada pela identidade, né? Os elementos são sieves, você pode fazer a indexação exatamente usando a própria autoindexação, um elemento é indexado por ele mesmo. Então isso dá uma pré-topologia e, dado qualquer pré-topologia, você gera, através dos crivos gerados, basicamente, né, uma topologia de Grothendieck. Né. Então, está aqui a topologia, a pré-topologia dos locais, e aqui tem a versão, digamos, estabilizada pelo sieve. Então, você tomou todos os elementos que estão abaixo de algum id, eles vão ter o mesmo sup. Com a topologia discreta, a pré-topologia era só formada por isomorfismos, a topologia é formada apenas pelos, digamos, pelo morfismo identidade do hom-c no hom-c. Tá? O que interessa mesmo para a gente é a noção de feixe, né? Agora, feixe nesse sentido ampliado para topologias ou pré-topologia de Grothendieck. Então, a Ana explicou a noção de feixe na aula passada, de duas maneiras, uma versão mais concreta, com aquele mote. Toda família é um pré-feixe, né, um funtor, contravariante, a valores de 7, pré-feixe de conjuntos, tal que toda família F compatível tem uma única colagem. Né? Isso era expresso diagramaticamente de forma bastante sintética através de um diagrama de equalizador, onde aqui aparecia um aberto, aqui os elementos daquela cobertura do aberto, e aqui a interseção de dois abertos da cobertura, e esses mapas tinham a ver com as restrições. Né? Então, a interseção, no caso dos abertos do espaço topológico de um locale, sendo ínfimo, é substituída pelo pullback na categoria. Naquele caso, eles são pullback, e na definição sobre feixe sobre uma pré-topologia de Grothendieck, a gente usa de fato o pullback. Né? E conseguimos reproduzir a ideia dos mapas todos. Né? Um mapa de projeção são feitos com propriedade universal desse produto, como a gente define esses mapas. Uma vai expressar, dada uma família FI, você associa na posição IJ o FI restrito a CI pullback com CJ, e o outro vai associar, não o FI restrito ao pullback por CI por CJ, mas o FJ restrito ou mapeado no CI por CJ. Esses são os mapas PIQ aqui. Ó. Aqui eu estou usando restrição, mas tecnicamente é o F calculado na projeção. Então, quais projeções? As flechas canônicas do pullback. No caso dos locais ou do espaço topológico, isso aqui são inclusões, mas a gente usa as projeções no sentido das categorias, em geral. Né? Bem, agora começamos com alguns exemplos. Né? A gente mencionou primeiro que, dado qualquer categoria, ela tem sempre uma topologia de Grothendieck muito na vista, que é a topologia discreta, onde as únicas coberturas, a única cobertura do feixe do subfuntor hom-c é o próprio hom-c com a identidade. Né? Isso vai dar que a categoria de feixe associada é a categoria dos prefeixes, a topologia discreta põe todo mundo. Né? Mas o Peter, há poucos momentos atrás, mostrou a utilidade de olhar a categoria de prefeixes, mesmo do ponto de vista, digamos, lógico e categorial. Né? Mas, em geral, muitos topos não são topos equivalentes a topos de prefeixe. Né? Então, esse aqui é um deles, né? O topo de Zariski. Isso tem a ver com a topologia de Zariski que a Ana mencionou sobre um anel, né, comutativo com unidade. E eu vou apresentar aqui brevemente também o que é isso. Tá? Então, se a gente... É esse aqui? Né? Se a gente começa com um anel comutativo e finitamente apresentado, né? Finitamente apresentado, como o Peter também mencionou agora há pouquinho, significa para a gente, digamos, com a abordagem da álgebra, é só ter um número finito de geradores e também apresentado através de um número finito de relações, né, qualquer anel dado por geradores de relações. Por que a gente usa essa categoria também? Bem, primeiro, essa é uma categoria que é essencialmente pequena, ela é equivalente a uma pequena. Então, você pode tomar um esqueleto dessa categoria, isso quer dizer que é pegar uma parte que é efetivamente pequena e que é equivalente à categoria toda, que é uma classe própria, né? Todos os esqueletos vão ser isomorfos e vão ser conjuntos, categorias pequenas mesmo. Então, se você está um anel finitamente representado A, bem, o topos de Zariski é feito olhando a topologia na categoria oposta dos anéis comutativos finitamente representados. Então, isso aqui, na verdade, a gente está falando de co-coberturas, né? Isso aqui é fazer a co-cobertura de um anel A por anéis BI, tá? Através de flechas. Na categoria oposta, isso troca de ordem, né? Então, A é finitamente representado e os BIs também tem que ser. Os BIs que a gente vai tomar aqui são, bem, essencialmente localizações do anel A. Então, vou colocar aqui um elemento, sei lá, T, né? Mas a gente não vai usar exatamente o T, mas vai usar o inverso de T. É algo que a gente faz fazendo as frações desse elemento, né? Quer dizer, aqui os elementos desse cara são da forma x sobre t elevado a n. Né? Os elementos de alguém aqui. Bem, com a definição de fração muito parecida com a gente está acostumado a trabalhar com corpos, mas não exatamente a mesma, né? A gente pode lembrar um pouco que nós temos uma condição universal. Quando você pega um subconjunto, digamos, multiplicativo num anel A, comutativo com unidade, você pode fazer esse anel de inversão formal, né? De mais de um jeito. O jeito mais comum é dizer que uma fração x1 sobre S1 é x2 sobre S2, como classe de equivalência, C e somente C. Existe um T em S, tal que x1 S2 menos x2 S1 dá zero. Tá? Isso, com essa definição, a gente não precisa que o anel A seja um domínio de integridade, né? Isso resolve o problema universal de inversão do conjunto S num anel A. Ele tem uma propriedade universal. Dado qualquer anel B, onde a imagem por um homomorfismo cai dentro dos invertíveis de B, ele vai se fatorar de forma única. Então, esse cara inverte o S e é o melhor que inverte, né? Ok, essa definição é legal, mas ela não resolve a questão que a gente quer inverter um elemento e garantir que é finitamente representado. Então, a gente tem que dar uma outra definição de finitamente representado. Agora, estou usando x para anel de polinômios, tá? A gente quer inverter o elemento, digamos, T do anel. Bem, seja numa definição ou outra, isso é feito da seguinte maneira. Oi? Vamos ver. Ah, tá. A gente pode... Esse aqui é o anel de polinômios. E esse aqui é o cara que é feito com a construção universal, digamos, que a gente quer mostrar. Então, aqui não é difícil de ver que isso satisfaz a propriedade universal. Como A é finitamente apresentado, também você consegue mostrar que isso aqui é finitamente apresentado e tomar um quociente também você está adicionando mais uma relação, então esse cara é finitamente apresentado. Então, esses caras estão na categoria que está em vista, né? Estou fazendo esse serviço porque nos anéis sem infinito a gente vai ter que passar por algo muito parecido com isso e não é tão, não tem um análogo disso, tá? Então estou perdendo tempo aqui para ganhar na aula que vem, que é mais corrida. Bem, então o que é uma cobertura do anel A nessa acepção? Bem, é uma família de flechas de localização desse tipo, onde essa família AI vai gerar o ideal inteiro. Então, ela tem uma propriedade aqui. Tá? A gente consegue ler essa propriedade de uma forma topológica, né? Porque se nós olharmos o que é o espectro de A, o espectro primo de A como espaço topológico, nós vemos que esse morfismo aqui vai induzir um morfismo do espectro dessas localizações no espectro de A, um morfismo contínuo, espectral de fato. E o espectro desse cara aqui é homeomorfo ao aberto principal gerado pelos AIs. Então, essa condição de cobertura equivale a essa condição aqui. E aí a gente pode fazer as contas espacialmente, de alguma forma, tá bom? Para mostrar, por exemplo, que isso aqui dá uma topologia de Grothendieck. Então, a condição de cobertura agora é essa. Cobrir o anel A equivale a dizer que essas famílias de abertos dão isso. É uma continha de álgebra comutativa. Bem, então, na categoria oposta, você tem efetivamente uma cobertura, não coberturas, né? E essa é a topologia de Zariski e Grothendieck, tá? Tem contas para fazer que valem aqueles 3 axiomas, né? Que isomorfismo cobre imediato, né? É isso. Localizar por um é isomorfo ao A. Localização de localização é uma localização dos produtos, também é uma continha, assim, você pode fazer numa tacada só. E estabilidade por pullback vai se tornar uma coisa que envolve push-out, é um diagrama de push-out, porque a gente está trabalhando com a categoria oposta. Tá? Mas também não é difícil de ver usando as propriedades universais do que é uma localização. Então, as 3 propriedades a gente consegue verificar trabalhando um pouco com anéis. Tá? Okay? Ou, se vocês preferirem, podem trabalhar usando essa correspondência topológica e mostrar isso. Então, esse é chamado de site de Zariski. Bem, em cima do site de Zariski, você pode considerar o topos de Zariski, que são os feixes sobre essa topologia de Grothendieck. Né? Em geral, dado um site, né, um sítio CJ, nós podemos considerar o topos associado a CJ, o topos de Grothendieck. Né? Então, exemplos, né? Toma um locale ou um espaço topológico e olha aquela noção de cobertura dado por supremos. Bem, isso é um topos de Grothendieck. Ou, como eu mencionei agora há pouquinho, né, a gente tem a topologia discreta em qualquer categoria pequena. Então, o sítio é formado por essa topologia. Os caras que são os feixes, todo mundo é feixe. Ele não vai acarretar nenhum tipo de condição extra. Ou seja, todo funtor contravariante vai ser feixe. Ou seja, essa categoria é uma categoria que é um topos de Grothendieck. A categoria de prefeixes é um topos de Grothendieck também. Né? E, em especial, os conjuntos dão um topos de Grothendieck porque elas são equivalentes a uma categoria de feixes sobre a categoria com um objeto só, né? Um objeto e uma flecha, que eu estou usando essa anotação estrelinha. Né? Então, isso aqui vai dar uma categoria isomorfa à categoria dos conjuntos. Essa aqui é uma de prefeixes, que nós já sabemos que é o topos de Grothendieck para topologia discreta. Então, isso é uma prova muito boba, né? que os conjuntos dão topos de Grothendieck. Tá? Essa inclusão dos feixes dentro dos prefeixes tem um adjunto à esquerda. Isso é um pouco trabalhoso de explicar como fazer. Né? Ele envolve o jeito mais simples de apresentar isso através de chamado funtor mais, que vai colar famílias compatíveis que envolve a topologia. Né? Então, se você tem preta, né? Se a gente tem um funtor F, um prefeixe F, a valores em conjunto, o F+, calculado no objeto C, é o colimite, não vai caber aqui, das transformações naturais sei lá, teta não, S, F, onde S é um subfuntor que cobre C. Em particular, como o home traço C pertence a J de C, então a gente já vê, usando a propriedade universal do limite, que isso tem uma cópia do F de C, lema de Oneda. A Ana tinha mencionado que apareceu aqui, primeira vez. Tá? Então isso é uma forma de colocar, esse é um limite filtrante, porque esse cara é um filtro, você pode mostrar que isso aqui dá um filtro de conjuntos. Então esse é um colimite filtrante e o feixe associado, o funtor A de F, calculado no objeto C, é F mais calculado em C. Então essa propriedade do funtor A, que preserva limites finitos, vem de algo que acontece excepcionalmente em matemática, excepcionalmente em categorias também, que é quando duas funções muito diferentes, no caso limites e colimites, conseguem trocar de posição. Então, nos conjuntos, limites finitos e colimites filtrantes ou dirigidos comutam, né? É por isso que a gente consegue construir colimites filtrantes sei lá, de qualquer estrutura algébrica, tipo grupos, anéis, até corpos, através de como se a gente fizesse o colimite dos conjuntos subjacentes e ter uma única forma de estender isso em cima desse conjunto e colocar uma estrutura de corpo, grupo, anel. Tá? Então isso aqui também aparece aqui, essa comutação ela é essencial. Tá? Morfismos geométricos. Tá? Morfismo, o Peter também falou hoje sobre isso, né? Então, esse aqui é um exemplo de morfismo geométrico, a inclusão dos feixes nos pré-feixes. Né? Esse é um funtor que tem um adjunto à esquerda que preserva limites finitos. Então, essa é a definição de morfismo geométrico entre dois topos, geral. Né? Então, um topos C' e um topos F, esse aqui é o adjunto à direita, o F estrelinha em cima é o adjunto à esquerda, o F estrelinha em cima vai preservar limites finitos. Então, todo adjunto à esquerda preserva todos os colimites, todo adjunto à direita preserva todos os limites, mas no morfismo geométrico, o adjunto à esquerda vai preservar não só os limites, os colimites, todos, mas também os limites finitos. Então, algo excepcional. Né? Então, está aqui isso. Né? Alguém que é adjunto à esquerda sempre preserva colimites. Né? De fato, para os topos, essas duas coisas se equivalem por uma aplicação do teorema de funtor adjunto e propriedades dos topos. Então, preservar colimites equivale a ser um adjunto à esquerda de alguma coisa. Né? E a gente pode formar uma categoria chamada categoria, digamos, se a gente presta atenção só, digamos, na parte esquerda, né, para não ter que fazer uma relação de equivalência, uma observação, né, se você tem um funtor que tem um adjunto à esquerda, esse adjunto é único a menos de único isomorfismo. Então, vamos dizer assim, não tem muita perda de informação se você diz que os morfismos geométricos são só funtores que preservam limites finitos e colimites, ou preservam limites finitos e tem um adjunto à direita. Né? Então, vou usar essa coisa e a tradição usar a direção oposta. Né? Eu prefiro a outra, mas essa é mais geométrica. Tá? Bem, então, o funtor de inclusão e com seu adjunto, o funtor feixe associado, formam um exemplo de morfismo geométrico. Como também foi falado mais de uma vez aqui, no nosso evento aqui, toda função contínua vai induzir um morfismo geométrico, esse par de funtores adjuntos. Um deles, que é a parte, digamos, à direita, ela é dada de forma mais direta, fazendo composição, né? E a forma de de montar o adjunto à esquerda, que é, digamos, mais intuitiva, é através da passagem que a Ana mencionou ontem, entre a equivalência de categorias entre feixes no sentido funtorial, que é o que a gente está trabalhando aqui, e feixes do ponto de vista geométrico como espaços etales, né? Então, você tem um espaço topológico X, um outro espaço topológico E, e aqui um homeomorfismo local, né? Então, se a gente apresenta, digamos, um feixe, pega um cara daqui, ou um cara de uma categoria equivalente, que é etale sobre X, linha, e expressa isso aqui e toma o pullback disso. Tem uma continha não muito trabalhosa para mostrar que pullback de etale é etale. Então, esse morfismo aqui também é um morfismo etal. Ele vai corresponder a um feixe, que vai ser o cara da imagem aqui. Então, essa é a forma de a gente passar de alguém desse lado para esse outro, né, através da equivalente de categorias, como está indicado aqui. Isso não é só para os objetos, não é só para espaço e espaço, mas se você tivesse um triângulo comutativo aqui, que corresponde a uma transformação natural, isso vai dar um outro triângulo comutativo aqui e mapas correspondentes. Isso você prova isso usando a propriedade universal dos pullbacks, né? Então, isso já dá um funtor do outro lado e é um funtor que, de fato, eu adjunto à esquerda desse aqui, né? E é um morfismo geométrico, tá? Novamente aqui, para mostrar que essa construção não é um morfismo geométrico, ou seja, preserva limites finitos, você escreve que é o espaço etal associado ao feixe. Ele é feito com a reunião de... A Ana mencionou isso na aula passada, né? O espaço associado ao feixe F, projeção, né? Isso aqui é a reunião de junta das fibras com uma certa topologia, né? Esse é um espaço localmente euclidiano. Como esses caras são feitos tomando colimites filtrantes, você consegue mostrar, e aqui a gente faz um pullback, você consegue mostrar que esse funtor vai preservar limites finitos, essa construção. Bem, esse foi mais ou menos o plano de hoje. Talvez eu tenha um minutinho aqui, eu quero comentar mais algo que talvez seja interessante. Mas amanhã a gente vai trabalhar sobre anéis sem infinito, do ponto de vista primeiro da álgebra universal. Então, anéis sem infinito vai ser uma expansão, você pode ler dessa forma, uma expansão da linguagem dos anéis, né, que vai interpretar mais símbolos do que soma, produto e etc., né. Depois um pouco sobre as construções de anéis sem infinito, a gente vai entender um pouco essa categoria, né. Ela tem semelhanças diferentes com a categoria dos anéis comutativos. Vamos desenvolver um pouco da álgebra comutativa suave, né, que é necessária para o que vem adiante, e falar um pouco de anéis, classes especiais de anéis sem infinito. A última observação que eu queria colocar é mais uma vez sobre os topos, o topos de Zariski, né? Bem, a primeira observação é que, como o Peter mencionou agora mais cedo de manhã, todo topos é um topos que está associado à matéria geométrica, né? E vice-versa, toda teoria geométrica tem um topos, o melhor topos associado, seu topos classificante. Então, o topos de Zariski, né, essa é a primeira observação, o topos de Zariski é o topos classificante da teoria dos anéis locais. Anéis comutativos, claro. Então, a fórmula para descrever que o anel é local, quer dizer que para todo A, vou escrever em termos de elementos mesmo, né? Não de fórmulas, ou A é invertível, que essa fórmula a gente consegue escrever como uma existencial, ou uma conjunção, se você quiser colocar as duas equações não necessárias, ou o 1 menos A é invertível. Então, ele é um topos especial, ele classifica uma teoria. O topos classificante da teoria dos anéis puramente dados é um topos mais simples, é um topos dos prefeixes sobre os anéis finitamente presentados. Então, esse aqui está dentro de 7 elevado a anéis finitamente presentados. Então, esse aqui é o topos classificante da teoria dos anéis, esse é o topos classificante da teoria dos anéis locais. A outra opção que eu queria falar sobre os topos de Zariski é sobre o feixe de Zariski, né? Então, uma das definições que aparecem quando a gente estuda a topologia de Grothendieck são de topologia subcanônica. Subcanônica quer dizer simplesmente que esses funtores contravariantes aqui são feixes. Feixes para a topologia J, né? A gente tem um sítio fixado CJ, vou fazer C aqui caligráfico. Então, se eles são feixes para J, isso para todo objeto C na nossa categoria, a gente diz que a topologia é subcanônica. A topologia de Zariski é subcanônica, né? Como a gente faz? Você quer mostrar que, por exemplo, esse cara aqui é um feixe. Bem, na verdade, a gente pode fazer, ser aqui um anel, né, finitamente apresentado. Tá? A gente pode fazer isso olhando, morfismos que são as os morfismos aqui na categoria de feixe são transformações naturais. Então, estou denotando desse jeito. Então, todos aqueles diagramas que vão envolver, digamos, a cobertura de alguém aqui, ele vai se tornar, justamente pelo lema de Oneda, algo desse tipo. Então, a propriedade que exibia que o F era um feixe, né? Que isso... Bem, a gente estava usando assim F do spec de A, né? Então, isso equivale a dizer, basicamente, que se a gente calcula nos abertos aí, lembra que eu tinha escrito que spec de A é a reunião dos D de A's, né? Isso equivale a ser uma cobertura básica, né? Então, isso aqui são interseções. Vou apagar aqui para não ficar poluído demais, né? Então, desde aí, a J é seu pullback, né? Bem, isso aqui é produto em I. Isso aqui é o produto em IJ do F, igual mesmo, D de AI vezes a J, propriedade de del primo. Bem, e isso, na verdade, a gente pode usar até... eu deveria ter usado home mesmo, mas tudo bem, mas já escrevi F, né? Isso é o A localizado em AI vezes AJ. Então, toda essa propriedade, tudo isso aqui segue de algo desse tipo. Então, aqui são inversões. Então, a propriedade da topologia ser subcanônica, que os funtores Hom são feixes, vem de uma propriedade que a topologia de Zariski de anéis é uma topologia que a nossa noção de, como a Ana mencionou na aula passada, né, que o feixe associado ao aberto, D de AI, é isomorfo, né, a essa localização. Não é igual, mas tem uma coisa técnica aqui. Então, a gente transforma uma propriedade, digamos, sofisticada, vamos dizer assim, numa conta puramente espacial que já estava valendo. Então, via, mais uma vez, o lema de Oneda salvando a pátria. A última coisa que eu queria mencionar, o lema de Oneda se enroscou, o lema de Oneda pode ajudar. Tá? Era isso, né? A gente volta amanhã com Anéis Sem Infinito. Tá? Essas são algumas referências.
Obrigado, professor. Quando gera a topologia, a partir da pré-topologia, é única essa topologia?
É única.
É única. Tem unicidade, né? Tá. Aí, por isso que pode definir o feixe em cima da pré-topologia. Que usando o pullback.
Sim, sim. Para mostrar que as duas coisas são iguais, tem que trabalhar um pouquinho mais, porque tem aquela condição de localidade, né?
Sim.
Mas elas dão a mesma coisa. Então, você não perde nem ganha se você passa de uma topologia de uma pré-topologia. Você não perde, não ganha feixe nem apresenta.
E mais uma coisinha. Aquele funtor A, ele tem relação com...
Sim.
Aquele funtor A que é adjunto?
Sim.
Ele tem relação quando a gente está com o espaço topológico que feixe, pré-feixe, aquela feixificação.
Sim.
Né?
Sim.
Tem, porque lá a gente pega as fibras, né, faz o étale, olha para o de novo. Se restringir é a mesma coisa. Ou não, é parecido, né?
Como os adjuntos são únicos a menos isomorfismo, ele não é igual, mas ele é naturalmente isomorfo. Né?
Tá.
Então,
porque a construção é bem diferente, né?
Só que essa aqui, digamos, geral, não precisa passar para a topologia. Né?
Uhum.
Então, se a gente toma funções contínuas sobre espaço X, e aqui prefeixes sobre X, a gente tem um par de funtores adjuntos. Né? Aí dá para mostrar que essas duas subcategorias, elas são plenas. Né? A gente pode mostrar, na verdade, que essas são as maiores subcategorias onde as unidades e counidades da adjunção são isomorfismos. Então, você pode restringir essa equivalência a uma equivalência de adjunção. Né? Então, essas categorias são equivalentes. Né? Então, você pode construir, digamos, o adjunto daqui, fazendo uma espécie de caça ao diagrama, fazendo um passeio.
Tá. Entendi.
Tá? Um funtor de equivalência, essa inclusão e o funtor de seções.
Certo.
Então, então, esse cara teria duas construções, uma através do mais e outra através do passeio.
Tá. Então aí vai dar
E para funcionar isso é importante que seja pré-definido fiel, senão um lado aqui não vai funcionar.
Tá, entendi. Obrigado, professor.
Nada.
Mais perguntas, comentários? Então, obrigada, Hugo, novamente. Continuamos amanhã. Temos ainda... vamos sair um pouquinho mais cedo hoje para o almoço, então voltamos às 13h30. Tá bom? Agradecer mais uma vez.
It's my pleasure to introduce Professor Valéria de Paiva from Topos Institute, and she will talk about problems, proofs, and the shape of mathematics. Thank you, Valéria.
Funciona. Obrigada, Hugo. Boa tarde, gente. Muito bom ver vocês por aqui. Eu pretendo falar em inglês, mas aceito perguntas em português ou em inglês, no que for melhor. Se bobear, até em espanhol também, se precisar. E eu queria começar dizendo que, desculpe, eu troquei o título da minha palestra um pouco, mas o assunto é o mesmo, então fica tudo do mesmo jeito, é só um título que me parece um pouco mais apropriado para o que eu estou falando aqui. E eu concordo, and now I'm going to swap with Benjamin, that blogs are very interesting, and I had already done this yesterday, saying that the talk that I want to give has a blog post called Problems Everywhere, and we can later on try to do connections between blogs and the Categorias Brasileiro in GitHub, like you guys produced. So, let's see if I can manage these two things. So let's start at the beginning. And I want to start thanking Anna, Hugo, Virginia, Flaviana, and all the organizers, the third EBTC. It's very nice of you to be putting all the effort to get these things going, and I'm very thankful, and I hope everyone else in the audience is thankful too. And personally, thank you guys, thank you. And personally, I'm also very thankful to Samuel Gomes da Silva, who is my co-author, and for all the work that we've been doing in the last, I think, our first paper is 2013, so quite a few years back. Like Benjamin, I was kind of wondering what to talk about here. I don't know if you guys heard, but I just came from the Amazon, where I was giving another talk on something that's more topical, and that I intend to make at the end, which is this business of automatization of mathematics and how we're going to deal with LLMs and the automatic proofs that we need to verify and stuff like that. But I thought it was better to start by talking about how this work on problems came about. And Paulo Veloso, who died in 2020, was a big pioneer of logic and computer science in Brazil. He actually studied at Berkeley, where I am now, the Topos Institute, but he taught at PUC-Rio and UFRJ, and he was my PhD supervisor for a few months, because he knew that I told him that I wanted to go to Cambridge, and that if I had a grant, I would go. And still, he kind of supported me for a few months, which was very sweet of him. He was a very sweet person altogether. So the talk is kind of a little bit of an homage to him. But the talk itself is about something that I hope you guys will be interested in, because it's about category theory. And it's about category theory for problems and solutions, mathematical problems and mathematical solutions. And this is work of Andrei Roth, which I hope everyone here has heard of, because he was one of the biggest mathematicians of the 20th century. And he's much more famous for Kolmogorov complexity and probability theory and all this kind of fancy new stuff, fancy difficult stuff, but he actually did some work on logic as well. In particular, I want to talk about a paper of his called On the Interpretation of Intuitionistic Logic, which is from 1932, and about how life is full of coincidences. So, you know, one of the few good things about getting old is that you can give talks like the one I'm doing today, which is about ideas. And, you know, there are calculations, there are theorems, and you guys will have to go and read about them in the right place. But I'm going to try to give you an idea of why I think these things are important and why I think category theory is a brilliant tool for this kind of work. So you'll see in a minute that there are quite a collection of coincidences, historical and not so historical coincidences. And Paulo Veloso also created his own notion of a theory, a general theory of problems, which he published in 1984. So, the main idea of this talk is that we will study a unified semantic structure for, and pay attention because that is the fun stuff. This semantic structure works for Kolmogorov problems from 1932. It works for Andreas Blass interaction spaces from 1993-95, works for Veloso's theory of problems, and works for dialectical categories, which is what I did my PhD. And so you might think, well, isn't that a bit too much? You know, is this thing really showing up in so many different settings? And yes, that is the point of the talk, is that it does show up in all these different settings, very strictly speaking. So the central object is something that everyone here knows quite well. It's a triple. You have two objects or two sets, and a relation between these two sets. And the point about this complete coincidence, this historical coincidence, is that you can think about this, you know, if you want to think the set theoretically, you can think of them as sets, or you can think of them as objects of a Cartesian closed category or something like that. But they can be thought of in very different ways. So we'll try to think about X as being instances of problems or questions or problems themselves, because an instance of a problem is also a problem. You can think about U as representing solutions to problems or witnesses in logic, in constructive logic, or answers. And you can think of alpha of U and X as U solves X, or U combines a question and an answer, or U deals with witnesses and counterexamples, because I've forgotten to say that X can be thought of as counterexamples as well. And the main surprise of the paper is that Veloso's theory of problems has an additional solvability requirement that corresponds, when you think about these things categorically, to forms of the axiom of choice. So I thought, Hugo would be happy about kind of bringing in the axiom of choice into this talk. But so let's start on the coincidences and the different things that can happen in category theory and in mathematics in general. In 1987, that was almost 40 years ago, I introduced categorical models of Gödel's dialectic interpretation, which were the two first chapters of my thesis in a conference in Denver, Colorado. The conference was about category theory for computer science, so it was one of the first of those things. And unexpectedly, these categories that were models of Gödel's dialectica were also models of Gerais', which was then new, linear logic. At the same conference, Gerais was sitting on the audience and suggested a simplified construction, which I wrote about in 1989. And in 1993, Blass connected it to complexity theory and set theory. And in 1993-95. And after that, Samuel, who is a theorist, realized that, that we could do work together on that, at theory. And very recently, we realized that Kolmogorov and Veloso problems fit the same framework. So we started writing about it in 2021, and I'm at the moment trying to see what else we can do with that. I mean, I have several ideas of things that I still want to do with that, and that's what I want to tell you about. But the point here is that we want to consider this problem, the problem of problems, from a categorical perspective. So we want to see what exactly is the categorical structure underlying all these notions. And more interesting, I want to see whether this is I want to show you that I don't think it's just a historical coincidence, that actually it's not just analogies, but there is essentially the same mathematical structure viewed from 3 different perspectives. And the dialectical categories are the way to actually see the similarities between Kolmogorov's ideas, Veloz's ideas, and Blas's ideas. So let's kind of see where the categories come in. But doing this old trick of kind of telling you what I want you to remember at the end of this talk, at the beginning, what will happen is that for this sort of semantic spaces that I was talking to you about, which I actually managed to get into Wikipedia. So if you try to go into Wikipedia and say dialectic spaces, you're going to see those guys there. But for this kind of guys, Kolmogorov thought about solutions, instances of problems, and solving. Blas and the category that called PV talks about questions, answers, and correctness. And the logical meaning will be witnesses, challenges, and realizations. And I said that the surprise part of the talk is the fact that the axiom of choice comes to play. But I think the important part of the talk is that the mathematical structure is the same. It's only the interpretation that changes. So let's kind of start from how Blas was the first person mentioning this coincidence, at least the first person that I saw mentioning this coincidence. So Blas wrote, a category used by the Paiva to model linear logic also occurs in Vocha's analysis of cardinal characteristics of the continuum. Its morphisms have been used in describing reductions between search problems in complexity theory. So what is kind of interesting here is that Blas, there's a picture of Professor Blas, wrote this. He wrote that in 1993. You can read it in the archive, but it also appears in a book in 1995. And he mentions reductions between search problems in complexity theory, but he does not mention Kolmogorov. He didn't make the connection to Kolmogorov. And when I asked him recently if he had seen it, he said that no, he never paid attention to the paper of Kolmogorov's that I was just introducing to you. But Blas has the same sort of idea, the same sort of objects. Problem is a structured interaction space, but Blas is very famous for doing game semantics, so he thinks about U, X, and alpha as a game, a game between U and X, where alpha is the payoff function. It's a very strange game because it's a game that only has one move. So X issues a challenge, U responds, and it's what we used to jokingly a superpower game, because you say what you're going to do, the other one says, I will reply like that, and then you look and see who won, if it was the challenger or the responder. There's no interaction. You don't go playing the game as it were. So the alpha here is very important because it's the payoff. You decide, and it's not a determined game because, lots of times neither the challenger nor the responder wins. And as I was saying, Blas called this category PV, and as he said, it's a special case of my construction, because my construction was general. I started talking to you about saying U and X as being objects in a Cartesian closed category C, but the Blas and Voches are only using sets. And as I was saying, he was the guy who kind of connected to Galois two key connections, because, and now we get to the main definition. Let's see the morphisms, because a category is not about its objects, right? A category is about the morphisms. So let's see the morphisms. So the objects we know, and the way that this is going to discuss them, they're going to be binary relations between the U and the X, but he's going to write them as triples like that: A minus, A plus, and A, because he wants to remember that they are part of a single A. And you know, he's reusing the A several times because it appears here, here, and here, and the whole thing is an A, a bold-face A, because there's a relation between A minus and A plus, and the two objects are A minus and A plus. And you know, I'm a little bit dyslexic about lefts and rights, so kind of pay attention, but you know, pay attention, thinking hard, because I sometimes get confused here. That's why I prefer to use an axis and not A minus and A plus, because I always get confused between them. But let's see what happens to the morphisms here. So the thing about the morphisms in dialectical categories or in PV or in this Blas category is that morphisms tend to be, when you're thinking about things like Grothendieck construction and stuff like that, they tend to go in the same direction. Here they go in opposite directions. So you have a morphism is going to be a pair of an F minus and an F plus, and the F plus goes from A to B, A plus to B plus, but the F minus goes from B minus to A minus. So it goes down like that and up like that. And if you have been paying attention to things in computer science, you might think, oh, I've seen this sort of maps before, going contravariantly and covariantly, or vice versa. But here they're special, because they have to satisfy their relation A and the relation B in a special way, meaning that, you know, the F minus of B, so you take a B here and an A plus here, and if you take F minus of B, you get into A minus, and that guy has to alpha relate to a little A in A plus. That holds, then we have a similar preservation relation on B, because a B, the F plus of A will give you a B plus, and that has to connect to the B that we had before, which was a B minus. It requires thinking a little bit, but what is important here is that, you know, you might think you've seen this before, because you might think about that as being an adjunction. It looks like an adjunction, but it's a half of an adjunction. It only goes from this to that. So it's more like an implication than an adjunction. Or it's more, I mean, the two spaces, which is another traditional model of linear logic, has a if and only if here. But we only have direction. And it's this one direction that will make reduction of problems such an interesting thing. So I think I probably said that, but I think of an object as representing a problem. The elements of A minus are instances of the problem, specific questions of the type A minus. So the elements of A plus are possible answers, and the relation A represents correctness. So A of xy means that y is correct answer to the question x. I'm sorry, I hadn't realized that I was using A's and B's here, and then in the description I use x and y's. My bad. That's why I prefer to use dialectical ones, where you do have, first, you don't know which thing is a question or which thing is an answer very much, but, you know, and I kind of got used, perhaps too used, to that thing going down here and up on this direction here. Okay. So a few objects, silly, simple objects, where you're thinking simply in terms of sets. You're not thinking in terms of problems quite yet. We're going to think about problems in a minute. So first trivial object is something where you have natural numbers and natural numbers, and n is related to m, if and only if n equals m. A slightly more complicated object, you take natural numbers to natural numbers, because you see, this is where Gödel's dialectica comes from. Gödel was trying to do his own version of Hilbert's program, but he was trying to say that that notions of functions between functions are more understandable, more concrete. Certainly for Gödel, they were very concrete in his head. So he thought that if we all thought more in terms of functional, then constructive logic would become more acceptable, and you wouldn't, I mean, lots of his work was about transforming things that were classical into post-classical. The sense that you want to be as classical as possible. No, sorry, you want to be as constructive as possible, but sometimes you have to give up and get something constructive in, so that you can have the power of the mathematics as we know it. So for Gödel, this thing here, which people find very difficult, particularly set theorists find very difficult, he felt that it was very concrete in some ways. And we can say that an object here, which is a function from natural numbers to natural numbers, is alpha related to a certain natural number, if and only if applying the function to the natural number is equal to the argument that we started from. The set theorists like very much doing things with reals, and you can have, say, inequality between reals, you can have equalities, and you can do that over very simplified objects. So, you could do it only if 0, 1, or the object 2 in a category. And we have some interesting results about that. But that's not to talk to you about. I wanted to talk to you about how to connect that to Veloso's problems. So Veloso kind of said he was inspired by Kolmogorov, but he had a different, it has a different theory of what we should know about problems, what should be considered a problem. So he says that we should think about what's unknown, what's the data that you have, and what's the condition that this data should satisfy to solve your unknowns. As I said, this is a very old stuff from 1984, and I think it has not been taken up very much. And he was not doing category theory. He was just doing some sort of modeling of problems in general. But for me, in Samuel, what happened was that in 2020, Wagner Sanz, who is someone in Goiânia, gave a talk on Kolmogorov in the general theory of problems. And then we realized that what we've been working on for set theory would fit here very well. So let's kind of dig in onto the Veloso notions of a problem. So he says that they are quadruples. So you have the data, what's given, you have the unknowns, what's sought. So these things are similar to questions and answers, right? And you have a condition, like we have both in Blas's and in the dialectica. So the condition means that U is valid answer to data D. But he has this extra thing, an existence postulate, asserting that every instance of a problem has to have at least one solution. And this is something that Kolmogorov was absolutely against. He always said that there are problems that are not solvable. We don't know, I mean, we cannot guarantee that every problem is solvable. But structurally, is exactly what a Kolmogorov problem is, or a PV object. So, you look at their philosophy and you see that they have different intentions for the mathematics that they are doing. But they have, thank you, but they have a very similar sort of thought that that they did not pay an awful lot of attention to how to relate those structures. And that's what we, as category theorists, do. We don't write objects and just leave them lying around. We kind of connect them through morphisms. So, I was kind of just saying, his concern was not logic, but a notion of the problem and what it means to solve one. And, I don't know if you guys kind of realize that, but 1932 is an awful long time ago. And there wasn't even, then there wasn't a formalization of Heyting logic. There was no formalization of intuitionistic logic. There were some ideas from Brouwer of what things should be like and shouldn't be like, but there was no axioms of intuitionistic logic. So what Kolmogorov was proposing is that problems are better than propositions in Aristotelian sort of ways. And so he says that the formula should just correspond to tasks, constructions, problem-solving activities. And in some ways, one of the things that Kolmogorov is very famous for is the Brouwer-Heyting-Kolmogorov interpretation. And I always thought that it was just because people are being nice to him. Until 2020, 2021, when we started doing this work, I never thought about what the K stood for in the BHK. But Thierry Coquin had thought about it and kind of wrote about how this notion of problem is more interesting than we might think. What Thierry did not do was to think of dialectica, which Thierry knows about, in this context. So how did Kolmogorov think about his stuff? He thought about triples, as we said before. You have a set of instances of the problem P, the set I, a set of solutions of the instances, and you have this sigma condition, which says that S sigma solves Z. And his main site was intuitionistic logic is fundamentally a logic of problems in constructions. But his original framework lacked a systematic notion of morphism, has no notion of composition of morphisms, and he kind of started thinking about a theory of reductions, but didn't, of course, 1932, there was no category theory. Category theory comes about in 1945, if you remember. So dialectical categories provide exactly this missing structure, which is an extremely funny coincidence, a very strange thing, if you ask me. So how do we do morphisms of problems? Well, the same way as we're doing it with Blas. You say that a morphism between a problem P prime and a problem P is a pair of functions, one that sends instances of problems to instances of problems, and one that sends solutions of problems to solutions of problems. They go in opposite directions, and they satisfy this condition that if Z sigma f of t, then f of Z sigma prime t. And I have to actually look at the next one to read the interpretation for you, because as I say, I got a little bit confused about, I have to swap things around from dialectica to Kolmogorov's view. So the F translates instance of a problem P into instance of problem P prime, and transforms solutions of P prime back into solutions of P. And this, as I was saying, he thought about it as a reduction of problems. So the thing that's confusing for me is this business that the roles are transposed. The instances that that are questions for Komogorov, they were witnesses for dialectica, and the solutions that were witnesses are now the challenges. So Komogorov problems are inside the category dial sets op, and opposite categories are always very confusing to me. But the op is not cosmetic. It really reverses the direction of the morphisms, turning reductions into the expected notion. A morphism P prime to P provides a way to solve P using a solver for P prime. I find this kind of confusing and complicated, but I always find ops confusing and complicated, so maybe you do better with it. Now I wanted to kind of, and the notion of Kolmogorov matches exactly Voch's connection. So at least everyone who's thinking about problems and solutions are thinking in the same direction. Oops, I think I went too fast because I didn't. So, have I gone too fast? Yeah. The role of the axiom of choice. So the existence postulate was obvious to everyone that it connected, it was obvious that it was extra. It was obvious that he was asking for solutions when no one else was asking for solutions. Blas doesn't ask for solutions. Dialectica does not ask for solutions, but Veloso did ask for solutions. And of course, you can transform a situation where you don't have a situation where you have for all I in I exists an X in S, such that I relates to S. You can transform that into transform this relation into a total relation, which will give you the solution. So Kolmogorov and Blas do not require totality. Things here are solvable or not, but Veloso restricts to total relations. So his is a subcategory of every solvable problems. And this requires choice, which you actually can do a bit better. And these are the terms that I was mentioned to you, that you have to go and read the proofs carefully in the paper, in the archive, which is kind of this one here. But we can show that every Kolmogorov problem admits a morphism to a Veloso problem if and only if P has at least one solution in each instance. And under ZFC, that is ZF with choice, this morphism always exists. And you can do a little bit better, because you can do countable axiom of choice. And you know, myself, I prefer to stay on the constructive base and simply do not deal with Veloso problems, but just deal with Kolmogorov problems, because category theorists would prefer not to deal with the axiom of choice if they can. And so at the same table that I showed at the beginning, saying that's what I want you to remember from this talk, showing up again with different notations. So the objects for Kolmogorov, he writes as instances, solutions, and sigmas. Blas writes like A minus, A plus, and A. Veloso writes data, unknowns, and condition, plus existence of choice, existence of solution. As I was mentioning, solvability, not required, not required, required. Needs AC, no, no, and yes in general. The categories kind of are dial sets up, and a subcategory of dial sets up, because you need to say that the objects here, which I didn't tell you much about, but I did mention that they were a model, that Gerais suggested them as a model of linear logic, a classical linear logic, so you can apply double negation to the objects, And if you do a double negation of the objects, this is the subclass of the guys who do the subcategory of PV that corresponds to classical, but classical linear logic. So if you have AC, you end up in classical logic as usual. And here is the most interesting bit for me, because there's a little bit of a perturbation here. For Kolmogorov, we should get to IPC, intuitionistic propositional calculus, or BHK, and you do. But you have a big problem, because diel-sets has two tensors. It has one tensor that is the one that corresponds to real implication, so a Cartesian closed category, and it has the other tensor that gives you linear logic. So this bit here is a little bit shaky at the moment. So the dialectical framework unifies the three things, but not when you're actually thinking about Curry-Howard isomorphism. It unifies it on the sense of pure algebra. So this is diel-sets op, subcategory of diel-sets op. But Curry-Howard is a little bit more complicated than I'm making it up here. So I now wanted to kind of try to show you problems like the ones that Kolmogorov discussed. So the structures that I've been discussing are not merely logical abstractions. Kolmogorov and Samuel really kind of came up with examples, and there are many more in the preprint. I'm just going to show you two. I'm going to show these two first ones here, analytic geometry and tangent planes. But just so that you can see how ordinary mathematical constructions can be understood as reductions between problems. And maybe this whole talk should have been given the other way around. Maybe I should start with that, because otherwise you just kind of get lost on what happens where. But I don't know, it was the historical view, and I kind of felt more comfortable going this way. So let's have a look at the examples. So everyone knows, kind of even in kind of fundamental, the first grades, I mean, we know about Descartes, right? We know that analytic geometry can be reduces geometric problems to algebraic problems. So the way we're going to use these funky triples is as follows. Let P be a plane, and with a coordinate system, which is a function from U and V. So F takes a pair U and V and gives, as a result, some point in a plane P. And think about L as the family of all the lines in the plane. So I put a colorful plane here, and the function F from U to V going into the plane. Now, think about the family of equations AX plus BX equals C, which we saw earlier today, right? Kind of, or was it yesterday? We saw it very recently. So these are equations of the line. And so the thing that you have to say is that A and B are reals, but not both 0, and C is either 0 or 1. And so you have this E that are all these collections of equations. And you can construct a predicate EQ of L, which is the canonical equation representing a line L in L. So I'm just giving you the setup for this example from analytic geometry. And you have two problems here, right? You have a problem to check whether the point P of UV lies on the line L, and you can write that in this stupid way that I'm doing things as a triple L pi, and it lies or it belongs to. So you will read this thing here, L opposite of belongs, PUV, as PUV lies on the L, on the line L. And you have this other problem, the algebraic problem, to say, does the point UV satisfy the equation E or not? And that we're going to write it like E is the collection of all the equations of lines on the plane. R2 are the points themselves, and chi is AU plus BV equals C. See that this is the same question in different languages, and we'll now use a dialectical morphism to show that one problem can be reduced to the other. So how do we do this reduction? Well, we will have a function f, which take the lines to equations. So this f is my little f and capital F from dialectica. So you take the line L and look at the equation of this line L, and you have this capital F that goes back from R2 to pi, which is like the coordinate system. And the morphism condition that I say is so strange, that goes in one direction and back in the other, says what? In this case, it says that if the point UV satisfies the equation L, then the point UV lies on the line L. So this is exactly what we wanted to do to reduce the problem from geometry to algebra. We'll kind of use the equations, the E equation here, to say that that satisfying that UV being in F of L means that UV satisfies A applied to A multiplied by U plus B multiplied by V equals C. So any algorithm solving the problem P2 algebraically immediately solves the problem P1 geometrically. And the function that goes back, this function that takes UV to the point determined by UV, does not depend on L. You might say it's an awful lot of symbols for something that's totally trivial that we teach people in the fourth year of undergraduate, not undergraduate, kind of school. But you know, it's a way of explaining how analytic geometry actually works via morphisms, saying that the morphism just repeats completely, literally, what we know from and the second problem is much more interesting and much more complicated, and it will show. So the problem now is to reduce the metric problem about surfaces to a problem about planes, and we're going to use the tangent plane for that. So you take a manifold M, two-dimensional smooth manifold, and take L again, all lines L in R3, and calligraphic P, all planes in R3. And kind of try to kind of write these things as problems, as triples, like I was doing before. So you have a sigma that says that an X is a point in the manifold, an L is a line. So L is the normal line to M through X is the sigma condition. And what we try to do is to say that solving the problem of finding the normal line to a manifold, we kind of will transform that into a problem of orthogonality of planes. So a line L through X is a normal line of the plane pi through X if L is orthogonal to every line of pi through X. Of course, orthogonal lines to a manifold are much more complicated than orthogonal lines to planes, right? Everyone knows that there's if you have a plane, you have a collection of an infinity of orthogonal planes to that plane. And then if you look at two planes, pi and rho, we're saying that they are orthogonal if at every point of their intersection, the normal lines of pi line in rho and vice versa. So what I kind of want to say here is that we have these two problems. Find the normal line through each point of M, and we write it like manifold set of lines normal to the manifold and satisfying this condition. L is the normal line to M at X. And the problem recognizing pairs of orthogonal planes. So I have all the planes in R3, all the planes in R3, and this relation simply says that they are orthogonal. And what the dialectical morphisms, the Kolmogorov morphisms, and the Blas morphisms do here is to reduce the plane, the problem one, the problem of finding normal line through M, to the problem of recognizing pairs of orthogonal planes using a slightly more complicated dialectical morphism than the one that I showed you, because I was cheating and trying to do the easy ones. And so the key point on this idea of the tangent planes is that the map that I kind of, let me go slightly, okay, I'm not going to go slightly through this. You can look at it, but the point that I want to make is just that the function f depends not just on the plane rho that we are trying to find the orthogonal line to, but depends on, you're trying to look, you have your manifold, you have your tangent plane in a point, you think about the whole tangent plane and all the things, all the planes that are orthogonal to that tangent plane, and you want to kind of look at the intersection of all those guys. So what you do is to think about when different planes are orthogonal to each other, and you have to move that to the point X where you want your normal line to the manifold. So this means that, and I know I'm getting into my question time, so I kind of just want to finish on this, because the point is, I want to show you where there's more things to be done, right? So this is the interesting example, because it relates to lenses in computer science, and the point here is that lenses in computer science have the same domain and codomain that I discussed before, but they don't have to satisfy this logical relation that I have for dialectica. So the open question that I wanted to get to is that I would like to see if the extra dialectic structure, which is the preservation of truth, can be used to enrich notions of lens and perhaps even automatic differentiation models. So, conclusions, all these notions of problems are manifestations of the same dialectic structure. The dialectical morphisms provide a natural notion of reduction. The Veloso solvability condition corresponds to choice principles, and I'm not very interested in choice principles myself. But the same categorical structure that we've been discussing appears in logic, geometry, set theory, computation, and possibly even automatic differentiation in lenses. So my main message is that category theory reveals common mathematical structure hidden behind apparently unrelated notions of problems and solutions. And I leave you with Tim Gowers on mathematics in general. So he says that there often happens that there are similarities between the solutions to problems, and sometimes the similarities point to more general phenomena that simultaneously explain several pieces of mathematics. And that's what category theorists like to think about, is this more general phenomena that can be very difficult to discover, but when they are discovered, they have very important simplifying and organizing role in the whole of mathematics. And they can lead to solutions of further problems or raise new and fascinating questions. And that's Tim Gowers in 2000, when he was not doing automatic mathematics yet, synthetic mathematics yet, LLM mathematics yet. But Tim Gowers in 2026 is doing LLM mathematics, and we as a community have to think about how we're going to deal with all this synthetic mathematics. Thank you. Sorry about over the running.
Thank you, Valeria. Questions? I think the first one is behind Mike. Mike and Ben.
Eu vou fazer a pergunta em português mesmo. Então, é que tinham fundamentalmente 3 componentes que foram sendo usadas ao longo da apresentação, que era basicamente a questão, o problema, que ele está interessado em resolver, a solução, entendeu? Ou o procedimento de resolução, a prova, e a relação que pareia essas coisas. Pois é. Só que, nos exemplos que foram dados, as condições elas eram aparentemente simples de a gente conseguir descrever como é que você relaciona uma coisa com a outra. Só que eu fiquei pensando em 2 coisas. Eu consigo compor condições para poder expressar condições que não são tão expressas de maneira direta, assim, numa linha. Tipo, eu tenho essa condição, essa condição, essa condição. E também a questão de o quão expressiva a linguagem que eu estou lidando tem que ser para eu poder conseguir expressar a condição ou as condições para isso, porque pode ser uma lista finita de condições, ou pode ser não enumerável, e como é que eu faço com esse tipo de coisa? Dá para tratar isso sistematicamente dentro desse framework que a senhora propôs?
É exatamente isso que eu estava querendo falar, por isso que eu acho que era uma coisa que eu queria falar hoje, porque tem muita coisa para fazer nesse sentido, né? Os problemas que o Kolmogorov descreve são todos mais ou menos fáceis, como você está falando. A gente já tem a solução e a gente está simplesmente reescrevendo ela nessa formato de tripla. Mas a esperança, ou a ideia, é de que a gente possa realmente reescrever muitas outras coisas e relacionar pedaços da matemática, construindo essas triplas de baixo para cima, né? Porque aqui a gente está pegando lá de cima, a gente está usando conceitos muito complicados. Concordo plenamente. No momento, está sendo só escritura das coisas que a gente já sabe a solução. Mas o que a gente pode usar... Porque, para ele não estava falando ele não tinha noção de morfismo, certo? Agora, como a gente tem a noção de morfismo, a gente quer começar por problemas pequenos, mas que possam ser compostos para criar um problema grande. Isso remete direto ao que o Benjamin estava falando antes, de que decomposição de grafos, porque se você pensar nesses problemas como nos conceitos dos problemas, coisas que podem ser representadas por grafo, talvez a gente consiga pensar nesse tipo de decomposição dele para poder depois resolver os problemas grandes, os problemas que vão se complementando. Mas é verdade, não tem... Eu não estou propondo para você uma solução de todos os problemas da matemática. Eu só estou dizendo que você pode escrever alguns desses problemas desse jeito. E eu gostaria de ver outros escritos desse jeito para ver quão longe a gente consegue ir com essa ideia. Ficou claro?
Várias perguntas, eu estou tentando decidir qual delas que eu vou fazer. Mas talvez uma mais básica, se você pudesse comentar um pouco sobre... Porque você falou que na parte que você fez uma tabela, colocou de um lado a lógica intuicionista, de outro lado a lógica linear, e elas são descritas pela mesma categoria dialética oposta, de relações binárias, certo? Poderia comentar um pouco melhor sobre como que isso surge, qual a relação entre essas duas coisas? Porque, pelo que eu sei, né, as categorias dialéticas, elas, de alguma forma, modelam a interpretação dialética do Gödel, né? E, enfim, eu ainda não consegui entender como é que isso acontece, mas como que isso se encaixaria nesse framework de solução de problemas? Né? Ou se eu estou pensando de maneira errada? Essa é uma das perguntas que eu fiquei com elas em mente, certo?
Tá. A conexão para a categoria original, a categoria que modela a dialética, é um pouco mais tênue, de uma certa forma, porque são os problemas mais difíceis. O jeito de pensar nisso é assim: quando você olha para a dialética, o que a dialética faz, eu não tentei falar sobre isso porque requer muito mais lógica das pessoas, mas a pergunta está valendo. Então, você você pega qualquer fórmula da aritmética e reescreve ela numa forma do tipo... Tipo, existe um U para todo X, A de UX. É uma espécie de eliminação de quantificadores, porque você pode ter quantificadores totalmente alternados, né? Existe for all, existe for all. Toda fórmula vai ser transformada numa dessa cara. E esse cara aqui é quantifier free. Ele não tem quantificador nenhum. O que a categoria dialética faz é pensar numa fórmula desse tipo como os U's, que são as witnesses dessa fórmula, os X's, que são os contra-exemplos dessa fórmula, e o alfa, que é simplesmente o que esse A está fazendo aqui. A grande sacada do Gödel, que é a parte que está faltando para você, no momento, é que, quando você tem... Então, a dialética pega qualquer fórmula F e faz isso, transforma numa coisa dessa cara. Você pega duas, pega um F e pega um G e vai transformar numa coisa com a cara parecida, agora com cara de morfismo da categoria que eu estava mostrando antes, porque ele vai ficar com a cara de existe um V para todo Y, B de VY. A grande sacada do Gödel, que todo mundo diz que ele era meio, assim, ele tirava as coisas do nada, a gente não conseguia saber como é que ele tirou isso, mas a grande sacada dele foi dizer que, se você tivesse um cara com essa cara e um cara com essa cara, e esse cara aqui provasse esse aqui, então, isso implica nesse aqui, o jeito de transformar isso num terceiro cara que fosse da mesma forma, é você transformar os seus quantificadores em funcionais. Então, ele vai subir, assim, você está trading off quantificadores por funcionais. É que nem a gente faz em Scholemization, né, que você transforma o for all numa função do X. Aqui ele tem essa versão. Quando você olhar o paper do Gödel, você vê que os funcionais dele vão ficar com essa cara. Existe um F de U para V, para todo F de U de Y para X. Alguma outra coisa acontece. Vai ser uma espécie de A implicando para B. Então, o que está acontecendo é que, na interpretação dialética, todas as alternações de quantificadores foram transformadas em coisas que têm a cara dos meus morfismos. Ele tem a cara da mesma coisa que a gente estava falando um minuto atrás, né? Ele vem para baixo desse jeito e volta usando o seu domínio de saída. Esse aqui é aquele xizinho do plano tangente no ponto X. E as versões de lentes só fazem isso. Não fazem muito... Quer dizer, desculpa, besteira. As versões de lentes fazem isso, mas não tem que satisfazer as relações. Então, esse é onde essa versão da dialética, como é que a dialética entra na história? Ela vai ser, em vez de dial 2 sets, ela vai ser the dial. Porque o Gödel está trading off complicações nas alterações de quantificadores por funcionais de ordem superior. Então, isso aqui vai ser um natural para natural, natural versus natural para natural, vai crescendo os tipos. Fica um pouco claro. Assim, trocar higher order types pelas pelas alternações de quantificadores que existem em primeira ordem. Vai subindo na hierarquia. Desculpa. É o que eu posso fazer no momento.
I'm sorry, Ben. Maybe you can ask Valeria after. Let's take it again.
Obrigada. Achei. Desculpa.
Eu marco aqui.
Hello, guys. Next, we have Sergey Burkin from PUC-Rio. He's talking about nerve and co-bar constructions. Sergey, please, the floor is yours.
Thank you very much. Doesn't work. Which button? Okay. It works. So today's talk is about Cauchy duality, or bar-co-bar duality, the same thing, and also about homotopy coherent nerves of homotopy coherent structures, about categories that allow us to encode homotopy coherent structures as presheaves over them, and some related notions. But the larger point is that these notions are very closely related, and most specialists, they don't know how closely they are related, actually. So the first notion that we will need is the notion of the operate. So what is an operate? An operate is like a category, but morphisms can have many inputs, but only one output. And we can compose morphisms like this, and also we can permute the inputs. So this is very similar to multi-categories that we saw yesterday. Why do people care about operates? Because for categories we have presheaves, we have functors from categories. For operates we have analogous notions of algebras and co-algebras. So an algebra is something that given an algebra over a given fixed operate is something whose elements you can take, so A, B, C, D. You can use these generalized morphisms to perform some computations. And the condition to be an algebra that the output, this output, when we perform sequential computation, coincides with this output when first we compute the operation itself. Okay. So what kind of algebras can we encode? For example, over vector spaces, we can encode associative algebras, commutative Lie algebras, and so on. And from that perspective, the main use of operates is Cauchy duality. So operates have Cauchy dual operates or co-operates also. And this duality explains certain phenomenon in homotopy theory of corresponding types of algebras. So, for example, associative algebras have bar complex, which is, so this part tensor n is something that is associative. While Lie algebras here have this analogous complex, where this symmetric is something commutative. And these complexes, for example, can be used to compute corresponding cohomology with coefficients of corresponding algebras. Good. But the actual story, so first nuance, is that operads themselves are algebras over a certain fixed operad of operads. And this bar-ka-bar-Koszul duality actually works in a bit more complicated way, that given an algebra over an operad P, we can compute bar over this algebra, which is actually co-algebra over the bar of P. And then we compute co-bar, which is an algebra over co-bar of bar of P. And why people do this? Because this is a nice cofibrant replacement of this algebra. So this is a kind of resolution. You can think as a resolution of this algebra. And you do homotopy theory with it. And the whole point of this, so if we consider operads as algebras and do this stuff, we get in the middle almost a cooperate up to signs. Why? Because we have this self-duality. Good. Well, the honest, more complete story is more complicated. I explained for characteristic 0, more general characteristic, more general setting was done fairly recently here. Not going to talk about it today. What I'm going to talk about is how operads allow to encode categories, allow to generate categories that encode homotopy coherent structures. Why do we care? For example, because we can get simplex category from this general construction, and it is very revealing. And today's talk is about this sequence of equivalences. So I will explain what it is. So going from here to here is what we care about. The monoidal product, it means that we preserve monoidal structure. Which monoidal structure? The Cartesian one. So it works in Cartesian setting. But the more general point of this talk actually is that these categories, they work in Cartesian setting, while these categories are correct replacement in more general enriched setting. Okay, so here is the particular case of this equivalence. So on the left is this thing in the previous slide, on the right is this thing. So this appears in this paper, and it is very useful. Why? Because this category is actually almost the category of necklaces, if you know this category. So maybe you don't care about homotopy coherent structures and so on, but like from today's talk, take this, that this category is almost like the category of necklaces, and actually it is slightly better. So now I will explain. In category of necklaces, you have objects like this. These are joins of simplexes, and each simplex is called a bead of the necklace. While in this category here, what you will actually have is something like this. So this has two inputs. This is an operation in the operad of associative algebras, and it here has two inputs because this has dimension 2, this has dimension 1, and this has dimension 3. So this is how it works on objects and morphisms a bit later. Why category of necklaces is so useful? It is, first of all, it leads to the notion of simplicial object, which is correct replacement of simplicial objects in the enriched setting. They allow to recover many nerve constructions as particular cases, and another application is they allow to get a concrete formula when we pass from simplicial spaces to Siegel spaces. And if you look at this paper, it has a lot of applications there of this just concrete formula. So, and here are all possible nerves that you can get using the category of necklaces and the notion of templicial objects. All right. So, another application of this general theorem is that the notion of enriched infinity operators that appeared in this paper, it is formulated in a different language, but it is equivalent to this picture. And yes, also if I go back, so this thing allows to encode not only presheaves, but presheaves, they can have, we can define Siegel conditions, and we can say that certain presheaves are Siegel, and Siegel presheaves are precisely presheaves that encode homotopic coherent structures. And here also we have Siegel conditions, and of course Siegel here is the same as Siegel here, while the categories are completely different. Okay. And another connection is with recent work of Fritz Hermann on bar-bar duality also. But his form is generalization of Lurie's bar-bar. Okay. Now, let's skip this. Or maybe not. So the only difference between this picture and this is that here we can also have operations of arity 0, and here we cannot. And this is very common, not mistake, not problem, but a nuance in this bar-bar duality is that people didn't know how to deal with units, and fairly recently realized that units correspond to curvature on the other side. You take bar of something that has units, you get something dual that, in linear setting, you will not have that d square is 0, so it will not be a chain complex or something similar, but it will be d square equal to something that is 0 only up to curvature. So this is what curvature is. And it is useful because, for example, in this paper, there is equivalence between DG categories and certain curved coalgebras. Now, the notion of twisted arrow category is like this. Probably you know, the objects are morphisms. Morphisms are commutative squares like this, but we can rewrite this morphism as this because we can compute the target by evaluation, and we can also think about this using this picture. Okay. So this twisted arrow category of an operator is a generalization of this construction to operators. Why do we care? Because when we take the operator of monoids, we get the simplex category. When we take the operator of commutative monoids, we get the category that encodes commutative associative structures. And similar for other examples. And the interesting example for me is monoids with bilinear form or with trace compatible, which gives us essentially the cyclic category. If you know, so this story is very much related to traces, and well, this is very basic underlying picture about certain very involved theory. Another new example here is that there is what's called fat simplex category, whose aim was to allow to strictify associative products, so product to make products strict while keeping units non-strict. But it has very concrete definition. But it turns out that it comes from the very same construction applied to certain operators of two monoids and a morphism between them. Okay. Another application is that, yeah, for me, the main problem was that this construction is canonical. It fits in a picture analogous to what we have for categories. There is independent work by Trong Hong, where he uses this category to, for example, define and work with Quillian and Hochschild cohomology of corresponding algebras. Now, how do we actually define these categories? We can take a slice of an algebra over an operator. We can take coslice. We can take composition of these two notions. And we can take underlying category of an operator, and we get the corresponding construction. So you don't need to know what this is, but this is very canonical and natural, and you get this in the end. Good. So what we get is actually this. So we get this category whose objects are morphisms of our operate, and morphisms are such expressions, and the target is just evaluation of this tree. Okay, so now about that theorem that I wrote, how does the passage work? Actually, these operates themselves that I briefly described, they turn out to be more useful than I expected. And they have this special property that there is exactly one operation of arity 0 for each output color. And precisely for such operates, we have that presheaves of underlying categories of these operates are the same as coalgebras of the whole operates. Okay. Now, what are such operates? They look like this, where the red circles are, so this is an operation. The red circles are inputs of this operation. The output is the evaluation of this tree. Okay. What is Fritz-Hermann's operate? It is like this. So if you look, operations like this, they are in particular operations like this, where all vertices are on this, all red vertices are on the same level. And yeah, and red and black vertices, they also need to be marked by actual operations. The next passage works like this, and that's why twisted arrow categories of props appear. So the actual picture, the particular case I was talking about, is actually like this. The generalized morphisms look like this. And so these were the objects, the morphisms will look like this. And these are almost, they are the same as morphisms in necklaces, just different expressions for them, except in our categories, we are also allowed to have such morphisms which we cannot have in necklaces. Okay. Particular statement that we get also is that simplicial presheaves, simplicial objects in Cartesian categories are the same as planar cooperates in such categories, and this can be proved by hand directly. What else? So there is this recent work by Fritz-Hermann about bar-kabar duality, and he recovers as particular case many classical notions. So you can read yourself, but the point is that each of these constructions involves this functor rho, and this rho is precisely what we were talking about, precisely this equivalence, but in particular case. So he understands that rho works in this particular case that is related to necklaces. What I do is show that this rho actually appears in more general setting. Okay, here's Luri's Cauchy duality work. It works like this. So we have bar of some object, which is adjoint to co-bar of some other object. And it has certain intermediate step, and this intermediate step precisely what involves twisted arrow categories. And this, very strangely, nobody understands why, but this inverts the direction in the usual bar-kabar duality. So here we have the usual bar-kabar. So this is kabar and this is bar, but somehow they get exchanged. How else do twisted arrow categories appear? In the work of Tronghang, here these things are used as indexing categories that allow to compute Quillen homology, cohomology, and Hochschild cohomology. Okay, and another nuance is that so I've mentioned that there is, for twisted arrow categories, we have this sequence. And for operates, we get partial generalization. And it turns out that there is more general picture whose partial case here is actually, so this functor here is the work of Protali. And I cannot explain, so this involves, I'm skipping lots of details, and I cannot explain them quickly because it's impossible to do. But the whole point is that it seems like there is very clean general theory such that many particular constructions that various mathematicians did fit very nicely into this general picture. And this, like the whole point of this construction was to prove that this, any infinity operate P here is infinity localization in the sense of operates of this. So this is infinity operate and this can be strict operate. But this turns out to be fitting very nicely into this general diagram. And this we can skip. How many minutes? 3. So yeah, another thing is that this twisted arrow infinity. I was talking, the stuff that is in my work, it works for set operates and it should work for infinity operates in spaces. But there is a definition, but I'm not very happy with it. So I wanted to have another definition that given a Siegel dendroidal space, which is like Siegel space, but for operates, would produce Siegel space, the usual Siegel space, in the sense that it would give us infinity category. At least, well, we will also need to complete it. But that's nuance, that doesn't matter much. So the whole point is that this construction from infinity operate to infinity category seems to go also through this general theory. And yeah, sorry, I cannot explain this in more details. Do you have any questions?
Thank you so Do we have any questions or comments? So let's thank Sergey again.
Certo. Oi. Oi, oi. Tudo bem? Eu acho. Consigo escutar? Ok, sim. Não, para cair. Não sinto. Peraí. Vai quebrar. Tá bom, obrigado. Tenho sim. Ok. Tá certo, sim.
Now we have Cesar Ipanaki Zapata from USP. He's talking about cohomology theory over a category with covers. Please.
Okay. Thank you so much for this opportunity. Well, I will speak in Portuguese, okay? Bem, nesta oportunidade eu vou falar sobre conceito de cohomologia. Tá? Esta cohomologia é motivada, tá? Num problema bastante simples de formular, tá? Que é a categoria seccional. Tá. Então aqui a gente pega uma aplicação. Tá? A categoria seccional consiste em encontrar a menor quantidade de abertos que cobrem y tá? De tal forma que em cada aberto existe uma aplicação contínua, tá? De tal forma que a composta, tá? Aqui é a inclusão, tá? Que a composta comute a menos de homotopia. Tá? Isso é a categoria seccional. Tá? Quando você pede que isso seja estritamente comutativo, ou seja, que de fato estas sejam seções locais estritas da F, isso é chamado número seccional. Tá, ok? Tudo bem. Esses dois problemas simples são, bom, de fato foram estudados, são parte da área de topologia algébrica, tá? Chamada categoria seccional. E quando você escolhe o caso particular de uma função, aparecem, dão início a teorias. No caso, por exemplo, quando f, se você pega x um ponto, tá, e a f aquela aplicação só, isso dá a categoria Listerner-Schirmer, que é toda uma teoria de um grupo de estudo. Ok? E quando você pega a f, justamente este tipo de fibração, aqui o x a 0,1 é o espaço de todos os caminhos em x, você pega um caminho e leva ponto inicial, ponto final. Essa é uma fibração. Para esse caso, dessa f é a teoria de complexidade topológica, que é uma teoria muito usada em problemas de robótica, no caso particular, problema de planejamento, movimento de robôs. Tá, ok? Muito bem. Então, em geral, para calcular a categoria seccional, tá? Não é fácil calcular diretamente a categoria seccional, então o que se faz é estimar. As cotas superiores, tá? Que me permitem estimar a categoria seccional são em termos da homotopia da função dos espaços. E, do outro lado, para estimar inferiormente, é onde justamente aparecem as comologias, teorias de comologia para estimar essa categoria seccional. Tá? Este nil que aparece aqui é simplesmente em geral, você pega um subconjunto num anel e você vai procurar o menor n, de tal forma que o produto de qualquer n elementos nesse subconjunto é zero. Esse é o nil de um subconjunto em um anel. Ok? Então, para estimar a categoria seccional, justamente você pega qualquer teoria de cohomologia multiplicativa, tá? Nos espaços topológicos, aí você induz em cohomologia, calcula o kernel desse daí, e aquele nil desse kernel é justamente uma estimativa cohomológica da categoria seccional. Ok? A categoria seccional, se bem se tem estudado em diferentes variantes. Por exemplo, você também pode estudar categoria seccional para aplicações equivariantes, tá? E muitas versões aparecem na topologia algébrica, é todo um campo de estudo estudar categoria seccional. Então, aqui, o trabalho que, de fato, eu já desenvolvi, tá? É não só conseguir estudar, porque aqui você pode imaginar, não, este problema, você pode pensar em outras categorias, tá? Pegando a ideia de Grothendieck. No lugar de aqui, por exemplo, a gente precisa de noção de cobertura, tá? Aqui a gente está usando a noção usual de cobertura por abertos. Então, se você muda, em particular, essa noção de cobertura, não, já pode explorar como é aquela categoria seccional com essa nova noção de cobertura. E não só isso, você pode também estudar isto, explorar em outras categorias. Se você está pensando, por exemplo, em grupos, aqui já seriam as inclusões usuais, não? E estes são subgrupos, e estes todos são homorfismos de grupos. E também o problema de estudar, não? Este tipo, não? Aqui, por exemplo, você considera estricto, ou al menos certa relação aí entre homomorfismos de grupos, e aparece toda uma teoria já em categoria de grupos. Se bem esse número seccional, ou categoria seccional, em teoria de grupos, é uma área que ainda está sendo explorada, tá? Se bem esse invariante generaliza outro problema já próprio teoria de grupos, que talvez alguém de vocês conhece, que é o número de cobertura de um grupo, que simplesmente você pega um grupo e procura a menor quantidade de subgrupos próprios, cuja união dá o grupo. É um problema muito estudado em teoria de grupos. Tá ok? Muito bem, então tudo isso, justamente para dar um jeito mais categórico de entender esse tipo de problemas, é o que vou apresentar hoje. Em particular, generalizar esta estimativa cosmológica. Tá? Então, justamente, bom, a questão era isso, inicial. Como que a gente pode generalizar, desenvolver a teoria de tal forma que aquela estimativa cosmológica eu consiga para esse contexto categórico. Tá ok? Muito bem. Bom, os trabalhos que eu desenvolvi já sobre categoria número seccional, nesse artigo que está aparecendo no archive, ok? Mas eu me vou enfocar só na parte da cosmologia. Tá? Então, bem, o primeiro que se faz, não? Seguindo a ideia de Grothendieck, eu vou pegar uma categoria e já vou fixar já uma topologia. Aqui na topologia no sentido bem geral, eu não vou pedir nenhum axioma, ou seja, não precisa ser uma topologia de Grothendieck. Simplesmente você já fixa aquela coleção do CIF que você vai considerar como coberturas. Ok? Uma vez feito isso, você já pode falar o que é uma cobertura para um objeto, certo? Você pega um objeto, aqui já você fixou, não, a topologia, e você simplesmente, bom, o natural é dizer que esta coleção de morfismo é uma cobertura quando o CIF gerado, justamente, é um J cobertura daquela que você fixou. Ok? Então, aí você já tem noção de cobertura para um objeto. E bem, aí já definir o que é o número seccional a nível de coberturas já é bastante natural, tá? Aqui já você tem o que são a noção de cobertura para o seu objeto, tá? E aqui pode você pedir que seja comutativo ou menos de uma certa relação, tá? Que você já prefixa no conjunto dos morfismos aí. Então, o número seccional, não, é justamente procurar a menor quantidade de elementos que cobrem seu objeto, onde existam, não, esses triângulos comutativos. Tá, ok? Então, esse é o número seccional. Como eu falei, todo foi inspirado em categorificar o que acontece em topologia algébrica. Então, os resultados se conseguem. Mas, no caso da estimativa cosmológica, tá? Justamente eu preciso dar as condições para conseguir, de fato, mostrar aquela desigualdade de que a categoria seccional está limitada pelo NIL em cosmologia. Bom, aqui é simplesmente questões bastante técnicas que eu apresento aqui, tá? Para definir, introduzir essa cosmologia que serve para essa estimativa inferior. Tá? O primeiro que se faz, bem, pego uma categoria, um objeto inicial, todos os limites finitos existem, também os colimites finitos, tá? Eu vou trabalhar com esse tipo de categorias, mas para definir, aqui, por exemplo, eu vou falar do que é uma família distinguida de morfismos, que é o análogo que acontece no caso topológico. Aquela família distinguida de morfismos simplesmente são as inclusões, não precisamente de abertos, simplesmente inclusões. Tá? Então, aqui, bom, aqueles axiomas para que sejam uma família distinguidas, isto aqui, bom, isto que aparece neste negócio acá, você pega o limite desta família de morfismo com codomínio X, pega o limite, depois pega o colimite. Tá? Isso que aparece acá, isto é a aplicação que sai da propriedade universal. Tá, ok? Bem, com isso, deixa eu ver. Aqui você define o que significa um par, tá? A nível já de categorias. Tá? Simplesmente você tem um X e um morfismo distinguido com codomínio X. Esse é um par. Tá? Tem aqui já as coisas usuais, quando você já sabe quem que é aquele I que aparece, já simplesmente se denota como XA. Tá? Para simplificar as notações aí. Muito bem, aqui aparece o morfismo restrição, que é aquele que aparece em cosmologia, tá? Mas aqui eu vou pegar uma congruência na categoria C elevado a 2. Esta anotação estou usando, pois, de fato, C elevado a 2 é uma subcategoria completa da arrow category. Tá? Com isso, eu já posso dizer primeiro o que é uma cosmologia sobre uma categoria com coberturas, tá? E análoga. simplesmente uma coleção de funtores, que caem aqui, por exemplo, na categoria grupos abelianos, na categoria de módulos. Tá? Uma família de funtores indexada pelos inteiros, tá? Com estas transformações naturais. Tá? E que satisfaz os axiomas que, de fato, eu preciso para aquela estimativa. O primeiro é que vocês imaginam justamente aquela sequência exata associada a um par. Isso eu vou pedir. Tá? Outro axioma que eu vou pedir é justamente relacionado com a topologia que eu fixei no início na minha categoria. E este axioma me diz o seguinte, que se eu tenho uma cobertura finita, tá? O grupo de cohomologia deste par tem que ser trivial. Isto é análogo que acontece no caso topológico. Se você tem uma cobertura finita com noção usual de cobertura, ou seja, acá aparece a união daqueles abertos, acá a união é o X, a gente sabe que o grupo de cohomologia do par X, X é zero para todo. Okay? Então, isso é uma abstração disso. Então, com esses dois axiomas, é uma cohomologia, tá? E, além disso, eu preciso de uma estrutura multiplicativa. Tá? Então, aqui também, para introduzir estrutura multiplicativa, eu preciso de um linguagem um pouco técnico aí, mas é bastante natural. Tá? Então, aqui eu consigo definir um produto cap, eu tenho já um anel de cohomologia para estes pares, tá? E com isso já, de fato, se dá uma categorificação daquela estimativa. Acontece de forma análoga, mas já agora sobre uma categoria com certa topologia que você aí fixou. E perceba aqui que este resultado, eu não preciso que se chame topologia com certos axiomas, vale para qualquer topologia que você fixou, não precisa de Grothendieck. É bem geral este resultado. Mas o importante aqui é que me permite, justamente como eu falei, trabalhar sobre categorias onde não consigo definir uma topologia de Grothendieck. Basta você escolher qualquer topologia e aí justamente explora como é um número seccional. Tá ok? Bem, a prova justamente, de fato, é dada pelos axiomas que eu disse. Bom, a ideia da prova primeiro é do seguinte jeito. Bom, vamos supor que o número seccional é M. Tá? Isso significa que você tem aquela cobertura, com M morfismos, e estes triângulos que comutam a menos da relação R. Ok? Depois, você supõe que aquele nil não é menor ou igual que M, do contrário, é maior que M. Pela definição, significa que existem M classes de cohomologia, cujo produto cap é não nulo. Então, aqui, você induz em cohomologia, tá? E aí, o que você tem é que, de fato, como estes estão no kernel, então estes alfa sub L estão nestas J sub L. Aqui onde você usa aquela sequência exata longa no par, tá? Justamente para chegar à contradição, você vai chegar na contradição que este produto cap é zero via estes levantamentos nas cohomologias. Ok? Bastante técnica a prova, é a mesma que se faz no caso topológico. Ok? Muito bem. Mas isso recupera o caso topológico, tá? Você já pega qualquer teoria de cohomologia generalizada, tá? E não só isso. Agora eu consigo usar isso para caracterizar justamente problemas, em particular a teoria de números, por exemplo. Bom, esse é um caso simples, onde a gente sabe que o número primo, a gente sabe que é infinito, de fato acá você pode reemplazar qualquer número, qualquer subconjuntos naturais. Se ele é infinito, induz esta informação, já em termos de cohomologia, sobre a categoria de conjuntos. Tá? Coisas assim desse estilo você consegue. Tá? E não só isso, por exemplo, se tem este resultado que eu consigo expressar em termos de cohomologia, é que se a conjectura de Goldbach é verdade, então qualquer cohomologia que exista na teoria de conjuntos, com aqueles dois axiomas, tá? Vai ter kernel trivial. Tá? Onde aquela função que você escolhe, bom, é bastante natural, essa daqui. Ok? Muito bem. Bom, são alguns exemplos de esta vantagem de trabalhar sobre este tipo número seccional que me permite, ¿no?, expressar, ¿no?, esse tipo de problemas, ¿no?, que de fato são problemas de bom nível. Tá? Muito bem. O interessante do número seccional só no contexto topológico é que você consegue expressar propriedades topológicas em termos desse número. Bom, vou dar alguns exemplos. Por exemplo, propriedade de ponto fixo. Tá? Existe um grupo de pesquisa, teoria de ponto fixo. A gente consegue, tá, caracterizar em termos do número seccional ponto fixo. Tá? Bom, isso é já de isso foi nesse artigo. Tá? Também, um pouco mais geral, teorias de coincidência, propriedade de coincidência. Também se consegue caracterizar em termos do número seccional aquela propriedade topológica. Não? Bom, isso, detalhes aparecem nesses trabalhos. Tá? Borsuk-Ulam, topologia algébrica no Brasil, muito conhecido por estudar a teoria de Borsuk-Ulam. A gente consegue caracterizar, em termos de número seccional, a propriedade de Borsuk-Ulam, em particular o índice da involução. Ok? Muito bem, e assim, no caso, por exemplo, já um pouco mais algébrico, no grupo, aqui só estou lembrando, tá, o número de cobertura do grupo. Ok? O interessante é que o número seccional, já em teoria de grupo, na categoria de grupos, justamente é uma generalização do número de cobertura. Tá? Bom, os resultados já neste contexto aparecem, neste artigo aqui, que está no archive. Tá? E, bom, aqui o interessante, pois, que já você estuda com próprias técnicas da teoria de grupos, tá? Por exemplo, em particular, com cohomologia já de grupos, aí você consegue relacionar esse invariante. Tá? E, bom, também aparece no caso de este problema, que é o problema migração de dados. Tá? Aqui já, de fato, a teoria se desenvolve já pensando em homorfismo de grafos, todos são homorfismos de grafos, subgrafos, tá? E aqui aparecem novos invariantes, que são estes negócios chamados de complexidades. Tá? Limitando inferiormente ao número seccional na categoria de grafos. Ok? Bem, são alguns exemplos que eu mostrei. Tá? E, bom, muito obrigado.
Temos perguntas ou comentários?
Você tem exemplo de uma cohomologia que se aplica naquele caso da conjectura de Goldbach, uma construção de cohomologia?
Justamente aí, a cohomologia é bastante... Só que aquela implicação que eu usei, a ideia é encontrar uma cohomologia, tá, onde você consiga um elemento no kernel. Se você faz isso, já mostraria que a conjectura de Goldbach não é verdade. Então, se você pensa, por exemplo, bom, aqui estamos nos conjuntos, simplesmente considera como a topologia discreta. Só que nesse caso, se você aplica cohomologia singular, isso não dá, justamente nesse caso dá que o kernel é trivial. Isso daí não foi suficiente. Justamente um grande desafio é construir uma cohomologia onde você consiga um elemento no kernel. Aí já você mostra que a conjectura Goldbach não é verdade.
Sim.
Mas é um grande, justamente, é um problema muito desafiante, de fato. Sim, sim. Mas outras técnicas justamente são, parte do trabalho de tentar, com outras ferramentas, construir este tipo de cohomologia. Mas aos usuários, quando a gente aplica aos usuários, até agora não são suficientes. Precisamos de melhorar isso. Sim. Obrigado.
Mais alguma pergunta? Vamos agradecer novamente o César.
Oi, oi. Tá... Foi. Não, acho que é assim. Você coloca assim. Tá funcionando, tá bom. Onde é que aponta aqui? Tá bom. Beleza.
And now, before the coffee break, we have Mike de Andrade from USP. He's talking about duality and completeness. Please.
Okay, thank you. So, I'm going to show you, talk about a little bit about my PhD thesis, the things I'm thinking about, and yeah, how I'm trying to solve those problems. I'm being supervised by Hugo and from Carnegie Mellon. So, okay. And I like to think about math because I come from physics, right? And in physics, math is basically this. You have algebra and you have geometry, and you try to switch from both worlds, right? But then this is an adjunction, actually, mostly of the time, right? And you have a functor, and that goes from an algebraic category, and from the opposite, and a geometrical category, right? And then I started to study like logic, and I realized, oh, it's the same thing, but a little bit more general, because in logic, usually you have syntax, and in the other side you have semantics. And I'm more like a semantics guy, because, yeah, I don't know. I like geometry, but yeah, I don't know. I think that things are supposed to have meaning. Maybe that's the thing. And I'm going to talk about, I'm trying to find such an adjunction, such a duality for a specific syntax. And I'm going to talk about give a motivation based on, I think that this was the first, or maybe one of the first dualities. And some reminders. This is well, are you listening? Okay. So some reminders here, but I won't have time to come up. Hopefully, you can remember some of the talks about talked about a little bit about this, and some other people too. But okay, so the main idea is that you have Boolean algebras. You have something called a filter or a prime filter, which is equivalent to a neutral filter. Is a set that a filter is a upward closed set with respect to this order and the order directed. It is prime if it is non-trivial and upward directed as well. The thing is, logically, so examples, the order of any set is also a Boolean algebra, which is the free Boolean algebra in the set. But the set order by inclusion is not Boolean in general. Okay? Okay, because, okay, so that's it. So we have a representation theorem. I think this was first proven by Stone, which says that if you have a Boolean algebra, and you then you have an injective Boolean homomorphism from B to the power of some set. And this set is the set of prime filters in B, which is the same as the set of ultra filters, which is equivalent to the set of Boolean algebras or homomorphisms from B to the 2 Boolean algebra. And this is basically what is interesting about this Stone representation and Stone duality that might be used some of you, or is that this is actually equivalent to the completeness theorem from logic. Say what this is, but yeah, I'm going to give an intuition about what I'm saying, which is equivalent to the axiom of choice. So this is highly non-constructive. You have the Boolean prime ideal theorem. If B is a Boolean algebra and I is an ideal and F is a filter, which the intersection is empty, then you have a prime filter, P, that contains your initial filter, such that the intersection of this new filter, prime filter, is also empty. And this is equivalent to the axiom of choice.
or maybe it's weaker. I don't remember. But this is the equivalent to the completeness theorem. And okay, I'm not going to give you the proof is highly non-constructive. Okay, because you need to use the axiom of choice. I don't know. I don't think I'm going to. Okay. Oh, this is the proof of the representation. Okay, the representation goes this way. Okay, if you you construct the map, you want to construct an injective Boolean homomorphism. Okay, and this is done like this. It is going to be this map H. Okay, and to each B, an element of your Boolean algebra, you associate the set of prime filters or ultra filters such that B belongs to F, which is the same thing as the set of Boolean homomorphisms such that F of B equals to 1. It's the same thing, okay? You might need to think a little bit about this, but trust me, it's the same thing. And you need to prove this is, okay, check this is homomorphism is Boolean, it's direct. But the interesting thing is to check that this is injective. Injectivity is equivalent to the Boolean primary theorem. It's going to say that if you suppose that A is different from B, we need to find a prime filter, okay? So this is a set of prime filter, such that B belongs to P, and A does not belong to P. And you find this applying the Boolean prime ideal theorem to the down set of A, which is an ideal, and the upset of B, which is a filter. Okay, and why this is a completeness theorem? Because, okay, in this setting, what would be the model of your Boolean algebra? The model, the model of a Boolean algebra in the two Boolean algebra is just a thing that's saying if an element is true or is false. It's just this, which also that is a model is just a Boolean homomorphisms, which is the same thing as a prime filter. So a prime filter is a model in a traditional, a two-valued model of your Boolean algebra. And inject in this representation theorem, which is the Stone representation theorem, is saying precisely that. That is, okay, so what is completeness? Completeness is just saying that if f of b equals 1, that is, b is true for all Boolean homomorphisms from b to 2, which are the models, then b is necessarily equal to 1. This is the completeness theorem for propositional logic. And or equivalently, if f of a equals f of b, then for all f, then a equals b. So, and this is the representation theorem is the completeness theorem, because it is precisely saying that if A is different from B, then because the injectivity condition is giving me that H of A is different from H of B, which means that the set of models that sends A to true is different from the set of models that sends A to B. So it's the counterpositive of this assertion, okay? So this is the completeness theorem. And the important thing for us is that if B is a Boolean algebra, then the set, so we can construct the set of prime filters. And, but when you map this to the set 2, we get another Boolean algebra, which is the Boolean algebra of subsets of your Boolean algebra of your set, okay? So basically this is going to give you an adjunction. So you consider Boolean algebra homomorphisms from B to 2, then functions from this set to this set. And this is just the evaluation function, the evaluation morphism. Okay, this is kind of a lot of, okay, so a lot of information because you have to carry on all the data you have, but trust me, this gives you a map, and you have a map in the other direction. First, you take a set, then take the subset of all subsets of this set, then you take the Boolean algebra homomorphisms from B, from this set to 2, you're gonna have another map from set to set, and those maps, they form an adjunction, okay? I didn't put the adjunction here, but yeah, you're gonna have an adjunction from the category of Boolean algebras to the category of all sets. Okay, I have Okay. The thing is, you have only an adjunction. You don't have an equivalence, of course. You don't have an equivalence between the category of sets and the category of Boolean algebras. But you can't restrict one of the functors. So you will get an equivalence of categories, and this will give you an adjunction. And how do you restrict this category? We will restrict the category of sets, basically. How? Putting a topology. Okay, so we're going to look at the image of this map here, and we are going to put a topology. Okay, and this topology is the stone topology. Okay, it is a spectral topology. It's very similar to the Zariski topology that Augusto was talking about. And it is simply like this. You take the set of prime filters and take a basis like this. P. A basis over the element P is going to be the set of models of prime filters belonging to, such that in this model B is true, or that B belongs to the prime filter, which is the same thing. This is going to be called spec of B, because this comes from algebraic geometry, is the same thing as the spectrum of a ring. And basically, if you do this, you can reconstruct your initial Boolean algebra from this by taking the Klopen, the Klopen with the sets that are open and closed, okay. So this is an adjunction. Basically, this is everything I said so far, and you can restrict even more, and you're going to have an equivalence between an algebraic thing and a geometrical thing. That's the idea. Homework. I think you could do the same for Zyka spaces and Heiting algebras, but you have to consider. So that is an important concept, which is the set 2 lives in the both worlds. So we call it a dualizing object. So you just need to think about what would your dualizing object would be here, and your dualizing object would be here. Those dualities, they exist in the literature, but no one has put them in this framing. I don't know why. And so we are about the low-level thing, a pre-order set with some structure. But you can do the same in regards to category. So we raise the level. So we were talking about propositional calculus. Now we are going to talk predicate calculus. And we do this by considering a category with some structure. And a category with some structure, you can think about it as a fibration of that structure, which is called a hyperdoctrine. But I'm going to give this definition. And we don't need to think about too much about this, but a pretopos is a category which is both extensive, which means that it is well-behaved with respect to coproducts. They are disjoint and put back stable, and exact if there exists well-behaved quotients of equivalence relations in this category. The thing is, a pretopos is the place where you can talk about coherent logic. And you can ask that the lattice of subsets of any object of C to be a Boolean algebra. Then this is a place where you can talk about classical first-order logic. And the thing is, set is a Boolean pretopos, any pre-shift pretopos over a groupoid is a Boolean pretopos. In fact, this is an equivalence. And a model of that pretopos would be a functor that preserves the structure of pretopos to the category of sets. If you take the category, so if you take the category of models of your pretopos, it is going to be another. It's going to have another structure. It's going to be an ultra category. And if you don't know what a ultra product is, you just need to think about this as an object that comes from an ultra filter on a set. And you have a functor that will respect the structure of the ultra filter construction. So an ultra category is a category with, 5 minutes. The thing is, you can make the same exact thing we did from the stone topology with the stone duality for pretopos, and this is going to be a completeness or stone representation for full first-order logic. Okay, cool. Okay, so there is one question: how can I restrict this equivalence? So why is this? Because the ultra category structure is the restriction. Now, you impose the ultra category structure is exactly to have the equivalence or the completeness theorem. Okay, so yeah, you can try to do this for heightened pre-to-point also, but I haven't been able to do this. I think this seems to be easy, but I don't think it's not so easy. So to finish, what I'm actually trying to do, I'm trying to do the same thing, but for Martin-Love type theory, extension of Martin-Love type theory. And basically, I think this is not extensional. I'm not going to say what extensional is, but there we have this famous theorem in category theory, which is the Gabriel-Wimmer duality. This is also a completeness theorem for a specific kind of logic. What I mean by that is that this is the category of exact or finite limit. Our category here has all finite limits. This functor preserves all finite limits. And when you take this category of functors, you're going to have a category with this structure, which is a locally finitely presentable category. Okay, what is a locally finitely presented category? An object of a category is said to be finitely presentable if this functor preserves future limits. And A has a small subcategory of finitely presentable objects, such that the whole category is obtained from the finitely presented by taking directed colimits. So this is an equivalence that is kind of canonical in category theory for almost 50 years, okay? But why is this a completeness theorem? Because lax categories, they are specified using everything that you can consider lax categories as the syntactical category of sublogic of first order logic, which involves conjunctions and existential quantifiers with a proof of unicity. So when you take this category of functors, you're taking models of this sublogic of first order logic. And okay, so by the discussion we have seen so far, this is a completeness theorem for this specific kind of logic. Okay? And okay, but there is also something interesting. This lax category is also what we call a bifibration. Okay, I'm not going to say what this thing is, but the thing is, a bifibration is the same thing as a model for Martin-Love type theory with dependent sums and extensional types. So this is some sort of completeness theorem for Martin-Love type, a specific kind of Martin-Love type theory. Okay, so what I'm trying to do is to cut this equivalence so that I can consider, okay, I have dependent sums. Dependent sums is something like this. It's kind of a set of tuples where X is from the set A, but you're going to have an Y that comes from a set B, but the B is not fixed. The B is going to depend on the first element, the first term. Okay, so I'm trying to extend this. Okay, actually cut the equivalence for the case. I have 1 minute. Okay, for the case where you have dependent products. This is some sort of data structure where we have dependent functions. Okay, so yeah, you can cut this very trivially if you in this side here. Okay, if in this side here you consider the locally finitely presentable categories where the finitely presentable categories are LCCC. This is kind of trivial, and okay, but the morphisms needs to be lax, and I'm trying to understand how I can do this when I consider this category locally Cartesian closed category. I'm not going to say what is this, but okay, those are the models, or kind of a model of Martin-Love type theory with dependent sums and dependent products. I'm trying to understand how can I cut the Gabriel-Wimmer duality if I consider LCCC with LCCC morphisms. I don't know what this is, because working with LCCC morphisms, which I'm not going to say what it is very complicated. It's the same thing as preserving this kind of structure, which is not a limit. So no one has talked about what this thing is actually. So I think this is some sort of generalized sketch, because it's some sort of limit of limits, of finite limits. I don't have time to say explicitly what this is, but okay, this is exactly the dependent product, and you take the initial object of this category of pullbacks. So okay, but the question is, how can I characterize the models? You have an article, and this guy proposes a generalization of scats, and I'm trying to understand if I can characterize the models of this generalized sketch in a Gabriel-Ulmer style. I think this could help me out. And to finish, I guess I need to finish. There is also other thing that I'm pursuing. It has been proved in topos theory that if you have Grothendieck topos, you can find a connected and locally connected Grothendieck topos F, such that F is the topos of sheaves of a topological space, and this morphism is going to be conservative, which means that it reflects isos and also LCCC. And the fun thing is, Steve had an idea that using this theorem, you can find a locally Cartesian closed embedding of any category into a category of sheaves over a topological space. And the thing I'm trying to do now is trying to characterize what properties this topological space are going to have. And by doing so, I could also find some sort of duality. And the things I'm trying to answer right now, I have a lot of answers, or a lot of questions, no answers. But it's good that I have a lot of questions, I think. I have many other things to say, but time is over. Thank you. I have some references here, and that's it.
Thank you. Any questions or comments?
Eu vou fazer a pergunta em português, tá?
Tá.
Então, o meu foco, na verdade, era essa primeira parte aí, que é dessa pergunta, de que estrutura geométrica pode melhor descrever o comportamento dos termos. Que, como você falou de teoria de tipos e categorias cartesianamente fechadas, que formam um modelo para lambda cálculo, e tem tudo a ver, então, tipo, você poderia explorar um pouco mais, tipo, quais foram os insights que você teve até esse momento para, tipo, tentar responder esse teu primeiro questionamento da estrutura geométrica, que parece que comunica, tipo, de maneira muito natural, ou pelo menos deveria aparecer em algum momento.
Então, eu acho assim que, primeiro, tem duas formas de ver, né? A parte geométrica, meio que travou aqui. Para o outro lado, tá? Tá. A parte geométrica, assim, a parte tem a categoria de modelos, né? Vai ser uma subcategoria dessa categoria localmente representável, que é a categoria de modelos da parte de limites finitos. Agora, a parte que não é de limites finitos, que tem a ver com a preservação do produto dependente, eu não tenho ideia. Tipo, eu estou tentando descobrir. Mas é uma categoria de modelos. Aqui também tem uma parte que é geométrica, né? Porque eu consigo associar um espaço topológico. Eu também não sei o que é, não tenho ideia. Tipo assim, são umas contas gigantescas, e eu tenho que pensar como que eu vou caracterizar. Eu estou tentando fazer isso, mas então, eu não sei exatamente dizer que forma teria isso, não sei dizer ainda se é uma categoria acessível, mas primeiro eu posso olhar para esse escopo que vem da dualidade igual a Gabriel-Ulmer, ou eu posso olhar para esse teorema topos teorético, assim, que dá um espaço lógico. Mas, na prática, assim, isso aqui, esse embedding aqui, na prática, é meio que um teorema de complexidade. Mais ou menos isso. Então, eu estou pensando como é que vai ser isso. Estou tentando descobrir, se alguém tiver alguma ideia, né? Mas ainda tem algumas questões. Você perguntou da parte de árvore, né? Da parte de tipos. Tem uma estrutura de árvore, só que de categoria localmente cartesiano fechadas, eles preservam toda a estrutura, particularmente a estrutura dos termos. Só que eu não sei dizer especificamente como isso acontece. Então, tem alguma coisa a ver com a estrutura polinomial desses funtores, que, na verdade, são estruturas de árvore. E árvores são um pouco menos bem comportadas do que álgebras de Poole. Então, é meio que estou tentando descobrir ainda também. Tudo isso aqui eu não estou tentando descobrir. Mas tem coisas relacionadas ao teorema da definibilidade de Beth, né? Coisas com relação à teoria de conjuntos abertos, né? A teoria da construção espectral lá do Cole. Tem algumas coisas que eu estou explorando, mas nada disso é concreto ainda.
More questions? Let's think back again.
E voltamos às 4h05.
Hello, people. After such a good coffee with tasteful quitutes mineiros, and we have Mariano from USP. He's talking about from quantilis to a monoidal topology of Grothendieck. Please.
Thank you, William. This is a joint work with Ana Teoria. In fact, most of part of this work is containing her thesis. Oops. Ok, foi demais. Passou tudo. Okay, so that's the plan of the talk, a bit of motivation and context. Sheaves on semi-Cartesian quantals, the quantals that we consider here. Some notion of coverings, generalized Grothendieck topology that we call Grothendieck pre-lopologies. Sheaves on this topology. The monoidal structure associated, sheafification, a bit of subobject structure, applications, and ideas. So the main goal of all these tryings, let's say, is develop a kind of monoidal closed, but not Cartesian closed generalization of topos theory. We want, in one hand, generalize metric spaces, so connect with analysis, and also consider non-commutative geometric situations like sheaves and algebraic geometry over non-commutative rings. And as part of this scenario is have some clues that some form of internal linear logic is around all this stuff. The studies of logic and categories in my department began around the middle of the 90s with Chico Miralha and Marcelo Conilho and Andrés Brunner. And more recently, Ana Tenorio, Caio Mendes, and José Alvim are working this idea of monoidal topos theory. And our perspective is a kind of different from the perspective that Chico Miralha and the students that deals with quantals or locals. The quantals are Grothendieck quantals, that meaning that they are idempotent and have a kind of property like call it right-sided. So our quantals that we are in our view are non-idempotent, but for our examples, they are commutative. So they are generalization of locales that we talked about yesterday morning. Today morning, Ciro talked about yesterday morning. So a quantal is this, as Ciro have told, is a complete lattice that is also a monoid that holds this both these compatibility relations. When the monoid is commutative, given a compatibility relation, the other is free. So a local is a quantal where the multiplication is the infimum, and we are more interested in semi-Cartesian quantals that when this product does not necessarily coincides with the infimum, but there's always this comparison. Okay. Examples, all locales, as we saw earlier, every open subset of a topological space is a locale. A thing that in general is not a locale is the quantal of ideals of commutative unital ring. This is a semi-Cartesian quantal with multiplication. and the Lovir quantile that is the set of positive reals with added with infinite, with opposite order and the sum. This is related to the idea of connections with metric spaces. So locales are some form of algebrization or of intuitionistic logic, as Valeria told earlier, and we can say that topos, or in particular Grothendieck topos, are kind of categorification of locales, and quantiles, by analogy, should be as categorified, some form of corresponds to some form of propositional logic that is not intuitionistic, but have a multiplication that we can consider like a fragment of linear logic, and the categorification of the quantiles, at least the quantiles that we are concerned, should be some generalization of Grothendieck toposes. So that's the scenario. So very much like the diagrams that appear in these days at least 3 times, we have an equalizer diagram. We have here a supremum. This is the idea of covering. So the compatibility ratio is not when we take here the infimum, that's the pullback, but is something that is less than infimum. That's this product when the quantile is semi-Cartesian, and these are the restriction maps given by a natural generalization. And in fact, these P and Q are given by kind of projection that I will explain in a minute. And that's here that the hypothesis of that we have a semi-Cartesian quantile is essential. And a bit of spoil, if we consider a semi-Cartesian quantile, the sub-objects of the terminal object is isomorphic to the quantile. These have some consequences, okay? This is the strong one. Stronger of all. In general, this kind of category of sheaves is not a topos, not an elementary topos, and a Grothendieck topos neither. Just because the sub-objects of a terminal object should be Heyting algebra if we consider elementary topos. And there is some quantiles that are not Heyting algebras. For instance, quantiles of ideals of some non-trivial ring. So the problem with the quantile coverings, recall that the covering in the idea of in a local is given by supremum, and you have this stability axiom that gives this condition if V is less than U, and then the pullback of the covering UI, that's V meet UI, is a covering of V. In fact, it's a covering of V infimum or meet U, but since V is less than U, less or equal than U, this is the same that U. So almost the same thing holds for a quantile. But here we have to stop in this moment, just have this V times U. That is not V or not U in general. So this product is not, even if V is less than U, this is not V. Okay. So we have to generalize the notion of Grothendieck pretopology. So we consider here a monoidal category where the unit of the monoidal is the terminal object. We suppose that it have a terminal object. Examples of things like this, take the Cartesian category where the tensor product is the categorical product, or a semi-Cartesian quantile as a positive viewed as a category, or given a monoidal category, this comma category from here is calligraphical I, here is just I, but this comma category is monoidal semi-Cartesian is easy to see because the identity here, I to I, is the terminal object. So the idea of pseudo pullback, that is the generalization of idea of times in quantiles, is this one. We mimic the construction of pullbacks by products and equalizer and substitute this product by tensor product. We have some projections to mimic this because the quantile is semi-Cartesian. So the B has a unique morphism to 1, and here is the isomorphism of unitor. So this thing works like a projection in the first coordinate, and analogous way in the other using other unitor, we have another projection. So we can construct this pseudo pullback in general for semi-Cartesian category, and of course when we have the product, the tensor product is the product. This is the usual pullback, and in a semi-Cartesian quantile, this construction is just the product. The product of quantile. So a weak lopology for linear topology, the idea of Juan Melero, is copy all the initial axioms, so isomorphisms are coverings, stability of coverings under composition, and stability under tensor products is a very natural notion that these three properties are valid in many situations. But in fact, Grothendieck prelopology, we should ask another axiom that seems more complicated. So here we have a morphism from V to U, and we try to do a pullback of this covering until V, but this is not a covering of V, but is a covering of this other pseudo pullback. Fortunately, when this is a local, a quantile, semi-Cartesian quantile, this property holds, and in fact the axiom 3 subsumes the property 4. And for a Cartesian category, these axioms coincides with the properties of Grothendieck topology, and here is the axiom 3 that subsumes axiom 4. It's a calculation, easy calculation because of this. So we can consider the category of sheaves in a very same way. We can combine into categories like this by product coordinate-wise. You take just two semi-Cartesian monoidal categories, and we consider the product of this structure component-wise, and the prelopology is also put component-wise. This is another mixed construction, so we have some non-trivial examples of Grothendieck prelopologies, not so many, but there is at least one. In general, this if F is a sheaf in this notion, this is not a sheaf in general, but with some hypotheses or some assuming some things, this will turn out to be a sheaf. And why this property is interesting? Because we can put also this like an axiom that we could be useful. This is called the strong prelopology. So in this situation, when 5 axioms holds, this the another axiom, then we can produce a monoidal structure that is Cartesian closed in the category sheaves. So the idea is the following: we can pass from the monoidal structure on C to the monoidal structure on the category of pre-sheaves of Xi by the convolution. This is a co-n, but you can see like a extension of the tensor product. Then this is the Yoneda embedding. It has a closed monoidal structure given by the convolution, and do a certain sheavification that I will explain very quickly. We can change or to transport the monoidal structure from pre-sheaves to sheaves. So quickly, this is a technical stuff, how to define sheaves and how to show that there is a left adjoint of the inclusion. This is an encoded thing, but the important thing is that the sieves does not explain how to work with prelopology. Sieves are not enough. Subfunctors are not enough. So this map in general is not a subfunctor of the Yoneda of home functor, but we can applying Yoneda again, we can show that this condition of sheaf is equivalent to orthogonality condition. And why orthogonality condition holds? Because this category is locally presentable, in fact, for some regular cardinal lambda. And so it's a lambda orthogonality class because we consider a small category and take a large regular cardinal, not a large cardinal, but a big enough large cardinal, regular cardinal. So it's it is a reflexive subcategory by a theorem of Gabriel Ulmer, and the inclusion preserves colimits lambda filtered. So it's a locally presentable category, so it's complete, co-complete, well-powered, has a set of strong generators, and all of this is useful to produce this normal enrichment. That's this thing that I mentioned here. This is Anna found in a mysterious paper of Day from '73, this condition, and this shows that, in fact, this when we apply the adjoint functor to the tensor product of Day convolution, this gives not only a monoidal structure in sheaves of C, L, but also a monoidal closed structure. This thing. So we have also this quantile information that's very similar to that holds in topos, but not the same thing. Here's again, this is the same result. We have some parallels. Okay. There's some work with Anna Teoria and Peter on check homology in this, at least for the quantile coverings, but we can define this also for these pseudo-Pullbacks conditions. That's some results that compares the cohomology, spatial cohomology with the ring cohomology or the quantile cohomology. Here, this almost thing, and I passed through this. Okay, this is the idea of categorification. I explained already, and some possible questions that we don't know very much about the properties of the left adjoint. This is essential to produce many results in topos theory. Have a precise description of the left adjoint, the sheafification functor, and extend some mathematical applications concerning chief cohomology in the setting, and of course the idea of in the back of the hand is consider what is the internal logic with these categories that is not a topic in general, but without going any further research on this. Thank you. Collaborators, Caio, José, Peter, and Anna, of course, and how many people want to deal with this, you will be welcome.
Thanks. Questions or comments?
Can I see the criterion again? Can I see the day criterion again? Yeah. Do you mind reading? I mean, what was exactly that he said in 72?
That this condition is enough to have a Cartesian closed structure. This is fancy thing for basically this explain exactly this. It's more than a Cartesian closure structure induced in this category, but have some other properties, but basically is what we need. Okay. So here we can see D like the category sheaves, and D, this condition is exactly the axiom of derivation of the axiom of strong pretopology. In the case of that we have in hands, that mean the quantile, we have shown this property, and also for the Cartesian classical case, this is also a sheaf if whenever F is a sheaf. So for the product construction of a quantile with a Cartesian or Grothin topology, this also holds, but for the general case we don't know, so we put as an axiom, and this guarantees that always this is a Cartesian closed and monoidal category.
Thank you.
More questions? Let's thank Professor Wu again.
Direita passa, da esquerda volta. Laserzinho.
Switching to Portuguese. Agora nós teremos Gabriel Luiz Adrião, da Unicamp. Ele vai falar conosco a respeito de Machines, a Generalization of Logics.
Oi, gente, tudo bem? Apresentar uma pesquisa que eu desenvolvi com a minha orientadora, a Ítala, lá do CLE. É uma construção que está um pouco defasada já na nossa pesquisa. Está um pouco defasada já na nossa pesquisa, do meio do ano passado, mas ainda assim é um resultado levemente interessante. Então, daí está a apresentação. A ideia é construir uma categoria que a categoria das lógicas seja uma subcategoria delas e vai ter algumas propriedades interessantes. Para começar, a gente vai falar sobre a categoria das lógicas, da forma como a gente está trabalhando. A primeira coisa é a definição do operador de consequência de Tarski, que é uma forma de abstrair a noção de derivabilidade. Então a gente vai ter esse operador aqui que vai agir sobre o conjunto potência de algum certo conjunto. Esse conjunto X é para representar o conjunto das fórmulas. Ele vai ter que seguir 3 propriedades principais. A primeira propriedade é que ele vai ter extensionalidade, né? Então que você tem o A, ele vai estar contido na consequência de A. A lógica é que você tem um conjunto de premissas. As consequências dessas premissas, as premissas são consequências delas mesmas. É isso que justifica isso. O segundo é monotonicidade. Então você tem um conjunto de premissas que está contido num outro conjunto de premissas. Então as consequências do primeiro conjunto estão contidas nas consequências do primeiro, porque você só adicionou mais premissas, isso justifica filosoficamente. E o fim aqui é a idempotência. No caso, isso daqui não é exatamente idempotência, tem que juntar isso com aquilo, aí você consegue idempotência, que é a lógica de ser um operador que vai agir só uma vez, né? Então você vai pegar umas premissas e com uma operação desse operador você vai conseguir todas as conclusões que são deriváveis a partir desse conjunto. Nesse trabalho, a gente está trabalhando com lógicas contáveis, então lógicas vão ser um conjunto que vai ter esse conjunto de fórmulas e o operador de consequência de Tarski, e vai ser contável quando esse conjunto de fórmulas for contável. Vocês vão entender por que em breve. Para além disso, a gente está trabalhando na categoria das traduções entre lógicas. Então, a gente vai ter o conceito de tradução, que vai ser os morfismos dessa categoria, e vão ter 2 conceitos de tradução. O conceito de tradução e tradução conservativa. A tradução ela vai ser uma coisa que vai preservar a derivabilidade. Então, se você tem o X como um elemento das consequências de algum conjunto de premissas A, então a tradução de X vai estar na consequência da tradução de A. A tradução conservativa é a mesma definição. A diferença é que, em vez de aqui ser uma implicação, você tem um C e somente C. Então, você vai ter mais estrutura sendo preservada. Aqui eu vou apresentar o conceito de máquina que vai ser usado. No fim, vocês podem ver uma definição bem simples, e é exatamente a definição de um sistema dinâmico discreto. Então, você vai ter o X como o espaço de estados da nossa máquina, e o F vai ser a função de interação. O que a gente pode pegar uma coisa nesse sentido. Cada bolinha ali vai ser um dos estados que a máquina está, a interação vai dar um estado ou outro. Vai ter construções que são... Está funcionando, né? Estava sem óleo. Pode fazer uma coisa nesse sentido, então você vai ter uma máquina uns estados que vão ser levados a ciclos e vão ser fechados e continuar neles eternamente, ou estados que chegam em construções tipo essa, né, que você tem meio uma continuidade central e que chegam nela e ficam presas dessa continuidade, e por fim estados que continuam eternamente para frente. Essas são as 3 construções primordiais que uma máquina pode ter. Para adicionar um pouco de estrutura nisso, antes de falar disso, a lógica de construir algo assim é tentar fazer a generalização do operador de consequência, porque, como a gente falou, a gente tem 3 axiomas que são necessários serem existir no operador de consequência. Porém, isso não engloba todas as lógicas. Existem algumas lógicas que não cabem no operador de consequência. Por exemplo, lógicas não monotônicas não cumprem esse segundo axioma. Lógicas abdutivas também não entram no operador de consequência. A questão é, como é que a gente pode retirar essas premissas, esses axiomas, de forma a não perder completamente a estrutura? Porque uma vez que a gente vai tirando essas axiomas, a gente vai tendo muito menos coisa para poder trabalhar. A lógica, então, é retomar a estrutura A lógica, então, é retomar a estrutura ao observar o funcionamento iterativo desse operador. Então, em vez de a gente exigir a estrutura estando na própria forma que o operador tem, a gente exige a estrutura na forma como ele se comporta com o funcionamento iterativo. Então, para isso, a gente vai construir algumas coisas. O primeiro é a órbita, que é a mesma coisa de sistema dinâmico, vai ser todos os estados que são acessíveis por um estado inicial. Então, a órbita de X, por exemplo, naquele caso ali, daquele primeiro, a órbita de x vai ser esses 4, forma esse ciclo. A órbita daqui vai ser tudo aqui para frente, etc. Por fim, a gente vai ter um componente fechado, que a lógica disso é meio que uma generalização da noção de uma órbita cíclica aqui. Então, por exemplo, esses 3 aqui que estão fechando um círculo aqui, vão ser um componente fechado. Para além disso, isso daqui, esse torre central, também vai ser um componente fechado, a partir dessa definição. Porque a definição é ter um componente, que vai ser um conjunto de estados dentro da máquina, que você vai ter a função f como sendo objetiva. E aí você vai conseguir definir uma forma de você sair daqui e ir para frente e, ao mesmo tempo, voltar. Porque você vai ter uma objetividade dentro desse eixo central. Essa é a lógica, e com isso é meio que imaginar um ciclo infinito, mais ou menos. Beleza. Agora a gente vai definir o fecho de um certo elemento, que no fim vai ter 2 casos. O caso em que ele entra num componente fechado, seja um ciclo, um desses generalização de ciclo infinito, o fecho vai ser o próprio ciclo. No caso de não ter algo assim, por exemplo, esse caso aqui, o fecho vai ser a sequência, vai ser a órbita. Então, o fecho desse elemento aqui, por exemplo, vai ser ele, incluso tudo que vem depois. Beleza. Com isso, a gente começa a falar de conversões, que vai ser o análogo das traduções para as máquinas. Ela vai ser muito parecido, a gente também vai conseguir definir conversões e conversões conservativas. E a lógica é o seguinte, você vai querer preservar o fecho. Então você vai ter que uma função juntando o conjunto de estados de 2 máquinas, vai ser uma conversão. Se você tem algo que está no fecho de y, o x está no fecho de y, então a conversão de x está na conversão, no fecho da conversão de y. E, similarmente, para transformar isso numa tradução conservativa, em vez de você exigir implicação, você exige um sei somente sei aqui, né? Aqui a gente tem um teorema de classificação de conversões. A gente vai ter que uma conversão, vai ser uma função vai ser uma conversão, se você tem essa relação. Então, a conversão de um fecho de x vai estar contido no fecho da conversão de x. E a mesma coisa para a conversão conservativa, só que em vez de ser contido, é uma igualdade. Bom, é isso. Isso daqui é bem parecido com a definição uma definição equivalente das funções contínuas, né, de você pegar o fecho, a imagem inversa de um conjunto fechado ser um conjunto fechado. A diferença aqui é que, em vez de ser imagem inversa, é a própria imagem. O que quebra um pouco a lógica das traduções, porque nas traduções a definição equivalente de tradução é exatamente igual. É a imagem inversa no conjunto fechado ser fechado. Bom, isso daqui vai definir 2 categorias, a categoria das máquinas conservativas. E beleza. Agora o que vai fazer vai ser o resultado, de fato, dessa pesquisa, que é mostrar o embedding da categoria das lógicas nessa nova categoria que foi construída aqui. Para isso, a gente vai pegar uma lógica contável, né, uma lógica numerável, que eu defini lá no começo, e a lógica de ser o motivo para ser uma lógica numerável é porque a gente está trabalhando com coisas que são funções iterativas, né? E como a gente não tem uma noção de topologia sobre os estados da máquina, a gente não consegue passar a princípio de um número de estados finito, né? Uma órbita seja numerável, por exemplo. Então não daria para passar para mais a princípio. Aí com isso a gente vai definir o número de estados como o conjunto das partes das fórmulas, né? Então todas as subconjunto de fórmulas de x, cartesiano o conjunto de fórmulas, e adicionar um estado dummy aqui, que vai ser só para o caso em que você tem uma consequência que não tem nenhuma fórmula. E aí a gente vai definir componente de consequência de A, que vai ser para o A vazio, você vai adicionar o dummy, mas no geral você vai ser um elemento que vai ter A, né, porque você está pegando consequência de A, e o x vai ser todo elemento que está na consequência de A. Então, no fim, você vai acabar formando meio que para cada conjunto A, você vai formar algo parecido com isso. Com isso daqui. Então, você vai deixar o componente de consequência, você vai adicionar um valor, um estado, para cada um. Se for infinito, vai ser uma linha assim. Se for finito, vai formar meio ciclo. E aí a gente vai impor uma ordem a isso da seguinte maneira. A gente vai pegar uma bijeção que vai sair dos inteiros módulo R, se você tiver um componente de consequência com módulo R, e aí você vai fazer uma bijeção entre esse conjunto e o componente de consequência, e se for infinito, você vai fazer uma bijeção entre os inteiros e o componente de consequência. Com isso, a gente vai definir uma função, que vai ser a função da máquina. Então, a gente vai fixar uma família de componentes de consequência, de ordenação do componente de consequência, que eu estou descrevendo assim, e a função induzida vai ser o seguinte: você vai pegar para um S pertencente a um desses componentes de consequência, você vai fazer que meio que uma iteração. Então, você vai pegar qual que é o índice do S na ordenação, somar 1 e depois voltar. Então, se você fez uma ordenação aqui, a função de aplicação vai ser isso. Se você tiver, por exemplo, isso daqui é o índice 0, isso é 1, isso é o 2. A função de ordenação vai levar esse nesse, esse naquele e esse naquele. Isso se o S estiver na consequência de A. Se não estiver, a gente vai jogar todos os que não estão para o estado com ordenação 0. Então, é realmente esse cenário aqui. Você vai ter, aqui vai ser todos os elementos que estão na consequência, e aqui são todos os que estão fora. E aí você joga eles para no meio. Se for um conjunto de consequência finito, você vai jogar para esse ciclo aqui. Bom, e aí, se for finito, você vai ler os índices como pertencentes ao os inteiros módulo R. Se for infinito, vai ser os inteiros mesmo. Beleza. Aí com isso você constrói uma máquina, por definição, né, que você vai ter um estado e uma função agindo sobre esse estado. É uma máquina, um sistema dinâmico, no fim das contas. E a proposição é que todos esses componentes de consequência EC vão ser componentes fechados da máquina induzida. Que é aqueles componentes fechados que eu introduzi lá no começo, que é ou um ciclo ou uma generalização de ciclo infinito aqui. Com isso, a gente tem esse resultado aqui, que a gente vai ter que, para uma lógica contável x, c, a gente vai ter que a máquina induzida dela, e para todo o y que está numa consequência de A, o y vai estar na consequência de A, sem somente C, o estado formado por A e y está no fecho desse estado AX. Então você meio que passa toda a informação estrutural do operador de consequência para essa construção de máquina. Beleza. Aqui tem um resultado de independência, que até agora a gente tinha escolhido uma ordem para cada um das máquinas que a gente está fazendo, né? A máquina estava dependendo de uma ordenação, e essa ordenação existiriam infinitas, e esse é um resultado que mostra que a ordenação não importa. No fim das contas, se você escolhe uma ordenação ou outra, as máquinas geradas vão ser isomórficas. Tanto por traduções, conversões conservativas. E esse aqui vai ser o isomorfismo. No fim das contas, a gente vai pegar uma ordenação, o valor de ordenação de um elemento de A, da consequência de A, por exemplo, e vai jogar para a ordenação, tipo, a ordenação O', a gente vai jogar para OA com o mesmo índice. Se fosse O, a gente vai jogar para A' com o mesmo índice. E se estiver fora do componente sequência, a gente vai jogar ele para ele mesmo. Porque não importa, a ordenação só age sobre os componentes, sobre os elementos que estão no componente de consequência. Então, no fim, a gente só está falando assim, as ordenações não importam. A gente vai pegar essa ordenação e jogar o mesmo elemento que tem a ordenação I no elemento da outra ordenação com valor I. Beleza. E aqui é o resultado principal. Com todas essas informações, a gente consegue construir um funtor da categoria das lógicas com traduções para a categoria das máquinas. Então, a definição é simples. Você vai jogar as máquinas, uma lógica. Aqui a TRE é a categoria das máquinas, das lógicas numeráveis. Vai jogar uma lógica para a máquina induzida dela, beleza? E vai pegar uma tradução e vai jogar a tradução, por exemplo, T, que vai de xC1 até YC2, você vai jogar para a conversão que leva o subconjunto A para a tradução de A e o subconjunto X para a tradução de X. Se for um elemento dessa forma. Se for o dummy state, que eu falei, você vai jogar para o dummy state de novo. De novo, esse dummy state é só para caso você tenha uma lógica que a consequência do subconjunto vazio seja vazio. E aí você conseguiria fazer essa construção aqui. Beleza. E aí esse teorema falava que essa construção aqui é um funtor, e mais que isso, é um funtor faithful e ele é injetivo em objetos. Então, a tradução a categoria das lógicas enumeráveis é isomórfico a uma subcategoria das categorias das máquinas. Isso vale tanto para a categoria das lógicas enumeráveis quanto para a categoria das lógicas com traduções conservativas. Então vale para as traduções e para as traduções conservativas. A diferença é que aqui vai ser as máquinas normais e no outro caso vai ser as máquinas conservativas. O que é interessante disso, porque generalização só vale a pena se você consegue a preservação de algumas propriedades, né? Para além disso, você tem que ter algum motivo para generalizar. Aí a dúvida que fica é que outras coisas são máquinas. Lógicas que não são tarskianas são máquinas, que você consegue fazer a mesma construção. Para isso, a gente nunca exigiu idempotência, não exigiu monotonicidade, não exigiu extensionalidade, etc. Então, você consegue colocar lógicas não tarskianas como lógicas, como máquinas. Autômatas celulares são máquinas. Você vai construir os estados como o estado de uma grid, e a função iteração vai ser a função iteração global desse autômata celular. máquinas de Turing determinísticas vão ser máquinas também. Você consegue imaginar por quê. Os estados vão ser a configuração da máquina de Turing, e a função de iteração vai ser a iteração da máquina. E como, particularmente, diretamente, você tem que qualquer sistema dinâmico discreto vão ser máquinas também. Por que isso é relevante? A busca por um formalismo unificado entre lógicas, objetos matemáticos, objetos lógicos e objetos computacionais. A gente está tentando fazer sentido de objetos computacionais a partir da relação entre eles. Como é que a gente faz a mesma coisa que a gente faz quando a gente estuda lógicas a partir de traduções, ou como quando a gente faz categorias no geral, né? E é isso, né? O que eu já falei, que é generalizar a categoria das lógicas para lógicas não tarskianas, e isso tentar explorar a conexão de sistemas computacionais e lógicos. Para continuar, eu quero procurar outros formalismos, outras abstrações que unificam objetos computacionais e objetos lógicos. Quero tentar explorar o que seria semanticamente, o sentido semântico de traduções conservativas, né, que objetos semânticos são conservados, etc. E se isso é traduzido para máquinas, e explorar conexões entre máquinas e coálgebras, que são objetos que são bem parecidos com máquinas. É isso. Muito obrigado.
Perguntas, comentários?
Você podia comentar brevemente, que você falou no início que você tem uma nova proposta, né, posterior a isso?
Ainda está muito no começo, mas a lógica seria você... Aqui no... Caralho. Pode ir? Tá. A ideia que eu estou tendo agora, também é algo que ainda não está muito desenvolvido, mas aqui na definição de máquina, exigir que o X seja um conjunto de potência. Que com isso você vai ter um funtor muito mais simples, que vai ser da categoria das lógicas para a categoria das máquinas, porque você consegue meio que fazer assim, quase direto, né, com toda a lógica, todo o operador de consequência com um conjunto vai ser uma máquina diretamente. E outra coisa interessante é que se você for analisar, por exemplo, sistemas dedutivos, que você vai ter o operador de consequência não idempotente, que você vai estar pegando um conjunto de premissas, aplicando uma vez, você pega todas as teoremas que são dedutíveis a partir de uma aplicação de uma regra. Aí aplica duas vezes todos os teoremas que são dedutíveis a partir da aplicação de duas regras, etc. Isso ainda vai ser uma máquina, e se você pegar o limite disso por infinito, você volta para o caso tarskiano. E aí você vai retornar para o que é. Então você conseguiria, provavelmente, fazer uma disjunção entre as máquinas e as lógicas, que você teria ido à volta. Mas ainda não desenvolvi isso completamente.
Obrigado.
Então, assim, eu não consegui acompanhar todas as definições, mas achei bem legal. Mas existe um livro do Lovir, né, que, na verdade, ele chama isso daí de autômata. Né?
Autômata.
E o livro dele basicamente é um livro que ele ensina a teoria de categorias a partir das propriedades categoriais, principalmente desse objeto. É um livro bem legal, assim.
Esse objeto é um sistema dinâmico discreto, assim.
Esse objeto aí. Esse objeto. Eu não sei, assim, eu acho que você gostaria de ler, chama Conceptual Mathematics.
Conceptual Mathematics.
Do Lovir.
Tá, eu vou
tem várias coisas aí que, enfim, eu acho que poderiam ser relevantes. Eu já li o livro, fiquei olhando, é bem legal. Se quiser conversar depois.
Vou dar uma olhada.
Bem legal a apresentação, parabéns. Queria saber sobre como essa discussão poderia, por exemplo, se encaixar com as questões... Não sei se você pensou sobre decibilidade de lógicas e saber se uma lógica é decidível a partir desse maquinário aí que você...
Eu acho que não se aplica tanto, porque na construção que a gente tem de máquina, ela é não construtiva, né? Então a gente acaba, de máquina induzida, a gente acaba já exigindo... Caraca, aqui, ó, para construir esse operador componente de consequência, a gente acaba já exigindo meio que a definição completa do operador de consequência. Então, se a gente tem uma construção completa do operador de consequência, é porque a gente já tem toda a informação. Então acaba não sendo muito útil, né? Porque para a gente conseguir fazer essa máquina funcionar, a gente tem que já ter informação completa sobre a máquina. É mais uma demonstração, assim, no sentido teórico mesmo, abstrato, de que isso funciona. Não acho que vai ter tanta usabilidade prática, pelo menos não dessa forma.
Nosso tempo acabou, depois podem buscar o Gabriel. Obrigado novamente.
Alô, alô, alô. Foi? Tá. Isso. Eu vou ter que usar a coisa aqui, a luzinha. Tá legal. Posso começar? Hi, my name is Eduardo Ox. I work at UFF, Universidade Federal Fluminense, but in a small campus called Puro at Rio das Ostras. I used to be a professor there, but I'm temporarily in another position working as psicopata do Cefet. I'm going to explain that later. Let me make an introduction. I was going to present something, but then I had a very nice idea and I decided to present something else. I was, or I am, a very incompetent category theorist in the sense that everybody understands the unit dilemma except me. No, sorry, now I understand, but for many years I didn't understand it well. Why? What was going on? And how could I diagnose the problem in a way that would let me fix it? One thing that I knew was that my working memory was relatively weak, and sometimes I could understand concepts from category theory by drawing lots of diagrams, but knowing that wasn't enough for solving all my problems. Then, a few years ago, I started to study mathematical education to understand some difficulties of my students, and lots of ideas fell into place. In short, mathematicians, at least all mathematicians that I know, they don't even know that mathematical education exists. Here are some books, articles, and chapters on mathematical education. For people that work on mathematical education, they are canonical in some sense. But even in books like the books by Eugenia Chang or by David Corfield, they don't cite them, so no one knows that. And one thing that I thought was that I could start my talk by apologizing profusely, of course, and by saying, people, my talk may look trivial, but at least you will learn a bit about an area that mathematicians know nothing about. More introduction. A few days ago, I found some nice technical things to present. It's a family of operations with omitted names that work like this. I'm going to explain it soon. Let me explain what is an operation with an omitted name. In some cases, like this one, the juxtaposition here means multiplication is an operation that was elided, but whose name we know. And we can write it explicitly by adding a dot, like this. In other cases, the operation doesn't have a standard notation, and we have to improvise For example, we can use the symbol F to denote application, and we can use this S to denote substitute. So this thing here becomes this, and this thing here becomes this. And here are some variants of the application. These are the operations that I prefer to omit their names. If we just started by, by applying this functor F on this diagram here, we would obtain this diagram here. If we apply this natural transformation here to this morphism here, we obtain this commutative square. So all these things here, plus the guarantee that the square commutes. And the novel thing here is that we can omit this name and we can omit this name, and things are going to make sense in a formal way. We can formalize what is going on here. Okay, what is the unit dilemma? Let me start with something simpler. What is an elephant? Not the book about topos theory. This elephant here, this is a drawing of an elephant. When a child sees a real elephant for the first time, even if the child have never seen a picture like this one, or heard it spoken of before, if you point your finger at the elephant and say, that's an elephant, the child knows immediately what you're talking about. And this is not very obvious. Why the child decides that this is an elephant and not this is an elephant or this? Why the child prefers to think that the elephant is this whole thing? And how we can apply this idea to the unit dilemma? So what is the unit dilemma? And what is the drawing of that? And what is a drawing of the unit dilemma? One thing that is discussed a lot in mathematical education is how memory works, how understanding works, and a good part of understanding in mathematics means summarizing and then reconstructing things from the summary. And this is a quote from a book. He stressed that the reconstructive nature of memory. What is remembered is not an exact copy, but a stripped down version of the original. And this figure here is from the introduction of my first article that was exactly about this idea of reconstructing things from their shapes, categorical concepts from their shapes. And this is how I remember the Frobenius property. I usually forget the letters that people put there, so I don't remember a formula. I remember a diagram, and I reconstruct the formula from it. I have another article that is called On the Missing Diagrams in Category Theory. That's true. It has an error in the second and the third words of the title. That is exactly about this idea, but much more formalized. And this is the shape of the unit dilemma. Not exactly the unit dilemma that we use most of the time, but one of the parts of the unit dilemma, one of the parts of the proof of the unit dilemma. And we can see that here we have something with the same shape with different letters. And this is exactly how MacLean proves the unit dilemma in his book, Categories for the Working Mathematician. And this is my favorite choice of letters because I hate the letters that MacLean chooses, so I prefer to use mine, in which the letters indicate temporal order. A comes before B, that comes before C as we draw things. And in my formalization of a diagrammatic language, if I say just this diagram, it has a meaning that is, the meaning of this diagram is its top-level operator, that is this curved arrow here. We can translate it to this thing here. And the interpretation of this is there is a natural bijection between this thing and this thing here. And here are some of the conventions. The conventions have names. CD means certain conventional diagrams. Here is above usually means inside, and so on. Here we have other conventions. But anyway, so I had several criteria for finding a good diagrammatic language. One was that diagrammatic language had to help me to read several books in category theory, either all or at least a good number of them. And this diagrammatic language works well enough. So it had to be translatable to the languages of several books, and it had to be translatable also to other formalizations like type theory. So at some point I'm going to learn lean, and this is going to be easily translatable to lean, for example. So this is a translation of this thing to type theory. Note that we have to declare C first is a category. This thing is inside that category. We start by declaring these two objects here. Then we can declare this morphism here. But no, there's an intermediate step. We first define this arrow here, and this arrow is a home set. So after defining these two objects, we define this home set here, and F is an element of that home set. And if we do things in that way, this diagram also makes sense. It can formalize that as we have this category here, this object in that category, this other object, and this home set here, and our declarations stop at that point. This is my favorite way of drawing adjunctions, my favorite shape for drawing adjunctions. My favorite general adjunction is L is left adjoint to R instead of using F and U. And I consider that L is a functor that goes to the left, and R is a functor that goes to the right. And the adjunction itself is this bijection here with some natural properties. So we have the same two things with the same shape. This is a generic adjunction. This is the adjunction that we usually explain first. And we can expand this diagram here, this one, to this big diagram here, in which we add names for this morphisms. We add the unit and co-unit. We add the functions and so on. So let me go back to the Ionia dilemma. The Ionia dilemma is this big thing here. That is, it has lots of symbols, and I find these symbols here very hard to understand. So what I usually do is that I remember this part at the top, and then I try to reconstruct the rest. Sometimes I omit this thing here, and I add it at the end, but this thing is easy to remember. And this thing at the bottom is, here we have a functor and another functor, and a natural transformation here. And what this part of the Ionia dilemma says is that we have a bijection between these morphisms here and these natural transformations here. So the problem is, how do I reconstruct these names here, in the sense that my memory is very small, okay, and I have to reconstruct them in some way. And here is the trick. We start by this thing here. I start by this figure, and I add this other part at the bottom. And I think that each morphism here has to generate a commutative square from this home set to this one, to this one, to this one, etc. These are the boring details. And I don't know what are the good names for these things. So what I'm going to do is that I'm going to erase all these names. And I'm going to give names to these things here that I want to discover. No, actually, I don't want to give a name to the natural transformation. I just want to discover who are F and G. In this smaller diagram here, I can think that I'm using one of those applications without a name here, variants of application here. I apply this natural transformation here to these morphism here, and I want to obtain this thing here. The colors indicate what are the home sets. So, I want to discover what are F and G here, and I can do that by guessing and testing. This is a very good guess. If I apply this thing here to this, I get this that is very close to this thing here. And, wow, that's it. We have more time for more questions.
Espera um pouquinho que você responde.
O que é?
Fica com o microfone aqui e você responde.
Não ouvi nada. Ah, tá legal.
Questions?
Então, assim, nós... Alô?
Alô, alô.
Não é exatamente uma pergunta do que tem aí, é mais um comentário em forma de pergunta para saber se eu entendi o ponto da apresentação.
Tá.
Que é, você tem uma determinada coisa que tem uma complexidade alta de ôneda para poder lembrar, lembrar e entender, e para fazer isso, ao invés de você tentar usar aquilo e tentar entender a coisa de maneira direta, você pega coisas mais simples, que você já entende, que é mais fácil de memorizar, coloca isso dentro de uma certa estrutura, e colocando essas coisas dentro da estrutura, isso vai conduzir aonde você quer chegar.
Exatamente.
E isso favorece memorização, porque você tem que lembrar de menos coisas, você se joga naquela estrutura sempre que você quiser lembrar. E por colocar dessa maneira estruturada esses dados, você consegue favorecer o entendimento, porque você não vai tentar entender a coisa de maneira direta por ela. Você vai derivar aquilo a partir dessas coisas mais básicas que você conhece, entende melhor, ou são mais fáceis de você tentar entender. E a relação estrutural estabelecida, você vai chegar no entendimento desse resultado final que você quer chegar.
Exatamente.
A ideia é essa.
Exatamente.
Tá. Então, entendi, eu não viajei aqui.
Exatamente, eu posso dar mais detalhes depois, mas a ideia exatamente é essa. Só faltou dizer uma coisa aqui, que é o seguinte, quem já tentou estudar pelo MacLane, por exemplo, sabe que algumas coisas funcionam por mágica. A partir do momento em que você encontra o nome de um funtor, você consegue deduzir qual é a ação dele, qual é a ação dele nos morfismos, nos objetos e nos morfismos. Então, os nomes têm poderes mágicos em teoria de categorias, e é o que aconteceu aqui. Eu comecei encontrando nomes, e aí eu suponho que eu vou conseguir reconstruir os outros detalhes depois. Quer dizer, eu sei reconstruir, só não fiz os diagramas.
More question? Let's thank Eduardo again.
Now because this is for the students, the Brazilian ones. Então, quem vai receber o auxílio, né, que a gente prometeu dos estudantes,